What's up, everybody? This is your boy Tech G, and I want to welcome you all to my CompTIA Network Plus N10-007 course. And the information that I will be presenting in this course is going to give you everything you need to know to successfully pass the CompTIA Network Plus N10-007 examination, assuming you properly study. The CompTIA Network Plus certification is an entry-level computer certification for PC computer service technicians, and the exam is designed to certify the competency of entry-level IT professionals in troubleshooting, configuring, and managing networks. So let's talk about some of the skills that you're going to learn. So the CompTIA Network Plus N10-007 exam will focus on 5 primary areas of study, which are also known as domains. You have domain 1, which is the networking concepts, and this will make up 23% of the exam. And this domain will focus on a variety of networking concepts and the implementation of them appropriately. You have domain 2, that's going to talk about infrastructure, and this is going to make up 18% of the exam. And this domain will focus on appropriate cabling, device, and storage technologies. You have domain 3, or the networking operations, and this is going to make up 17% of the exam. And this domain is going to focus on best practices to manage the network, determining policies, and ensuring business continuity. Then you have domain 4, the network security domain. This is going to make up 20% of the exam. And this domain is going to focus on physical security and common attacks while securing the wired and wireless networks. And then you have domain 5. This is the network troubleshooting and tools domain. This is going to make up 22% of the exam. And this domain is going to focus on the network troubleshooting methodology and appropriate tools to support connectivity and performance. And let's talk about the CompTIA Network Plus exam details. So the Network Plus N10-007, this is the latest and greatest exam version, and it was launched March 2018. Now, at the time of this recording, CompTIA has not scheduled a retirement date for this exam, but normally 3 years after the launch of an exam is when you can expect for the exam to be officially retired so they can begin introducing the latest version. The exam has a maximum of 90 questions. The questions are presented in multiple choice format, drag and drop questions, and performance-based questions. The exam has a 90-minute time limit, and in order to pass the Network Plus exam, you're going to need to score a 720 out of a possible 900 points, or get about an 80% on the exam. And it is recommended by CompTIA that a candidate be CompTIA A+ certified and have at least 9 to 12 months of networking experience. This exam is available in English, German, Japanese, Spanish, and Portuguese. And the company that is responsible for administering this test is Pearson VUE Testing Centers. And finally, the cost of the CompTIA Networking N10-007 exam is a whopping $338, ladies and gentlemen. Oh my. So those are the details of the CompTIA Networking Plus N10-00 examination, ladies and gentlemen. What you're going to do, you're going to go to a website called Pearson VUE. It'll be home.pearsonvue.com. And once again, I will put links in the description box below. First thing you want to do is you want to go click on this link where it says for test takers. You're going to click on that. You're going to click on schedule an exam. You're going to click on that link. It's going to take you to this page right here. You're just going to scroll down. Going to give you some useful information about all kind of wonderful things going on. You're going to want to click on schedule your exam right here. Then from there, it's going to give you some more useful information. Then it's going to say A to Z program list. You're going to want to click on the letter C for CompTIA. Then from there, it's going to present this drop down list. And then you're going to just scroll until you see CompTIA, which is right here. You're going to select CompTIA. And then from here, you are going to go about either signing in if you already have an account, or you're going to create an account. For this part of the video, I'm just going to be showing you guys a bunch of screenshots because some of this stuff requires me to put my personal information in there, and I'm not going to be showing you all my personal information. Like I said earlier, you're going to either sign in if you already have an account, or you're going to go ahead and create an account. And here's a screen showing you how to sign in. Like I said, if you don't have an account, you're going to go over here and create a web account if you are a new user. After that, you're going to be looking at the dashboard, and then it's going to present an option for you to view exams. You're going to click on that button right there. And then from here, you can type in the exam that you're looking for, or you just start scrolling down looking for certain exams. In this particular example, I've taken screenshots of the CompTIA IT Fundamentals Certification exam, and this is the one that we're going to focus on just for this demonstration only. All right, so I went through and I found the CompTIA Fundamentals exam, and here it is listed right here, the FC0U-61. That is the latest and greatest CompTIA IT Fundamentals exam. I click on that. Now, here it's going to ask you, how do you want to take your exam? So you're going to have two options that I'm familiar with. I'm not exactly sure what this I have a private access code is referring to, but you're either going to be taking this at a local testing center, or you're going to have the option to take it at your house. So we're going to go through both steps real quick to kind of show you what all this looks like to help you set up your exam. So in this example, we're going to go through looking at scheduling an exam for a local testing center. You would select local testing center, then you hit the next button. It's going to ask you the language, obviously English. Well, that's what I speak, but you would select whatever language that you are most comfortable with. You're going to hit next. Then it's going to show you the exam details. So it's going to tell you what exam you're taking, the FC0-U61 CompTIA IT Fundamental Certification exam. It's going to show you the price, $123, and it's going to show you the language that you are taking the exam in. And then you're going to hit next. Then it's going to ask you some information regarding as to whether or not you are a veteran using some government benefits like your post 9/11 bill. If you do use those benefits, you're going to hit yes, and then it's going to ask you to input some more information. If not, you're just going to check no and then hit next. From there, it's going to ask you to input your address, and then from there, it's going to populate the closest testing centers to where you currently live, and they will be displayed down here. It'll give a list of names, and then it'll actually show you the distance from whatever residence that you typed in up here to where the closest testing center is to you. And then you would just select whatever testing center that you want. And it says you can select up to 3 test centers to compare the availability. Then after you select the testing center, it's going to ask you to select a date. Now, here is where you might run into some issues due to all of the things that are taking place in the world concerning social distancing. So normally you would go here, it will have a bunch of dates for you to pick. You would select the date, select the time, then go through the motions of paying for your certification and booking your appointment. But over here, well, it's not presenting me any options. So I think I did a screenshot for why can't I find an available appointment? And I did. And this is the window that's going to populate. It's going to say the test center chosen has no available appointment times or is not open. Select a different test center. The exam delivery dates are not available. Check another month. The exam authorization window is not applicable for the month being searched. Or the exam may be available for delivery at your home or office through OnView. Consider selecting a different delivery option. OnView is going to be the online testing. So with this particular exam, I believe they're only offering this thing online due to all the social distancing taking place out there. All right. So with that being said, now we're going to go back and do the at-home testing or the at-home office options that they have presented right here. So if you select at-home office, it's going to tell you this right here. It says, are you going to be testing on this device and network? If so, you're going to have to run a pre-check to verify compatibility of your device and network before planning to take this exam in your home or office. If you skip, be sure to do a full system test before test day to avoid lost exam fees and launch delays. So what you're going to do, you're going to want to hit the run the pre-checks, and then this window is going to pop up right here, and it's just going to test your microphone, your internet speed, and your webcam. At the time I was taking these screenshots, I didn't have my microphone plugged in. That's why I got a big X right here, but if I did, then whatever mic you're using, you're going to have to get a green in order for you to be fully compatible, and then you would just hit the rerun button and bam, you should be good to go. After you do that, it's going to ask you to agree to some online exam policies. So you're going to get a couple paragraphs here that you're going to have to read or scan through, and then select the check boxes so that you can proceed. After you do all that, we're going to get back to the options that we already saw. It's going to ask you to select the language. It's going to tell you the price and the exam and what language you're taking the exam in. It's going to ask you if you're a vet or not. And then it's going to ask you to select the date. So over here, You just select whatever dates are not grayed out. And then it also says to avoid any issues on exam day, we recommend checking into your exam 30 minutes before the scheduled start time. This allows optimal preparedness, but does not guarantee an early admittance or start time. I would say check in at least 45 minutes to an hour early. That way you can make sure everything is good to go. Your computer's up and running. You got good internet. You told the wife, the husband, the kids, or the brother, the sisters, and the dogs to get out, give you your piece so you can do your thing up in here. Make sure everything is good to go, because what's going to happen is if you miss this exam time, guess what? Your voucher is bye-bye. You don't get another one. It is what it is, ladies and gentlemen. So you're going to want to make sure that you make this appointment and do not forfeit this voucher for any reason or whatever. After you do all that, you select a day. It's going to ask you to select a time, morning, afternoon. It's going to present a bunch of stuff. Change the times. You can show them in the 24-hour time. And then it's going to say, it's going to take you to your cart. So over here, it's going to say, hey, you got this exam. It's going to be taken in this language. This exam is X amount of minutes long. This is the day. This is the time. You can change the appointments at this point if you want. And this is the price, or you could just totally remove this thing altogether. And then you have the option to add another exam if you want to add another exam. You're going to scroll down on that same window. Then it's going to give you your confirmation contact information, your name, your telephone. You can edit all that stuff up. It's going to tell you the price of the exams. You're going to go to proceed to checkout down here. Then it's going to pop up this window that you're going to have to agree. It's going to tell you the CompTIA testing policies. It says admission policy. Please note this exam is proctored in English only. There is not an option for local language proctoring at this time. It says before the exam, it says visit the CompTIA online proctoring page and review information on exam policies and procedures, system requirements, and system tests. Complete the required system tests from the same computer and in the same location you'll be using on exam day. Corporate firewalls often cause issues while trying to take your exam. Please consider taking your exam in a setting without a corporate firewall. So try to take it at home if you can. But then it says review the identification requirements below. All right, so here's some of the ID requirements. So basically, you're going to have to show at least one valid form of unexpired government issued personal ID. The government issued ID must have your signature and a photo. So here's some examples. You're going to have a valid, unexpired passport, driver's license, military ID, some type of national or local ID, or a registration card, such as a green card, a visa, permanent resident. You're going to need to actually show that to the proctor. Then here's some other information pertaining to minors who are going to be taking the test. So for candidates who are 17 years of age and under, please note that the minor must have guardian authorization for each testing event. In addition, the minor must have a single form of photo ID, such as a school ID, and the guardian must be present during the check-in process and willing to show a proper government issued ID. So the stuff that we just talked about. Now here is the important stuff for exam day that you need to focus on. The day you take your exam, you're going to log into this account right here, www.pearsonview.com/CompTIA./on-view. You're going to click on your scheduled exam under purchased online exams. You're going to click begin exam and follow the on-screen prompts to complete the check-in process. Once you have completed the check-in process, you will be contacted by a proctor to begin your exam. Now, please note that you are required to have a clean and clutter-free workstation. During check-in, the proctor will ask you to perform a room and desk scan using your webcam and will inspect any materials near your website. So make sure you have a clean desk with nothing but your computer on it for the most part. That's it. No notes, no sticky tabs, no nothing. They are going to want you to take that webcam and scan the desk and make sure you don't have anything on your walls, because if you get caught cheating, guess what? Your voucher's gone and you fail the test, and you have to do this whole process all over again. All right, so after you do all of that, it's going to take you to the enter payment and billing page, and it's going to show you exactly how much the exam costs. Now, this is where you are going to enter your voucher number. So whatever your voucher number is that came to you in the email, you're going to put that number up in here, or some type of promotion code, but we're just going to assume you got a voucher. And once you hit apply, it's going to erase this price. That's it. Or it's going to change it. So let's just say you got a voucher to cover the whole $123. You hit the code, bam, this thing turns to zero. Or if you got a voucher saying that you get the exam for 50% off, this thing will turn to whatever $123 divided by 2 is? About $60 something, right? Then you hit apply. And then from there, it's just going to ask you to input your purchase, your credit card information, assuming you have a balance that you have to pay. So like I said over here, if you got it for 50% off, you put the exam code in, and then next thing you know, this thing changes to like $60. Go to this page where you're just going to have to pay $60 into your credit card information and all that great, wonderful stuff, and then hit next. And after you hit next, you booked your exam and you are on your way. And just to reiterate, the day you go take your exam, this is where you're going to go. You're going to go to pearsonview.com/CompTIA/onview. And these are the steps that you need to take so that you can take your exam. Like I said, please try to check in 45 minutes to an hour early. I know they say 30 minutes, but just give yourself a little wiggle room to make sure everything is nice and clean. Nobody's bothering you. Your system is fully functional. Your internet is good to go so that you can take this exam without any problems whatsoever. Because if you miss this exam time, guess what? Your voucher is gone and you have to go through the entire process again and pay for this exam or get another voucher somehow, some way so that you can get this certification. All right. So before we go, there's one final page that you guys want to go check out. You want to go check out the CompTIA candidate testing policies. You can do a simple Google search for CompTIA candidate testing policies, and it's going to give you some extra information pertaining to whether or not you have a disability and if special accommodations could be made for you, whether or not English is a second language for you, and if they can make accommodations for you, how they go about scoring the exam, the content of the exam, retesting, whether or not you need to provide a photograph, rescheduling, and the cancellation policy. Cancellation policy is very important. It says you must contact Pearson VUE at least a minimum of 24 hours prior to your exam appointment. Canceling or failing to appear for an exam will result in the forfeiture of your exam fee. So you need to, if you plan on canceling for any reason, you need to do it 24 hours before, or else it is what it is. You're going to have to pay for this whole thing all over again, ladies and gentlemen. And that's for rescheduling as well. So like I say, go visit this webpage, Candidate Testing Policies, so that you can get read up on the latest and greatest, so that you can go out there and successfully pass whatever certification exam that you are taking. In this video, you're going to learn about the purpose and uses of various networking ports and protocols. So let's talk about some ports and protocols. Let's start off with SSH and SFTP, which use port 22. So Secure Shell. This is a cryptographic network protocol for operating network services securely over an unsecured network. SSH is more secure than FTP and Telnet. Typical applications include remote command line, login, and remote command execution, but any network service can be secured with SSH. SSH servers housing data a client wants to retrieve utilizes port 22, and we need to have that port open to get access to the data. As previously mentioned, regular FTP, this is an insecure port, whereas Secure Shell FTP or SFTP is a secure way of utilizing TCP port 22 as it is run over an SSH session. Next, let's talk about DNS. So DNS or domain name system. This is a hierarchical and decentralized naming system for computers, services, or other resources connected to the internet or a private network. It associates various information with domain names associated to each of the participating entities. Most prominently, it translates more readily memorized domain names to numerical IP addresses, which are needed for locating and identifying computer services and devices with the underlying network protocols. In other words, DNS can be thought of as being the phone book of the internet. Instead of memorizing IP addresses to get a website such as YouTube, one can simply type in the URL or the Uniform Resource Locator, which is also known as the web address bar, such as www.youtube.com, and the DNS will match the name up to the IP address that is associated with youtube.com to take your client device to YouTube. When manually configuring an IP address, you typically provide the IP address of a DNS server or the IP addresses of multiple DNS servers as part of the configuration process. And some texts refer to DNS as either domain name service or domain name server, which is not all the way technically correct, but it is understood by those in the IT industry. Next, let's talk about SMTP, which uses port 25. So simple mail transfer protocol. This is a communication protocol for email transmission. SMTP uses port 25 to send email from a client system to an email server, which also uses SMTP to relay messages to a receiving email server. To configure email settings on the client device, just check with your ISP or the organization that provides internet access for the settings, such as the server type, whether you're using SMTP, POP3, or IMAP, the ports that are going to be used, the username and password for access to those servers, and the security settings as to whether or not you're going to be using SSH or not. Next, let's talk about FTP, which uses ports 20 and 21. So the file transfer protocol, this is a standard network protocol used for the transfer of computer files between the client and server on a computer network. FTP is also used by web browsers. To access an FTP site, you will use the prefix FTP:// Windows, Linux, and Mac, they contain a command line FTP program. You would just simply type FTP, press enter, and then type help at the FTP prompt to see the commands that you can use. FTP sites with downloads available to any user, they support anonymous FTP. And anonymous FTP is a means by which archive sites allow general access to their archives of information. These sites create a special account called Anonymous, and user Anonymous has limited access rights to the archive host, as well as some operating restrictions. Some FTP sites require the user to log in with a specified username and password. One drawback to FTP is that it is not considered secure due to FTP login credentials being transmitted and authenticated in clear text. And to increase security, you would use FTP secured with SSL TLS or FTPS, or Secure File Transfer Protocol or SFTP. Let's talk about TFTP, which uses port 69. So Trivial File Transfer Protocol is a simple lockstep file transfer protocol which allows a client to get a file or put a file onto a remote host. One of its primary uses is in the early stages of nodes booting from a local area network. TFTP has been used for this application because it is very simple to implement. Due to its simple design, TFTP can be easily implemented by code with a small memory footprint. It is therefore the protocol of choice for the initial stages of any networking booting strategy like BootP, Pixie, BSDP, etc. when targeting from highly resourced computers to very low resource single board computers and systems on a chip. It is also used to transfer firmware and configuration files to network appliances like routers, firewalls, IP phones, etc. But today, TFTP is virtually unused for internet transfers. Let's talk about Telnet, which uses port 23. So Telnet, this is an application protocol used on the internet or a local area network to provide bidirectional, interactive, text-oriented communication facility using a virtual terminal connection. A Telnet emulation enables a user to connect to a remote host or device using a Telnet client over port 23. A Telnet connection allows for users to Telnet into a computer that hosts their website to manage their files remotely versus simply downloading pages and files as if he or she would with an HTTP or FTP connection. And before a Telnet connection from a client can be established, a remote computer must already be configured to accept a Telnet login on port 23, and that port must be open before a login can take place. Now, to utilize the Telnet command on a Windows or Linux computer by way of a command line Telnet program, you would have to open a connection to a remote computer, followed by opening a command prompt in Windows or a terminal session in Linux, and then typing Telnet and pressing enter. For help command, you would just simply type help and then press the enter key. And Telnet has been removed from recent versions of Mac due to the standard practice of using SSH. But if Telnet is still needed, it is possible to install it. Let's talk about DHCP, which uses port 67 and 68. So Dynamic Host Configuration Protocol. This is a network management protocol used on IP networks whereby a DHCP server dynamically assigns an IP address and other network configuration parameters to each device, such as PCs, printers, servers, routers, etc. on a network so they can communicate with other IP networks. A DHCP server enables computers to request IP addresses and networking parameters automatically from the ISP, reducing the need for a network administrator or a user to manually assign IP addresses to all network devices. In the absence of a DHCP server, a computer or other device on the network needs to be manually assigned an IP address or to assign itself an APIPA address, the latter of which will not enable it to communicate outside of its local network. If you get your address from a DHCP server, you are getting your address assigned dynamically, and it could change periodically. Some devices on the network, they require static addresses that do not change, such as printers and servers, which have to be assigned manually by a network administrator. This enables these devices to be more reliable and easily accessible over time. And DHCP uses port 67 and 68, whereas UDP port 67 is the destination port of a server, and UDP port 68 is used by the client. Let's talk about HTTP and HTTPS. So Hypertext Transfer Protocol. This is an application protocol for distributed collaborative hypermedia information systems. HTTP is the foundation of data communication for the World Wide Web, where hypertext documents include hyperlinks to other resources that the user can easily access. So for example, by a mouse click or by tapping the screen in a web browser. HTTP is used by all major web browsers such as Internet Explorer, Microsoft Edge, Firefox, and Chrome. HTTP for unsecured sites use the prefix HTTP : //, whereas sites that are secured with various forms of encryption, such as HTTP Secure or HTTP over SSL, which is also known as HTTPS, they use the prefix HTTPS : //. HTTP uses port 80 and HTTPS uses port 443. To check to see if a website is secure, most browsers, they will display a closed padlock symbol right next to the website's address in the web address bar. Let's talk about SNMP, which uses port 161. So Simple Network Management Protocol. This is an internet standard protocol for collecting and organizing information about managed devices on IP networks and for modifying that information to change device behavior. Devices that typically support SMTP include cable modems, routers, switches, servers, workstations, printers, etc. And they are often incorporated into software known as Network Management System, or NMS. The NMS is the main software installed on a computer known as a manager that controls everything SNMP based. The devices to be monitored are known as managed devices, and NMS installs a small piece of software known as an agent that allows the NMS to monitor those managed devices. And once again, SNMP, it uses port 161. Let's talk about RDP, which uses port 3389. So Remote Desktop Protocol. This is a proprietary protocol developed by Microsoft, which provides a user with a graphical interface to connect to another computer over a network connection. The user employs RDP client software for this purpose, which is known as Remote Desktop Services, while the other computer must run RDP server software or remote desktop connections. And once again, RDP, it uses port 3389. Let's talk about NTP, which uses port 123. So the Network Time Protocol. This is a networking protocol for clock synchronization between computer systems over packet-switched variable latency data networks. NTP is intended to synchronize all participating computers to within a few milliseconds of coordinated universal time. It uses the intersection algorithm to select accurate time servers and is designed to mitigate the effects of variable network latency. NTP can usually maintain time to within tens of milliseconds over the public internet and can achieve better than 1 millisecond accuracy in LANs under ideal conditions. Asymmetric routers and network congestion can cause errors of 100 milliseconds or more. The protocol is usually described in terms of a client-server model, but can as easily be used in peer-to-peer relationships where both peers consider the other to be a potential time source. Implementations send and receive timestamps using UDP port 23. They can also use broadcasting and multicasting, where clients passively listen to time updates after an initial round-trip calibrating exchange. NTP supplies a warning of an impeding leap second adjustment, but no information about local time zones or daylight savings time is transmitted. Let's talk about SIP, which uses port 5060 and 5061. So the session initiation protocol is a signaling protocol used for initiating, maintaining, and terminating real-time sessions that include voice, video, and messaging applications. SIP is used for signaling and controlling multimedia communication sessions in applications of internet telephony for voice and video calls, in private IT telephone systems, and instant messages over internet protocol networks, as well as mobile phone calling over LTE. The protocol defines the specific format of messages exchanged and the sequence of communications for cooperation of the participants. SIP is a text-based protocol incorporating many elements of HTTP and SMTP. A call established with SIP may consist of multiple media streams, but no separate streams are required for applications such as text messaging. The exchange data as payload in the SIP message. SIP clients typically use TCP or UDP on ports 5060 or 5061 for SIP traffic to servers and other endpoints. Port 5060 is commonly used for non-encrypted signaling traffic, whereas port 5061 is typically used for traffic encrypted with transport layer security. Let's talk about SMB, which uses port 445. So server message block, one version of which is also known as Common Internet File System or CIFS. This is a network communication protocol for providing shared access to files, printers, and serial ports between nodes on a network. It also provides an authenticated inter-process communication mechanism by way of using packets that authenticate remote computers. SMP uses ports 137 through 139 for SMB traffic using NetBIOS over TCP, also known as NetBT, and it uses port 445 for SMB hosted on TCP. CIFS was originally used as the standard method for sharing files via corporate intranets and the internet. CIF has now been widely replaced by updated versions of SMB such as SMB 2.0 and 3.0. Let's talk about POP3, which uses port 110. So Post Office Protocol version 3. This is an application layer internet standard protocol used by email clients to retrieve email from a mail server. Email is downloaded from the mail server to folders on a local system. For users who frequently switch between computers and or mobile devices, POP3 email is not a suitable solution for checking emails on multiple devices due to the email being downloaded onto only one device when the client device puts in a request. Users who utilize POP3 servers to retrieve email typically use SMTP to send messages. POP3 is the current version standard that is used, and once again, it uses ports 110. Let's talk about IMAP, which uses port 143. So Internet Message Access Protocol. This is an internet standard protocol used by email clients to retrieve emails from a mail server over a TCP IP connection. IMAP was designed with the goal of permitting complete management of an email box by multiple email clients. Therefore, clients generally leave messages on the server, which can be retrieved from multiple devices from any location until the user explicitly deletes them. IMAP 4 is the current version of IMAP, and to configure an IMAP based email account, you must select IMAP as the email server type. You need to specify the name of the server. You need to supply a username and password, and then you need to indicate whether the server is using SSL. And once again, IMAP uses port 143. Let's talk about LDAP, which uses port 389 and 636. So lightweight directory access protocol. This is an open, vendor neutral, industry standard application protocol for accessing and maintaining distributed directory information services over an IP network. Domain directory services, they play an important role in developing intranet and internet applications by allowing the sharing of information about users, systems, network, services, and applications throughout the network. As such, directory services may provide any organized set of records, often with a hierarchical structure, such as a corporate email directory. Microsoft refers to this as directory services, and LDAP, once again, it uses ports 389, and LDAPS or LDAPS over TLS SSL, it uses port 636. Let's talk about the H.323, which uses port 1720. So H.323 defines the protocols to provide audio-visual communication sessions on any packet network. The H.323 standard addresses call signaling and control, multimedia transport and control, and bandwidth control from point-to-point and multi-point conferences. It is widely implemented by voice and video conferencing equipment manufacturers. It is used within various internet real-time applications and is widely deployed worldwide by service providers and enterprises for both video and voice services over IP networks. Now let's start talking about protocols. So what is a communication protocol? So a communication protocol, this is a system of rules that allow two or more entities of a communication system to transmit information via any kind of variation of a physical quantity. A protocol defines the rules, syntax, semantics, and synchronization of communication and possible error recovery methods. And protocols may be implemented by hardware, software, or a combination of both. And protocols are designed to allow for applications to send and receive data via predefined ports on a network adapter to make connections to another computer. And port numbers on computers are used to identify protocols for the purpose of sorting various processes. So for example, if you want to visit www.technologyg.com, you would open up a browser and type http://www.technologyg.com. The hypertext transfer protocol, or HTTP. This is what is being used to make a connection to the web server known as technologyg.com. For the transmission of data, HTTP selects an unused outbound port on your computer to send and receive data to and from the web server technologyg.com. On the technologyg.com web server, port 80, which is the inbound port corresponding to HTTP, is open at all times to allow for a computer to make a connection to the technologyg.com web server. Let's talk about ICMP, so the Internet Control Message Protocol. This is a supporting protocol in the Internet Protocol Suite, or the IP suite. It is used by network devices, including routers, to send error messages and operational information indicating success or failure with communicating with another IP address. So for example, an error is indicated when a requested service is not available or that a host or router could not be reached. ICMP differs from transport protocols such as TCP and UDP in that it is not typically used to exchange data between systems, nor is it regularly employed by end-user network applications, with the exception of some diagnostic tools like ping and traceroute. Let's talk about UDP. So User Datagram Protocol is one of the core members of the IP suite. With UDP, computer applications can send messages, also known as datagrams, to other hosts on an IP network. Prior communications are not required to set up communication channels or data paths. UDP uses a simple connectionless communication model with a minimum of protocol mechanisms. UDP provides checksums for data integrity and port numbers for addressing different functions at the source and destination of the datagram. It has no handshaking dialogues like TCP, and thus exposes the user's program to any unreliability of the underlying network, meaning there is no guarantee of delivery, ordering, or duplicate protection. Voice over IP and streaming media sessions, they utilize UDP in addition to simple queries and responses such as DNS. Let's talk about TCP, so Transmission Control Protocol. This is one of the main protocols of the Internet Protocol Suite. It originated in the initial network implementation in which it complemented the Internet Protocol, therefore being commonly referred to as TCP/IP. TCP provides reliable, ordered, and error-checked delivery of bytes between applications running on hosts communicating via an IP network. TCP is a connection-oriented, and a connection between the client and a server is established before data can be sent, which requires every packet that has been sent to be checked for delivery. If packets that are transmitted to a receiving computer are not received, the receiving computer cannot assemble the message, and therefore the sending computer has to retransmit the missing packets. For example, if a computer sends a picture of a car, but for some reason the picture is missing parts of the image that display the tires, TCP will instruct the sending computer to retransmit the missing data for the proper assembly of the image. And let's talk about IP. So the Internet Protocol, this is the principal communications protocol in the Internet Protocol Suite for relaying datagrams across network boundaries. Its routing function enables internetworking and essentially establishes the internet. IP has the task of delivering packets from the source host to the destination host solely based on the IP addresses in the packet headers. For this purpose, IP defines packet structures that encapsulate the data to be delivered. It also defines addressing methods that are used to label the datagram with sources and destination information. All right, so now let's go ahead and get into some of this outstanding check on learning, shall we? So the first question is, which of the following answers refers to a protocol used by routers, hosts, and network devices to generate error messages associated with the delivery of IP packets? Is it CCMP, RSTP, ICMP, or SNMP? So which of the following answers refers to a protocol used by routers, hosts, and network devices to generate error messages associated with the delivery of IP packets? The correct answer is ICMP, or the Internet Control Message Protocol. Next question. Which of the answers listed below refers to a protocol used for managing audio-visual communication sessions? Is it SMB, H.323, SCP, or IGP? So which one of these refers to a protocol used for managing audio-visual communication sessions? The correct answer is H.323. And the final question is, POP3 is used for what? Is it name resolution, sending email messages, file exchange, or email retrieval? So what is POP3 used for? The correct answer is email retrieval. All right, so in summary, we have talked about the purpose and use of various networking ports and protocols. In this video, you're going to learn about the OSI model and the TCP/IP stack. So let's talk about the OSI model. This stands for the Open Systems Interconnection Model, and this is a conceptual model that characterizes and standardizes the communication functions of a telecommunication or computing system without regard to its underlying internal structure and technology. Its goal is the interoperability of diverse communication systems with standard communication protocols. The model partitions the flow of data in the communication system into 7 abstraction layers, from the physical implementation of transmitting bits across a communication medium to the highest level representation of data of a distributed application. Each intermediate layer serves a class of functionality to the layer above it and is served by the layer below it. And classes of functionality are realized in software by standardized communication protocols. Let's talk about layer 1, or the physical layer. So the physical layer is responsible for the transmission and reception of unstructured raw data between the device and the physical transmission medium. It converts the digital bits into electrical, radio, or optical signals. Layer specification define characteristics such as voltage layers, the timing of voltage changes, physical data rates, maximum transmission distances, modulation scheme, channel access method, and physical physical connectors. This includes the layout of pins, voltage, line impedance, cable specification, signal timing, and frequency for wireless devices. Bitrate control is done at the physical layer and may define the transmission mode as simplex, half duplex, and full duplex. The components of a physical layer can be described in terms of a network topology, and physical layer specifications are included in the specifications for the ubiquitous Bluetooth, Ethernet, and USB standards. Next, let's talk about layer 2, or the data link layer. So the data link layer provides node-to-node data transfer, which is a link between two directly connected nodes. It detects and possibly corrects errors that may occur in the physical layer. It defines the protocol to establish and terminate a connection between two physically connected devices. It also defines the protocol for flow control between them. And the IEEE 802 divides the data link into two sub-layers. You have the media access control layer. This is responsible for controlling how devices in the network gain access to a medium and permission to transmit data. And then you have the logical link layer. This is responsible for identifying and encapsulating network layer protocols and controls error checking and frame synchronization. Layer 3, or the network layer. So the network layer is primarily concerned with forwarding data based on logical addresses. The network layer provides the functionality and procedural means of transferring packets from one node to another connected in different networks. A network is a medium to which many nodes can be connected, on which every node has an address and which permits nodes connected to it to transfer messages to other nodes connected to it by merely providing the content of a message and the address of the destination node and letting the network find the way to deliver the message to the destination node, possibly routing it through intermediate nodes. If the message is too large to be transmitted from one node to another on the data link layer between these nodes, the network may implement message delivery by splitting messages into several fragments at one node, sending the fragments independently, and then reassembling the fragments at another node. It may, but does not need to, report delivery errors, and message delivery at the network layer is not necessarily guaranteed to be reliable. A network layer protocol may provide reliable message delivery, but it need not do so. And the network layer is responsible for a variety of tasks such as logical addressing, switching such as packet switching and circuit switching, message switching, route discovery and selection, connection services, flow control, which is also known as congestion control, and packet reordering. Let's talk about layer 4, or the transport layer. So the transport layer acts as the dividing line between the upper layers and the lower layers of the OSI model. The transport layer provides the functionality and procedural means of transferring variable length data sequences from a source to a destination host while maintaining the quality of service functions. The transport layer controls the reliability of a given link through flow control, segmentation, desegmentation, and error control. Some protocols are state and connection oriented. This means that the transport layer can keep track of the segments and retransmit those that fail delivery. The transport layer also provides the acknowledgement of the successful data transmission and sends the next data if no errors occurred. And the transport layer creates segments out of the messages received from the application layer. In segmentation, this is the process of dividing a long message into smaller messages. And two common transport layer protocols are, you have TCP, or Transmission Control Protocol. This is a connection-oriented transport protocol. And then you have UDP, or User Datagram Protocol. And this is a connection-less transport protocol. And then we have two common flow control protocols, which are windowing. So TCP communication uses windowing in that one or more segments are sent at one time, and a receiver can attest to the receipt of all the segments in a window with a single acknowledgement. And then you have buffering. So a device such as a router uses a chunk of memory, also known as a buffer or a queue, to store segments if bandwidth is not available to send the segments. A queue has a finite capacity, however, and can overflow or drop segments in case of sustained network congestion. Layer 5, or the session layer. So the session layer controls the dialogues or connections between computers. It establishes, manages, and terminates the connections between the local and remote application. It provides for full duplex, half duplex, or simplex operation, and establishes procedures for checkpointing, suspending, restarting, and terminating a session. In the OSI model, this layer is responsible for gracefully closing a session. This layer is also responsible for session checkpointing and recovery, which is not usually used in the Internet Protocol suite. The session layer is commonly implemented explicitly in application environments that use remote procedure calls. In the modern TCP/IP system, the session layer is non-existent and simply part of the TCP protocol. And the functions of the session layer include the following. You have setting up the session. So this checks the user's credentials, such as the username and password. It assigns numbers to a session's communication flow to uniquely find one another. It negotiates services needed during the session, and it negotiates which devices will begin to send data. You have maintaining a session. This refers to transfer of data, reestablishing a disconnected session, and acknowledgement of receipt of data. And you have tearing down of a session. This is where a session can be disconnected based on agreements of the devices in the session, or they can be torn down because one party just simply disconnects intentionally or unintentionally. Layer 6, the presentation layer. So the presentation layer handles formatting the data being exchanged and securing the data with encryption. The presentation layer establishes context between application layer entities, in which the application layer entities may use different syntax and semantics if the presentation service provides a mapping between them. If a mapping is available, presentation protocol data units are encapsulated into session protocol data units and passed down the protocol stack. This layer provides independence from data representation by translating between application and network formats. The presentation layer transforms data into the form that the application accepts. This layer formats data to be sent across a network, which is sometimes called the syntax layer, and can include compression functions. And functions of the presentation layer include data formatting. So some applications might format text using ASCII, while other applications might format text using EBCDIC, or extended binary coded decimal interchange code. The presentation layer handles formatting the text in a format that allows compatibility between the communicating devices. And then the other function is encryption. To add a layer of security for data transmission, encryption is used to scramble data that will make it impossible for a third party to decrypt the transmission. And then we have layer 7, or the application layer. So the application layer is the OSI layer that is closest to the end user, which means both the OSI application layer and the user interact directly with the software application. This layer interacts with software applications that implement a communicating component. Such application programs fall outside of the scope of the OSI model. Application layer functions typically include identifying communication partners, determining resource availability, and synchronizing communication. When identifying communication partners, the application layer determines the identity and availability of communication partners for an application with data to transmit. The most important distinction in the application layer is the distinction between the application entity and the application. So for example, a reservation website might have two application entities, one using HTTP to communicate with its users and one for a remote database protocol to record the reservations. Neither of these protocols have anything to do with the reservations. That logic is in the application itself. The application layer has no means to determine the availability of resources in the network. And some of the functions of the application layer are as follows. You have application services. So examples of these services may include file sharing and email. And then you have service advertisements. So some application services, they periodically send out advertisements such as network printers, making their availability known to other devices on the network. Now, here is an easy way to remember the OSI model layers. You could just simply remember this phrase called, please do not throw sausage pizza away. This begins at layer 1 and it goes all the way up through layer 7. So please do not throw sausage pizza away. That is the easiest way to remember the layers and the correct order of the OSI model. And let's talk about the TCP/IP stack. So the TCP/IP stack is a more relevant model for network designers and administrators to reference, which was developed by the United States Department of Defense. The TCP/IP stack has only 4 defined layers as opposed to 7 layers from the OSI model. The TCP/IP stack allows for network designers and administrators to more easily categorize a given networking technology into a specific layer. And the 4 layers of the TCP/IP stack are as follows. You have the network interface layer. This maps to layers 1 and 2 are the physical and data link of the OSI model. You have the internet layer. This maps to layer 3 or the networking layer of the OSI model, and it focuses on IP as the protocol to be routed through a network. You have transport. This maps to layer 4 or the transport layer of the OSI model, and the 2 primary protocols found here are TCP and UDP. And then you have application. This maps to layers 5 through 7, which are the session, presentation, and application layers of the OSI model. All right, now it's time for some of this wonderful check on learning. So the first question is, layer 6 of the OSI model is also referred to as what? Is it the application layer, the presentation layer, the session layer, or the transport layer? And the correct answer is, this is the presentation layer. Next question. Which of the terms listed below refers to the OSI network layer? Is it layer 2, 5, 3, or 4? So which one of these is the network layer for the OSI model? And the correct answer is layer 3 is the network layer for the OSI model. Next question. Which of the following protocols reside at the application layer in the OSI model? Would it be ATM, HTTP, FTP, IP, SSH, or TCP UDP? So which of these, and there's multiple answers here, which of these resides at the application layer in the OSI model? And the correct answer is HTTP, FTP, and SSH. These are all specific protocols that run on the application layer of the OSI model. So in summary, we've talked about the OSI model and the TCP/IP stack. In this video, you're going to learn about the properties of network traffic such as Ethernet, network switching, broadcast and collision domains, collision detection and avoidance, maximum transmission units, and broadcast versus multicast versus unicast. So let's talk about Ethernet. So Ethernet, this is a family of wired computer networking technologies commonly used in wired local area networks, metropolitan area networks, or wide area networks, enabling them to communicate with each other via a protocol, which is a set of rules or common network language. Ethernet describes how network devices can format and transmit data, so other devices on the same local or campus area network segment can recognize, receive, and process the information. An Ethernet cable, this is the physical encased wiring over which the data travels. Let's talk about network switching. So network switching, this is the process of channeling data received from any number of input ports to another designated port that will transmit the data to its desired destination. The device through which the input data passes is called a switch. Data entering a port is referred to as ingress, while data leaving the port is referred to as egress. The switch represents the medium through which the data is routed to its final destination. A network switch is networking hardware that connects devices on a computer network by using packet switching to receive and forward data to the destination device. A network switch is a multi-port network bridge that uses MAC addresses to forward data at the data link layer, which is layer 2 of the OSI model. And some switches can also forward data at the network layer or layer 3 of the OSI model by incorporating routing functionality. And these switches are commonly referred to as layer 3 switches or multi-layer switches. Packet switching. This is a method of grouping data that is transmitted over a digital network into packets. Packets are made of a header and a payload. Data in the header is used by networking hardware to direct the packet to its destination, where the payload is extracted and used by application software. Packet switching is the primary basis for data communications in computer networks around the world. Let's talk about broadcast domains. So a broadcast domain is used to describe a group of devices on a specific network segment that can reach each other with Ethernet broadcasts. Broadcasts sent by a device in one broadcast domain are not forwarded to devices in another broadcast domain. This improves the performance of the network because not all devices on a network will receive and process broadcasts. Routers separate a LAN into multiple broadcast domains where every port on a router is in a different broadcast domain. Switches by default flood Ethernet broadcast frames out all ports, just like bridges and hubs. All ports on these devices are in the same broadcast domain. Let's talk about a collision domain. So a collision domain is used to describe a part of the network where packet collisions can occur. Packet collisions occur when two devices on a shared network segment send packets simultaneously. The colliding packets must be discarded and sent again, which reduces network efficiency. Collisions occur often in a hub environment because all devices connected to the hub are in the same collision domain. Only one device may transmit at a time, and all the other devices connected to the hub must listen to the network in order to avoid collisions. Total network bandwidth is shared amongst all devices. So in contrast to hubs, every port on a bridge, switch, or router is in a separate collision domain. This eliminates the possibility of collisions and enables the devices to use the full duplex mode of communication, which effectively doubles the maximum data capacity. Let's talk about CSMA-CD, or Carrier Sense Multiple Access with Collision Detection. And this is a media access control method used notably in early Ethernet technologies for local area networking. It uses carrier sensing to defer transmissions until no other stations are transmitting. This is used in combination with collision detection, in which a transmitting station detects collisions by sensing transmissions from other stations while it is transmitting a frame. When this collision condition is detected, the station stops transmitting that frame, transmits a jam signal, and then waits for a random time interval before trying to resend the frame. And this is how CSMA-CD works. So the following procedure is used to initiate a transmission. The procedure is complete when the frame is transmitted successfully or a collision is detected during transmission. So step one, it'll say, is a frame ready for transmission? If not, it will wait for a frame. Then it will check to see if there is a free medium. If not, it will wait until one becomes ready. Then it will start transmitting and monitor traffic for collisions during the transmission. Then it will check to see if a collision did occur. If so, it will then go to the collision detected procedures, and then it'll reset retransmission counters and complete frame transmission. And here is a handy dandy little graphic explaining everything that I just said on the last slide. Next, let's talk about CSMA/CA. So this stands for Carrier Sense Multiple Access with Collision Avoidance. And CSMA/CA in computer networking is a network access method in which carrier sensing is used, but nodes attempt to avoid collisions by beginning transmission only after the channel is sensed to be idle. When they do transmit, nodes transmit their packet data in its entirety. This method was developed to decrease the chances of collisions when two or more stations start sending their signals over the data link layer. Carrier Sense Multiple Access requires that each station first check the state of the medium before sending. So collision avoidance, this is used to improve the performance of the CSMA method by attempting to divide the channel somewhat equally amongst all transmitting nodes within the collision domain. So step one is carrier sense. So prior to transmitting, a node first listens to the shared medium, such as listening for wireless signals in a wireless network to determine whether another node is transmitting or not. Then step two is collision avoidance. So if another node was heard, it'll wait for a period of time, which is usually random, for the node to stop transmitting before listening again for a free communications channel. Then it will initiate the request to send or clear to send, and this may optionally be used at this point to mediate access to the shared medium. This goes some way to alleviating problems of hidden nodes because, for instance, in a wireless network, the access point only issues a clear to send to one node at a time. However, wireless 802.11 implementations do not typically implement RTS-CTS for all transmissions. They may turn it off completely or at least not use it for small packets. And then it goes on to transmission. So if the medium was identified as being clear or the node received the CTS to explicitly indicate it can send, it sends the frame in its entirety. Unlike CSMA-CD, it is very challenging for a wireless node to listen at the same time as it transmits. And once again, here is a handy dandy graphic basically explaining everything that I just stated about CSMA-CA. All right, let's talk about MTU, or the maximum transmission unit. And this is a term used in networking and operating systems. It defines the largest size of the packet that can be transmitted as a single entity in a network connection. The size of the MTU dictates the amount of data that can be transmitted in bytes over a network. The larger MTU results in more data transmission during a single connection, therefore reducing the overhead. On the other hand, the smaller MTU can be transferred faster because of its size, which then reduces a delay in the network. Therefore, the size of the MTU should be adjusted to optimize both these requirements. And another way to visualize this is to imagine it being like a height limit for freeway or underpasses or tunnels. Cars and trucks that exceed the height limit cannot fit through, just as packets that exceed the MTU of a network cannot pass through that network. However, unlike cars and trucks, data packets that exceed MTU are broken up into smaller pieces so that they can fit through. This process is called fragmentation. Fragmented packets are reassembled once they reach their destination, and the MTU is measured in bytes. And remember, a byte is equal to 8 bits of information, meaning 8 ones and zeros, and 1500 bytes is the maximum MTU size. And here is a handy dandy little graphic showing you what the actual MTU represents, as you can see at the bottom down there. Next, let's talk about broadcast. So in computer networking, broadcasting refers to transmitting a packet that will be received by every device on the network. In practice, the scope of the broadcast is limited to a broadcast domain. Broadcasting is the most general communication method and is also the most intensive in the sense that many messages may be required and many network devices are involved. Broadcasting may be performed as all scatter, in which each sender performs its own scatter in which the messages are distinct from each receiver, or it may be performed as all broadcast in which they are all the same. Next, we have multicast, and multicast is a group communication where data transmission is addressed to a group of destination computers simultaneously. Multicast can be one-to-many or many-to-many distribution, and multicast enables distribution of content such as internet, TV, and other types of streaming media. And then we have unicast. So unicast is a one-to-one transmission from one point in the network to another point. That is one sender and one receiver, each identified by a network address. Unicast is in contrast with multicast and broadcast, which are one-to-many transmissions. Internet protocol unicast delivery methods such as transmission control protocol and user datagram protocol are typically used with this one. All right, that is the end of my class for this particular video. And in summary, we have talked about Ethernet, we talked about network switching, broadcast and collision domains, collision detection and avoidance, maximum transmission units, and broadcast versus multicast versus unicast. In this video, you're going to learn about network segmentation such as VLANs, trunking, tagging and untagging ports, port mirroring, switching loops, spanning tree protocol, power over Ethernet and power over Ethernet plus, DMZs, MAC address tables, and ARP tables. Let's talk about a VLAN, or a virtual local area network. So a VLAN is any broadcast domain that is partitioned and isolated in a computer network at the data link layer or the OSI layer 2. LAN is the abbreviation for local area network, and in this context, virtual refers to the physical object recreated and altered by additional logic. VLANs work by applying tags to network frames and handling these tags in network systems, creating the appearance and functionality of network traffic that is physically on a single network but acts as if it is split between separate networks. In this way, VLANs can keep network applications separate despite being connected to the same physical network and without requiring multiple sets of cabling and networking devices to be deployed. VLANs allow network admins to group hosts together even if the hosts are not directly connected to the same network switch. Because VLAN membership can be configured through software, this can greatly simplify network design and deployment. Without VLANs, grouping hosts according to their resource needs the labor of relocating nodes or rewiring data links. VLANs allow devices that must be kept separate to share the cabling of a physical network and yet be prevented from directly interacting with one another. This managed sharing yields gains in simplicity, security, traffic management, and economy. So for example, a VLAN can be used to separate traffic within a business based on individual users or groups of users or their roles, or based on traffic characteristics. Many internet hosting services use VLANs to separate customers' private zones from one another, allowing each customer's servers to be grouped in a single network segment, no matter where the individual server is located within the data center. And some precautions are needed to prevent traffic escaping from a given VLAN, which is also an exploit that is known as VLAN hopping. Next, let's talk about trunking 802.1q. So trunking is a technology for providing network access to multiple clients simultaneously by sharing a set of circuits, carriers, channels, or frequencies, instead of providing individual circuits or channels for each client. Trunking is a technique used in data communications transmission systems to provide many users with access to a network by sharing multiple lines or frequencies. As the name implies, the system is like a tree with one trunk and many branches. The data transmitted through trunking can be audio, video, controlling signals, or images. Trunking is the mechanism used to form an internetwork, or the internet, composed of LANs, VLANs, and WANs. The switches are interconnected to establish these networks using trunking, and trunking is not limited to any medium since its main purpose is to maximize the bandwidth available in any type of network. And 802.1q, this is a VLAN tagging protocol developed by the IEEE, or the Institute of Electrical and Electronics Engineering. Since it is an open standard, it can be used between switches from different vendors. So if you're trunking between a Cisco switch and a different brand of a switch, you can use 802.1q for the trunk to work. Let's talk about tagging ports. So VLAN tagging is performed by putting the VLAN ID into a header to identify which network it is present in. This helps in determining which interface or broadcast area the information packet needs to be sent in order to receive the right information. The switches need to be configured beforehand to work properly with the process of VLAN tagging. With this system, multiple broadcast systems can be segregated into individual domains. Bridging traffic can be forwarded with the use of this system, and clients and information can be organized, configured, and grouped logically. Overall, the functionality of the system will be optimized. An untagged port or access port on a switch connects to hosts. So the host is unaware of any VLAN configuration, which causes the host to send its traffic without any VLAN tag on the frames. When the frames reach the switch port, the switch will add a VLAN tag. The switch port is configured with the VLAN ID that it will put into that tag. Most switch ports will use this mode by default with VLAN ID 1. When a frame leaves an untagged port, the switch then strips the VLAN tag from the frame, and then the traffic is then forwarded as normal. Let's talk about port mirroring. So port mirroring is used on a network switch to send a copy of network packets seen on one switch port or an entire VLAN to a network monitoring connection or another switch port. This is commonly used for network applications that require monitoring of network traffic, such as intrusion detection systems, passive probe, or real user monitoring technology that is used to support application performance management. Network engineers or administrators use port mirroring to analyze analyze and debug data or diagnose errors on a network. It helps admins keep a close eye on network performance and alerts them when problems occur. It can be used to mirror either inbound or outbound traffic or both on single or multiple interfaces. Next, let's talk about a switching loop. So a switching loop or a bridge loop, this occurs in computer networks when there is more than one layer 2 path between two endpoints, such as multiple connections between two network switches or two ports on the same switch that are connected to each other. The loop creates broadcast storms as broadcasts and multicasts are forwarded by switches out every port. The switch or switches will repeatedly rebroadcast messages, flooding the network. Since the layer 2 header does not include a time to live field, if a frame is sent into a loop topology, it can loop forever. Let's talk about spanning tree protocol. So the spanning tree protocol is a network protocol that builds a loop-free logical topology for Ethernet networks. The basic function of STP is to prevent switching loops or bridge loops and the broadcast radiation that results from them. Spanning tree also allows a network design to include backup links, providing fault tolerance if an active link fails. As the name suggests, STP creates a spanning tree that characterizes the relationship of nodes within a network of connected layer 2 bridges and disables those links that are not part of the spanning tree, leaving a single active path between any two network nodes. All right, let's talk about power over Ethernet. So power over Ethernet is a networking feature that lets Ethernet cables supply power to network devices over the existing data connection. Power over Ethernet cable devices can be power sourcing equipment, powered devices, or a combination. The device that transmits power is a power sourced equipment, while the device that is powered is a powered device. Most PSCs are either network switched or PoE injectors intended for use with non-PoE switches. Common examples of PDs include voice over IP phones, wireless access points, and IP cameras. Power over Ethernet Plus, this is the update to Power over Ethernet. The major difference between PoE and PoE Plus is that PoE Plus power sourcing equipment can provide almost twice as much power over a single Ethernet cable. PoE Plus PSCs can supply power to both PoE and PoE Plus powered devices, but PoE PSEs can only supply power to PoE PDs. Also, Power over Ethernet Plus powered devices, they require more power than the Power over Ethernet PSEs can provide. All right, let's talk about the DMZ, or the demilitarized zone. So a demilitarized zone, which is also sometimes referred to as a perimeter network or screen subnet. This is a physical or logical subnetwork that contains and exposes an organization's external facing services to an untrusted, usually larger network such as the internet. The purpose of the DMZ is to add an additional layer of security to an organization's LAN to where an external node can access only what is exposed in the DMZ, while the rest of the organization's network is firewalled. The DMZ functions as a small, isolated network position between the internet and a private network, and if its design is effective, it allows the organization extra time to detect and address breaches before they would further penetrate into the internal networks. Next, we have a MAC address table. So a MAC address table, sometimes called a content addressable memory table. This is used on Ethernet switches to determine where to forward traffic on a LAN. MAC address tables map each port to a MAC address. When a switch receives a frame, it associates the MAC address of the sending devices with the interface on which it was received. The table that stores such associations is known as the MAC address table. This makes it efficient to forward traffic directly to a host. Without a MAC address table, traffic will be forwarded out each port like a hub. This table is stored in volatile memory, so associations will be erased after the switch is restarted. Let's talk about an ARP table, or an ARP table. So an address resolution protocol. This is a communication protocol used for discovering the link layer's address, such as MAC addresses associated with a given internet layer address, typically an IP version 4 address. This mapping is is a critical function in the Internet Protocol suite. An ARP table is simply a method for storing the information discovered through ARP. It is used to record the discovered MAC and IP address pairs of devices connected to a network. ARP allows for pairs of MAC and IP addresses to not have to be discovered or rediscovered for every data packet sent across the network. Once a MAC and IP is learned, it is kept in the ARP table for a specified period of time. All right, so that is my quick little class on network segmentation, where we talked about VLANs, trunking, tagging, and untagging ports, port mirroring, switching loops, spanning tree protocol, power over Ethernet and power over Ethernet plus, DMZs, MAC address tables, and ARP tables. In this video, you're going to learn about routing protocols such as distant vectors, link state, hybrid, static, dynamic, and default routing protocols. Let's talk about routing protocols. So a routing protocol specifies how routers communicate with each other to distribute information that enables them to select routes between nodes on a computer network. Routers perform the traffic directing functions on the internet. Data packets are forwarded through the networks of the internet from router to router until they reach their destination computer. Routing algorithms determine the specific choice of route. Each router has a prior knowledge only of networks attached to it directly. A routing protocol shares this information first amongst immediate neighbors and then throughout the entire network. This way, routers gain knowledge of the topology of the network, and the ability of routing protocols to dynamically adjust to changing conditions such as disabled connections and components and route data around obstructions is what gives the internet its fault tolerance and high availability. Let's talk about distance vector routing protocol. So a distance vector routing protocol in data networks determines the best route for data packets based on distance. Distance vector routing protocols measure the distance by the number of routes a packet has to pass, where one router counts as one hop. Some distance vector protocols also take into account network latency and other factors that influence traffic on a given route. To determine the best route across a network, routers on which a distance vector protocol is implemented, they exchange information with one another, usually routing tables plus hop counts for destination networks and possibly other traffic information. And distance vector routing protocols also require that a router inform its neighbors or other routers of the network topology changes periodically. A form of a distance vector routing protocol is called RIP, or Routing Information Protocol. So the Routing Information Protocol, this is one of the oldest distance vector routing protocols, which employs the hop count as a routing metric. RIP prevents routing loops by implementing a limit on the number of hops allowed in a path from source to destination. And the largest number of hops allowed for RIP is 15 hops, which limits the size of networks that RIP can support. The next type of distance vector routing protocol is EIGRP, or Enhanced Interior Gateway Routing Protocol. So EIGRP, this is an advanced distance vector routing protocol that is used on computer networks for automating routing decisions and configuration. The protocol was designed by Cisco Systems as a proprietary tool that was only available on Cisco routers. Functionality of EIGRP was converted to an open standard in 2013. EIGRP is used on a router to share routes with other routers with the same autonomous system. Unlike other well-known routing protocols such as RIP, EIGRP only sends incremental updates, reducing the workload on the router and the amount of data that needs to be transmitted. EIGRP ultimately eases the workload on a network admin so they don't have to configure changes to the routing table manually. Next, let's talk about link state routing protocols. So link state routing protocols are one of the two main classes of routing protocols used in packet switching networks for computer communications, the other being distance vector routing protocols. The link state protocol is performed by every switching node in the network. The basic concept of link state routing is that every node constructs a map of the connectivity to the network in the form of a graph showing which nodes are connected to which other nodes. Each node then independently calculates the next best logical path from it to every possible destination in the network. Each collection of best paths will then form each node's routing table. This contrasts with distance vector routing protocols, which work by having each node share its routing table with its neighbors. In a link state protocol, the only information passed between nodes is connectivity related, and link state algorithms are sometimes characterized informally as each router, quote unquote, telling the world about its neighbors. So a type of link state routing protocol is OSPF, or Open Shortest Path First. So Open Shortest Path First, this is a routing protocol for the Internet Protocol networks. It uses a link state routing algorithm and falls into the group of interior gateway protocols operating within a single autonomous system. And routing protocols like OSPF calculate the shortest route to a destination through the network based on an algorithm. All right, let's talk about hybrid routing protocols. So hybrid routing protocols, commonly referred to as balanced hybrid routing. This is a combination of distance vector routing, which works by sharing its knowledge of the entire network with its neighbors, and link state routing, which works by having the routers tell every router on the network about its closest neighbors. Hybrid routing protocol uses distant vectors for more accurate metrics to determine the best paths to destination networks and report routing information only when there is a change in the topology of the network. Hybrid routing allows for rapid convergence but requires less processing power and memory as compared to link state routing. Let's talk about a type of hybrid routing protocol known as BGP, or Border Gateway Protocol. So Border Gateway Protocol, this is a standardized exterior gateway protocol designed to exchange routing and reachability information amongst autonomous systems on the internet. BGP is classified as a path vector routing protocol as well, and it makes routing decisions based on paths, network policies, or rule sets configured by a network administrator. Another way to think about BGP is to think of it as the postal service of the internet. When someone drops a letter into a mailbox, the postal service processes that piece of mail and chooses a fast, efficient route to deliver that letter to its recipient. Similarly, when someone submits data across the internet, BGP is responsible for looking at all of the available paths that data could travel and picking the best route, which usually means hopping between autonomous systems. Let's talk about some routing types, and the first one is static routing. So static routing, this is a form of routing that occurs when a router uses a manually configured routing entry rather than information from dynamic routing traffic. In many cases, static routes are manually configured by a network administrator by adding entries into a routing table, though this may not always be the case. And some of the advantages of static routing are as follows. You have no routing overhead for router CPU, which means a cheaper router can be used to do the routing. It adds security because only administrators can allow routing to particular networks only, and there is no bandwidth usage between the routers. Some of the disadvantages are, for a larger network, it is a hectic task for an admin to manually add each router to the network in the routing table of each router, and the admin should have good knowledge of the topology. If a new admin comes along, then he or she has to manually add each route, so he or she should have a very good knowledge of the routes of the topology. Next, we have dynamic routing. And dynamic routing, this is a process where a router can forward data via a different route or given destination based on the current conditions of the communication circuits within a system. The term is most commonly associated with data networking to describe the capability of a network to route around damage, such as loss of a node or connection between nodes, so as long as other path choices are available. Dynamic routing allows many routes as possible to remain valid in response to change. And some of the advantages of dynamic routing are as follows. It's easy to configure, and it's more effective at selecting the best route to a destination remote network and also for discovering remote networks. And some of the disadvantages are it consumes more bandwidth for communicating with other neighbors and is less secure than static routing. And then we have default routing. So default routing, this is a configuration of the internet protocol that establishes a forwarding rule for packets where no specific address of a next hop host is available from the routing table or other routing mechanisms. The default route is generally the address of another router, which treats the packet the same way. So if a route matches, the packet is forwarded accordingly. Otherwise, the packet is forwarded to the default route of that router, and the device device to which the default route points is often called the default gateway, and it often carries out other functions such as packet filtering or proxy server operations. All right, so that is my quick little class. So let's go ahead and get into some of this outstanding check on learning, shall we? So the first question is, which of the following refers to a type of routing protocol that determines the best route for data packets based on the lowest number of hops? Is it hybrid, link state, distance vector, or dynamic? And the correct answer would be, this would be a distance vector. Let's go to the next question. A type of routing protocol that calculates the best path between source and destination nodes based on a map of network connectivity between nodes is called what? Is it dynamic, link state, static, or distance vector? And the correct answer would be, this is a link state routing protocol. And the final question is, a manually configured routing table entry is referred to as what? Is it a static route, dynamic route, hybrid route, or a default route? So a manually configured routing table, this is called what? And the correct answer is, this would be a static route. So in summary, we have talked about various routing protocols such as distant vector, link state, hybrid, static, dynamic, and default routing protocols. In this video, you're going to learn about IP version 6 addressing and network performance concepts such as NAT, PAT, port forwarding, access control lists, distributed switching, packet switch versus circuit switch networks, and software-defined networking. First things first, let's talk about IP version 6. So Internet Protocol version 6, this is the most recent version of the Internet Protocol, or the communications protocol that provides an identification and location system for computers on networks, and it routes traffic across the internet. IP version 6 uses 128-bit source and destination IP addresses as compared to 32-bit for IP version 4, and this theoretically enables you to have up to 340 undecillion addresses, or 3.4 times 10 to the 38th power. IP version 6 also features built-in security and provides better support for quality of service routing, which is important to achieve high-quality streaming audio and video traffic. And Windows, Mac, and Linux, they all support IP version 6. So IP version 6 addresses, like I stated earlier, they are 128-bit addresses that are each divided into 8 16-bit blocks. The blocks are converted into hexadecimal, and each block is separated from the following block by a colon, and leading zeros, they are typically suppressed, but each block must contain at least one digit. And let's talk about the rules for abbreviating an IP version 6 address. So the first thing is, leading zeros in a field can be omitted, and then contiguous fields containing all zeros can be represented with a double colon, and this can only be done once for a single IP version 6 address. So here's an example. You have the IP version 6 address of ABCD01234040, so on and so forth. Its abbreviated version will look like the following: ABCD:123:4040 double colon A:B. So those colons basically represents all of the zeros being taken out, and then if the certain block leads with the number 0, you can leave off the 0, as in the case of the 123. Let's talk about IP version 6 address types. So IP version 6, it supports 3 types of addresses. You have unicast, multicast, and anycast. And unicast, this is any address that identifies a unique node on a network. Unicast addressing is available in IP version 4 and IP version 6, and typically refers to a single sender or single receiver, although it can be used for both sending and receiving. Unicast is the most common form of IP addressing, and IP version 6 globally routable unicast addresses, they start with the first 4 hexadecimal characters in the range of 2,000 to 3,999. Next, we have multicast, and this is a specific type of IP address labeling a network location that is used to multicast data packets within a network. It stands in contrast to other IP addresses that only allow for unicast models. Both IP version 4 and IP version 6, they support multicasting, and multicast enables the distribution of content such as the internet, TV, and other types of streaming media. And multicast addresses, they begin with FF as the first two hexadecimal characters. And then we have Anycast, and this is a network addressing and routing methodology in which a single destination address has multiple routing paths to two or more endpoint destinations. This is also known as one-to-one to many association, and Anycast can be used for distributed services such as DNS or other situations in which automatic failover is desirable. And IP version 6 uses Anycast addresses as destination addresses that are assigned only to routers, and Anycast addresses, they are assigned from the unicast address space. And here are some other unique aspects about IP version 6 addressing. So in IP version 6 link local address, this is also used on each IP version 6 interface, and the link local address that begins with FE80. And then IP version 6 can also use auto configuration to discover the current network and select a host ID that is unique to that network. Automatic generation of a unique host ID. This is made possible through a process known as EUI64, which uses the 48-bit MAC address on the device to aid in the generation of the unique 64-bit host ID. And then IP version 6 can also use a special version of DHCP for IP version 6, which is referred to as DHCP version 6. And then the protocol that is used to discover the network address and learn the layer 2 address of neighbors on the same network is called Neighbor Discovery Protocol. Next is IP version 6 tunneling. So IP version 6 tunneling, this is a mechanism for encapsulating IP version 4 and IP version 6 packets within a site-to-site IP version 6 VPN. It is used to form a virtual point-to-point link between IP version 6 nodes, and IP version 6 tunnels are stateless and they have no knowledge of the configuration or existence of the remote tunnel endpoint. Once an IP version 6 tunnel is configured, packets are encapsulated and forwarded regardless of whether the decapsulating device is present or not. And IP version 6 tunneling allows hosts in one private IP network to communicate with hosts in another private IP network by providing a tunnel between two routers across the internet. And the IP version 6 tunnel connection endpoints are terminated via a virtual tunnel interface, or a VTI, that is configured in each device. Next, we have IP version 6 dual stack. So dual stack means that devices are able to run IP version 4 and IP version 6 in parallel. It allows hosts to simultaneously reach IP version 4 and IP version 6 content. So it offers a very flexible coexistence strategy. With dual stack, every networking device, server, switch, router, and firewall in an ISP's network will be configured with both IP version 4 and IP version 6 connectivity capabilities. And some of the benefits of the IP version 6 dual stack are as follows. You have native dual stack. It does not require any tunneling mechanisms on internal networks. Both IP version 4 and IP version 6, they run independent of each other. And then dual stack supports gradual migration of endpoints, networks, and applications. Next, let's talk about router advertisements. So routers, they advertise their presence together with various link and internet parameters, either periodically or in response to a router solicitation message. And the host will then use the information to learn the prefixes and parameters for the local network. Next, we have neighbor discovery. So neighbor discovery, this is a protocol that allows different nodes on the same link to advertise their existence to their neighbors and to learn about the existence of their neighbors. And routers and hosts, or nodes, they use neighbor discovery messages to determine the link layer addresses of neighbors that reside on attached links and to overwrite invalid cache entries. Hosts also use neighbor discovery to find neighboring routers that can forward packets on their behalf. In addition, nodes use neighbor discovery to actively track the ability to reach neighbors. And when a router or the path to a router fails, nodes actively search for alternatives to reach that destination. All right, next we're going to talk about performance concepts. And the first concept we're going to talk about is called traffic shaping. So traffic shaping, this is a bandwidth management technique used on computer networks which delays some or all datagrams to bring them into compliance with a desired traffic profile. Traffic shaping is used to optimize or guarantee performance, improve latency, or increase usable bandwidth for some kinds of packets by delaying other kinds. It is often confused with traffic policing, which is the the distinct but related practice of packet dropping and packet marking. The most common type of traffic shaping is called application-based traffic shaping. In application-based traffic shaping, fingerprinting tools are first used to identify the application associated with a data packet. And based on this, specific traffic shaping policies are then applied. So for example, you might want to use application-based traffic shaping to throttle peer-to-peer file sharing while giving maximum bandwidth to a business critical application such as voice over IP, which is especially sensitive to latency. The next performance concept is called quality of service. So quality of service, this is the description or measurement of the overall performance of a service, such as telephony or computer network or cloud computing service, particularly the performance seen by the users on the network. So quality of service is very important when it comes to streaming media, gaming, or voice over IP services. Quality of service prioritizes real-time and streaming traffic, and depending on the router, QoS can simply be turned on and off, or it can be tweaked by specifying services to prioritize, whether to optimize for gaming and uplink downlink speeds to use. QoS can also be configured by an ISP, and if an ISP is performing QoS optimization, the changes you make on your router, well, they simply will not improve your traffic. The next performance concept is called diff-serve or differentiated services. So differentiated services, this is a computer networking architecture that specifies a simple and scalable mechanism for classifying and managing network traffic and providing quality of service on modern IP networks. Differentiated services can be used to provide low latency to critical network traffic such as voice or streaming media, while providing simple best effort service to non-critical services such as web traffic or file transfers. And the next performance concept that we're going to learn about is called class of service. So when a network experiences congestion and delay, some packets must be prioritized to avoid random loss of data. Class of service accomplishes this prioritization by dividing similar types of traffic such as email, streaming video, voice, large document file transfers into classes. Different levels of priority are then applied for throughput and packet loss to each group to control traffic behavior. All right, now let's talk about network address translation. So network address translation, this is a method of remapping an IP address space into another by modifying network address information in the IP header of packets while they are in transit across a traffic routing device. So in layman's terms, NAT is the process where a network device, usually a firewall, assigns a public address to a computer or group of computers inside a private network. The main use of NAT is to limit or hide an entire IP address space on a LAN for both economic and security purposes. This functionality is typically built into a router, so when NAT is implemented, before an IP address on the LAN can communicate with the internet, the IP address has to be converted to the public IP address of the router. This allows for the router to appear as if it is the only device making a connection to remote computers on the internet, which provides safety for computers on the LAN. It also allows a single IP address to do the work for many IP addresses in the LAN, and NAT is performed automatically on SOHO routers when connected to an IP version 4 network, and NAT is not necessary on an IP version 6 network because IP version 6 is much more secure and has no shortage of IP addresses. Next, we have port address translation, or PAT. So port address translation, this is a function that allows multiple users within a private network to make use of a minimal number of IP addresses. Its basic function is to share single IP public addresses between multiple clients who need to use the internet publicly. It is an extension of the network address translation, and an example of PAT is a home network that is connected to the internet. Within this setup, the system's router is assigned a discrete IP address, and then multiple users can access the internet over the router and are each assigned a port number as they do so. Next concept we're going to talk about is port forwarding. So in computer networking, port forwarding, which is also known as DNAT or Destination Network Address Translation, this is an application of NAT that redirects redirects a communication request from one address and port number combination to another while the packets are traversing a network gateway, such as a router or a firewall. So in layman's terms, port forwarding allows remote computers to connect to a specific computer or service within a private local area network. An example could be an FTP server residing inside of a LAN that has the IP address of 192.168.1.240 with port 21 open to allow for external computers to connect to engage in file transactions. In order for the external computers to connect, these devices would need to know the IP address of your router. So let's just imagine that your IP address is 68.54.121.93, and then they would also need to know the appropriate port number or port 21. And once the external computer is granted access to the LAN, the external device's packets will then be forwarded to the FTP server at 192.168.1.240 port 21. Next, we're going to talk about an ACL or an access control list. So an access control list, this is a set of rules that is usually used to filter network traffic. ACLs can be configured on network devices with packet filtering capabilities, such as routers and firewalls. And ACLs, they contain a list of conditions that categorize packets and help you to determine when to allow or deny network traffic. And they are applied on the interface basis to packets leaving or entering an interface. Next is distributed switching. So distributed switching, this is an architecture in which multiple processor controlled switching units are distributed. There is often a hierarchy of switching elements with a centralized host switch and with remote switches located close to a concentration of users. Distributed switching is often used in telephone networks where it is often referred to as host remote switching. So in rural areas, population centers tend to be small for economical development of full-feature dedicated telephone exchanges, and distances between these centers make transmission costs relatively expensive. So normal telephone traffic patterns show that most calling is done between people in these population centers, and the use of distributed switching would allow for the majority of these calls that are local to that population center to be switched there without needing to be transported to and from the host switch. The host switch provides connectivity between the remote switches and to the larger network, and the host may also directly handle some rare and complex call types such as conference calling that the remote itself is not equipped to handle. Next, we have a packet switch network. So packet switching, this is a method of grouping data that is transmitted over a digital network into packets, and packets are made of a header and a payload, and data in the header is used by networking hardware to direct the packet to its destination, where the payload is extracted and used by application software. And packet switching, this is the primary basis for data communications in computer networks around the world. Then we have circuit switch networking. So circuit switching, this is a method of implementing a telecommunications network in which two network nodes establish a dedicated communications channel, also known as a circuit, through the network before the nodes may communicate. The circuit guarantees the full bandwidth of the channel and remains connected for the duration of the communication session. The circuit functions as if the nodes were physically connected as with an electrical circuit. Circuit switching originated in analog telephone networks where the network created a dedicated circuit between two telephones for the duration of a telephone call. It contrasts with packet switching used in modern digital networks in which the trunk lines between switching centers carry data between many different nodes in the form of data packets without dedicated circuits. And then we have software-defined networking. So software-defined networking technology, this is an approach to network management that enables dynamic, programmatically efficient network configuration in order to improve network performance and monitoring, thereby making it more like cloud computing than traditional network management. And SDN is meant to address the fact that the static architecture of traditional networks is decentralized and complex, while current networks require more flexibility and easy troubleshooting. And SDN attempts to centralize network intelligence in one network component by disassociating the forwarding process of network packets from the routing process. The routing process consists of one or more controllers, which are considered the brain of the SDN network, where the whole intelligence is incorporated. However, the intelligent centralization has its own drawbacks when it comes to security, scalability, and elasticity, and this is the main issue associated with software-defined networks. All right, so that is my quick little class. So let's go ahead and do some of this outstanding check on learning, shall we? So the first question is, which of the following IP version 6 protocols is used by network nodes for locating routers? Is it NDP, NTP, NDR, or NCP? So which of the following IP version 6 protocols is used by network nodes for locating routers? And the correct answer is, this would be the Neighbor Discovery Protocol. Next question. A rule-based access control mechanism implemented on routers, switches, and firewalls. This is known as what? Is this an ACL, a CSR, a DLP, or an AUP? So a rule-based access control mechanism implemented on these networking devices is known as what? The correct answer is, this would be an access control list, or an ACL. All right, so in summary, we have talked about IP version 6 addressing and networking performance concepts such as NAT, PAT, port forwarding, ACLs, distributed switching, packet switching versus circuit switching, and software-defined networking, and a whole bunch of other stuff in between. In this video, you're going to learn about IP addressing concepts such as private versus public IP addressing, reserve IP addresses, loopback IP addresses, default gateways, virtual IP addresses, DHCP and DHCP version 6, static IP addresses, a PIPA, and IP reservations. All right, let's talk about a public IP address. So a public IP address, or an external IP address, this is assigned to every device that connects to the internet, and each IP address is unique. This addressing scheme makes it possible for the devices to find each other online and exchange information, and the user has no control over the public IP address that is assigned to the device. The public IP address is assigned to the device by the ISP as soon as the device is connected to the internet. Also, a public IP address can be static, dynamic, or even shared. Let's talk about private IP addresses. So in IP networking, a private network is a computer network that uses private IP address space. These addresses are commonly used for local area networks in residential, office, and enterprise environments to allow for devices to communicate with each other on the same network. Private IP addresses are not allocated to any specific organization, and anyone may use these addresses without approval from regional or local internet registries. An IP address is considered private if the IP number falls within one of the IP address ranges reserved for private networks, such as a local area network. The IANA, or the Internet Assigned Numbers Authority, they have reserved the following 3 blocks of IP address space for private networks or local networks. In order to communicate with the outside world, these IP addresses must be translated to a public address using NAT, or Network Address Translation. And so you have 10.0.0.0 through 10.255.255.255. That will make up a grand total of 16,777,216 IP addresses. Then you got 172.16.0.0 through 172.31.255.255. You'll get 1,048,576 addresses within that space. And then you got 192.168.0.0 through 192.168.255.255. You'll get 65,536 addresses within that space. Let's talk about reserve IP addresses. So in the Internet Addressing Architecture, the Internet Engineering Task Force, and the IANA, they have reserved various IP addresses for special purposes, and the types of reserved IP addresses are as follows. You've got private IPs, which we just talked about. You have loopback addresses, and then you have addresses in the range from 0.0.0.0 through 0.255.255.255. And these IP addresses do not do anything, and they will not function properly no matter where on the network they are configured. Let's talk about a loopback IP address. So a loopback IP address, this is a special IP address reserved for use in testing network cards. This IP address corresponds to the software loopback interface on the network card, which does not have hardware associated with it and does not require a physical connection to a network. The loopback address allows for for a reliable method of testing the functionality of an Ethernet card, its drivers, and software without a physical network. It also allows IT professionals to test IP software without worrying about broken or corrupted drivers or hardware. And the loopback IP address for IP version 4 is 127.0.0.1, and then the loopback address for IP version 6 is 7 zeros and a 1, or you could just shorten it out to be : 1. Let's talk about the default gateway. So a default gateway, this is a network node that serves as the forwarding host or the router to other networks, often involving not only a change of addressing, but also a different networking technology. More narrowly defined, a router merely forwards packets between networks with different network prefixes. The networking software stack of each computer contains a routing table that specifies which interface is used for transmission and which router on the network is responsible for forwarding a specific set of addresses. If none of these forwarding rules is appropriate for a given destination address, the default gateway is chosen as the router or last resort. In a small office, home office environment, the default gateway is a device such as a DSL router or a cable router that connects the local network to the internet. It serves as the default gateway for all network devices. Enterprise networks, they may require internal network segments where a device wishing to communicate with the host on the public internet would have to forward the packets to the default gateway for its network segment, which would have a default route configured to a device on an adjacent network, which would be one hop closer to the public internet. Let's talk about virtual IP addresses. So a virtual IP address is an IP address assigned to multiple domain names or servers that share an IP address based on a single network interface card or a NIC card. Virtual IPs are allocated to virtual private servers, websites, or other applications residing on a single server. The host server for these applications has a network IP address assigned by a network administrator, whereas the different server applications have virtual IPs. So in layman's terms, a server IP address depends on the media access control or the MAC address of the attached NIC, and only one logical IP address may be assigned per card. However, virtual IP addressing enables hosting for several different applications and virtual appliances on a server with only one logical IP address. The virtual IP is used for communication by all hosted applications, even though data packets are routed through actual network interfaces. And virtual IPs are primarily implemented for one of the following reasons. It's either to consolidate resources through the allocation of one network interface per hosted application, or to improve redundancy by providing alternative failover options on one machine. Now we're going to talk about address assignments, and the first one we're going to talk about is DHCP. So DHCP stands for a Dynamic Host Configuration Protocol, and this is a network management protocol used on IP networks whereby a DHCP server dynamically assigns an IP address and other network configuration parameters to each device such as PCs, printers, servers, routers, etc. on a network so they can communicate with other IP networks. A DHCP server enables computers to request IP addresses and networking parameters automatically from the ISP, reducing the need for a network admin or a user to manually assign IP addresses to all network devices. In the absence of a DHCP server, a computer or other device on the network needs to be manually assigned an IP address or to assign itself an APIPA address, the latter of which will not enable it to communicate outside of its local network. If you get your address from a DHCP server, you are getting your address assigned dynamically, and it could change periodically. Some devices on the network require static addresses that do not change, such as printers and servers, which have been assigned manually by a network administrator. This enables these devices to be more reliable and easily accessible over time. And DHCP uses ports 67 and 68, where UDP port 67 is the destination port of the server, and UDP port 68 is used by the client. Then we have DHCP version 6. So DHCP version 6 is a network protocol for configuring IP version 6 hosts with IP addresses, IP prefixes, and other communication data required to operate in an IP version 6 network. Basically, it is the IP version 6 equivalent of the DHCP for IP version 4. In DHCP version 6, it uses UDP port 546 for its clients and port number 547 for the servers. Let's talk about static IP addresses. so a static IP address is simply an IP address that does not change. Once your device is assigned a static IP address, that number typically stays the same until the device is decommissioned or your network architecture changes. Static IP addresses are generally used by servers or other important equipment that devices need to have constant access to. Next, let's talk about a PIPA. So if a router does not have enough IP addresses for the device that need to connect to it, a PIPA IP addresses will be assigned, and they range from 169.254.0.0 through 169.254.255.255, and they will be assigned to devices arriving after the pool of addresses are used up. A PIPA, it stands for Automatic Private IP Addressing, and this is a feature in Windows-based operating systems that enables computers to automatically self-configure an IP address and subnet mask when their DHCP server is not reachable. The PIPA service checks regularly for the presence of the DHCP server every 3 minutes, and if it detects a DHCP server on the network, the DHCP server will replace the PIPA networking address with dynamically assigned addresses. IP reservation. So DHCP IP reservation, this allows for the same IP address to be assigned to a specific device whenever that device connects to the network. So think of it as a reserved parking spot at an apartment complex. Most devices use DHCP, which assigns dynamic IP addresses as a default, but sometimes you may want or need devices to always have the same IP address. So for example, a wireless printer is a device that should have the same IP address at all times. When you print something, your computer and printer locate each other using IP addresses. If your printer's IP address keeps changing, your computer may not always be able to find the printer. Giving your printer a static IP address will ensure that your computer always knows the address of your printer, as it won't change if it's rebooted or if a DHCP IP lease expires. All right, so that is the lesson. Now let's go ahead and do some of this outstanding check on learning, shall we? So the first question is, which of the answers listed refer to an IP version 4 loopback address? Is it : 169.254.0.0, 0 : with 6 other zeros and a 1 at the end, or is it 127.0.0.1? So which one of these is the loopback for an IP version 4 address? And the correct answer would be 127.0.0.1. That is the IP version 4 loopback address. Next question. Which of the following refers to a permanent assignment of an IP address? Is it static IP, private IP, dynamic IP, or public IP? So which of the following is a permanent assignment of an IP address? And the correct answer is, it would be a static IP address. Next question. Which of the following converts a private IP address into a public IP address to allow for devices in a LAN to communicate with the internet? Would it be QoS, DHCP, NAT, or DNS? So which converts a private to a public IP address to allow for devices within the LAN to communicate with the internet? And the correct answer is, this would be NAT, or Network Address Translation. So in summary, we have talked about IP addressing concepts such as private versus public IP addressing, reserved IP addresses, loopback addresses, default gateways, virtual IP addresses, DHCP and DHCP version 6, static IP addresses, a PIPA, and IP reservations. In this video, I'm going to show you guys how to convert decimal numbers into binary, binary into hexadecimal, hex into binary, and binary back into decimal, so that you can look like a superstar out on these streets with these conversions. So let's get into it. First thing we need to understand, ladies and gentlemen, is what is decimal, what is hexadecimal, and what is binary. So all of you out there, you all know what decimal is. This is the base 10 numbering system that you guys learn how to count your fingers and toes when you were in preschool. And that is numbers 0 through 9, 0 through 9 or 1 through 10, but we refer to it as 0 through 9 over here in the IT world. Next, we have hexadecimal. hexadecimal. Hexadecimal represents base 16 values, base 16 numbers, right? And how this works is you have the same numbers 0 through 9 over here, but then when you get to the number 10, instead of it becoming the number 10, it is represented by the letter A all the way through the letter F, which stands for 15. So A through F, A, B, C, D, E, F, all of those letters represents numbers 10, 11, 12, 13, 14, and 15, okay? And then we have binary. This is powers of 2 or base 2 mathematics. And this represents zeros and ones, which stand for off and on. So in binary, what happens is we're going to take what is called an IP version 4 address. You guys have seen these before. It'll be some number here, dot some number here, dot some number there, dot some number there. That represents an IP address. And if you guys aren't familiar with IP addresses, go check out my IT Fundamentals course where I explain all of this to you. But a lot of you guys are familiar with IP addresses. You're just familiar with the names that are associated with them. Like if you type in youtube.com, or youtube.com is associated with an actual IP address. So think of the IP address as the house number to the house that you currently live in. Okay. Now, how binary relates to the IP version 4 that we're looking at here, we're only going to be focusing on what is called the 4th octet. This is octet 1, octet 2, octet 3, and octet 4. We're going to be focusing on the 4th octet so that we can try to figure out which bits to turn on and off, you know, zeros and ones. And so first things first, we have to lay out the binary numbering system. So it goes like this. It goes from number 1, 2, 4, 8, 16, 32, 64, 128. This red decimal point represents the break in the 4th octet. Then we're going on to the 3rd octet. But as you can see, all of these values double themselves by a power of 2, and it just keeps going on and on and on. So we got to get this down packed first, because this is what is going to help us go through our conversion process, right? And how the actual conversion process works is if you want to go from decimal to hexadecimal, you're going to have to use binary as the middleman. If you want to go from hex back to decimal, you're going to have to use binary as the middleman. So I'm going to show you guys how to do this. It's really simple. Don't sweat it. You'll be doing this like a boss by the time I'm done with this video. All right, so let's do our first example of how to convert decimal to binary. So in this example, we're going to convert the decimal number 175 into its binary equivalent. So the first thing that you're going to want to do is you're going to want to lay out all of your powers of 2s like I just showed you, from the 4th octet, numbers 1, 2, 4, 8, 16, 32, 64, and 128. And now we're going to turn on the values that actually add up to the number 175. Because if you recall, I just stated in binary, we work off of ones and zeros. Ones represents a value or a bit is turned on, and 0 represents a value or a bit is turned off. So in order for us to get 175, we have to turn on the number 128, the number 32, the number 8, 4, 2, and 1. You add all those numbers up together, you get 175. Real simple stuff, right? I know. All right, let's take this problem one step further. So we're going to go ahead and convert the decimal number 175 into its hexadecimal equivalent. Now, if you recall, I stated that in order to go from decimal to hexadecimal, or from hex back to decimal, you have to go through binary as the middle guy. All right, so now let me go ahead and explain what all this madness on your screen means, okay? So we have the decimal number 175, and we've already figured out how to solve for its binary equivalent, and that will come out to be 1010111. Now, remember, I stated that this was basically the 4th octet, right? The last octet of an IP address. I have this blue line right here going down the middle because when we go through the process of converting it into hexadecimal, we're only going to be focusing on what is called a nibble, an N-I-B-B-L-E. This is basically half an octet that we're going to use for our conversions, okay? So we got our binary 1010111. We're going to move it down here. Now, we're going to break this down into 2 groups of 4s, or 2 groups of nibbles, right? We're just going to draw a line straight down the middle, just like I did. Being that we're only operating off of half of an octet, we're only going to basically apply half of the powers of 2 conversion. So we have 1111. So basically the values 1, 2, 4, and 8 have all been turned on. And then we're going to apply the same 1, 2, 4, and 8 over here. So as you can see, the value 8 and the value 2 have been turned on. And now we're going to go ahead and just start adding numbers up. 8 plus 2 2 is what? 10. 8 plus 4 plus 2 plus 1 equals what? 15. So now we have 10 and we have 15. That is what these nibbles break down into. So now we have to go ahead and figure out what do these values mean as it relates to hexadecimal. So if you look over here, remember I told you hexadecimal numbers, they represent numbers 0 through 9 and letters A through F, where A through F represent numbers 10 through 15. So now that we have the number 10 over here, well, A equals 10. F equals 15. So the decimal number 175 equals the hexadecimal value AF. Now, if you want to go ahead and check your work real quick to verify that you know what you're doing, you can just go to Google and type in decimal to hexadecimal converter, and you just type in the number 175 and it will show you the conversions right here. Here's your hexadecimal value and here is your binary value that I was showing you earlier on this screen. All right, so now let me give you an example of how to go from hexadecimal all the way back to decimal. So in this example, we have the hexadecimal value of B2. We're trying to figure out what its decimal equivalent is. So what we're going to do with the B2, we're going to go ahead and convert it to binary, because remember, to go from hex to decimal, you got to go through binary. From decimal to hex, you got to go through binary. So we're going to go ahead and apply our middleman. So what we're going to do, we're going to take our B2 and we're going to divide it into its own little sections here of B and 2. And then we're going to come back over here and figure out what its equivalent is in its nibble notation. So remember, we're working with the number 2. So we got to come down here and do our 1, 2, 4s, and 8s that represent our nibbles so that we can figure out which value is actually turned on. So out of 8, 4, 2, and 1, the only value that is turned on is the value number 2. So that'll be 0, 0, 1, 0. Then we come over here to the letter B. If you look back up here, remember in hexadecimal notation is expressed in numbers 0 through 9 and A through F, where the letter A equals 10 and the letter F equals 15. So B would be the number 11. So 11 equals B. We go here and look at our nibble, 1, 2, 4, and 8. We add the values that are turned on. So it'll be 8, 2, and 1. 8 plus 2 plus 1 equals 11. And then we just put them all together. And this is what our binary equivalent for B2 is going to look like. It's going to be 1, 0, 1, 1, 0, 0, 1, 0. Now we're going to take this and we're going to figure out what our decimal equivalent is. So now we're going to come back to the fourth octet, the entire thing. 1, 2, 4, 8, 16, 32, 64, 128. We're going to take our binary equivalent and figure out which of these values are turned on. As you can see, values 128, 32, 64, and 2 are turned on. We're going to come up here and just add those numbers together. 128 plus 32 plus 16 plus 2, and that will get you 178. So the decimal equivalent of the hexadecimal value B2 is the number 178. And like always, if you're unsure, you can just run over to Google and do a check to verify that you added your numbers up correctly. So as you can see, I put B2 up into the converter. We got our decimal equivalent of 178, and then we have our binary equivalent of 10110010. And for my last trick, ladies and gentlemen, I'm going to show you how to convert a hexadecimal number that has 3 values back into its decimal equivalent. So if we look at our screen here, we have the hexadecimal values A, B, and C. Okay, so first thing we got to do, we got to convert A, B, and C back into its binary equivalent, because binary is the middleman. Also remember, hexadecimal values are the numbers 0 through 9 and the letters A through F, where A equals 10 and F equals 15. So we go through, we take ABC and we break it down into its individual groups. And then we figure out, what do these values represent? Well, A equals 10, B equals 11, and 12 equals C. We go ahead and apply our little nibbles that I was talking about here with 8421, 8421, 8421. We figure out which values are turned on that add up to this number right here. So 8 plus 4 equals 12, 8 plus 2 plus 1 equals 11, 8 plus 2 equals 10. So this is our binary equivalent of ABC, 101010111100. Now we're going to move on down to converting this into its decimal equivalent. So now we're going to apply the entire octet again. So remember, 1, 2, 4, 8, 16, 32, 64, 128. Now if you look right here, I have a little red dot right here that indicates the separation between the fourth octet and the third octet. So this value ABC is going to drag us out into the third octet. So what we're going to do, we're still going to apply the powers of 2. So 128 plus 128 is going to get us 256. 256 plus 256 is going to get us 512, then 1024, 2048, and so on and so forth. So now we're going to take our binary value and just figure out which of these numbers are turned on. As you can see, 2048's on, 512, 128, 32, 16, 8, and 4. Come up here, add up all these numbers together. 2048 plus 512 plus 128 plus 32 plus 16 plus 8 plus 4. That's going to get you the decimal equivalent of 2,748. So the hexadecimal value ABC equals 2748. And like always, you can just run over to Google and check your work if you want. So as you can see, hexadecimal number ABC, decimal value 2748, binary value down below. All right, ladies and gentlemen, that is my quick little class on how to perform decimal to binary to hexadecimal conversions and hex back to binary back to decimal conversions. In this video, you're going to learn about classful subnetting concepts such as classful IP addressing, subnetting, subnet mask, and broadcast IP addresses. All right, let's talk about classful IP addressing. So classful IP addressing, this is a method that divides the IP address space for IP version 4 into 5 address classes based on the leading 4 address bits. Class A, B, and C provide unicast addresses for networks of 3 different network sizes. Class D is for multicast networking, and Class E address range that is used for future or experimental purposes. And as a refresher as to what an IP address is, an IP address is divided into 2 fields. You have the network prefix or the network ID, and you have a host ID. And what separates the network ID from the host ID depends on whether the address is class A, B, or C. So let's talk about some of the classes of IP addresses. So you have class A, and that ranges from 1 to 126. So if you see an IP address in the first octet that starts with the number 1 all the way through the number 126, you are dealing with a class A IP address, and this can support 16 million hosts on 127 different networks. Then you have class B that ranges from 128 to 191. So once again, if you see the first octet starting with the number 128 all the way through 191, you're dealing with a class B address, and that can support 65,000 hosts on 16,000 networks. And then you have class C that goes from 192 to 223, and that supports 254 hosts on 2 million networks. And then you got class D, that's 224 to 239, and that's reserved for multicast groups. And then you got class E, that's 240 to 255, and that's reserved for future use, research, or development purposes. But what you really need to be concerned about is just class A, B, and C. Those are the IP class ranges that you need to be most concerned about. Next, let's talk about subnetting. So subnetting, this is the strategy used to partition a single physical network into more than one smaller logical subnetwork or subnet. Subnetting allows for an organization to subdivide a large network into smaller, more efficient subnetworks to help minimize traffic and increase network speeds. Subnets are designed by accepting bits from the IP address's host part and using these bits to assign a number of small subnetworks inside the original network. And subnetting allows an organization to add subnetworks without the need to acquire a new network number from an ISP or an internet service provider. And here are some of the benefits of subnetting. It reduces network traffic by reducing the volume of broadcast. It helps to surpass the constraints in the LAN. So for example, you can surpass the maximum number of permitted hosts. And then it enables users to access a work network from their homes where there is no need to open up the complete network. Now let's talk about a subnet mask. So a subnet mask, this is a 32-bit number created by setting network bits to all ones and setting host bits to all zeros. The subnet mask splits the IP address into the network and host addresses, thereby defining which part of the IP address belongs to the network and which part belongs to the host. And you can readily identify a subnet mask because it will always start with the number 255. All right, so let's talk about the subnet mask classes. So you have class A, that is 255.0.0.0. That has 8 bits available for the network portion, which is represented by the number 255, and then 24 bits that are available for the host portion, which is the last 3 zeros. Then you have class B, that is 255.255.0.0. That's 16 bits for the network portion and 16 bits for the host portion. Then you have class C, that's 255.255.255.0. That's 24 bits. That's for the network ID. And then you have 8 bits for the host portion of the address. And then you have class D and E, and they are not defined. So now we're going to take all of that information that we just learned and we are going to put it all together to make it make sense. So once again, we have 3 main classes of IP addresses that we are dealing with when we're dealing with classful subnetting. You have class A, and those IPs start with the number 1 going all the way through the number 126. So once again, if you look at the first number in the IP address and it's between the numbers 1 and 126, you are dealing with a class A IP address. And this supports 16 million hosts on 127 different networks, and its subnet mask will be 255.0.0.0, and that subnet mask will have 8 bits available for the network portion, which is 255. And then if you convert the 255 into its binary equivalent, you will have a series of 8 ones followed by a series of 24 zeros, and the ones indicate that the bits have been turned on. And then it will also have 24 bits that are available for the host portion of the IP address, which is represented by the 0.0.0. And then you see the binary equivalent for 0.0.0, which will be represented by 8 zeros, dot 24 ones following after it. Now, if you are a little bit lost and confused on how to convert from decimal to binary and binary to decimal, I suggest you guys go visit my Network Plus playlist on this YouTube channel and check out the video that comes right before this one. I give a full breakdown on how to convert from decimal to binary to hexadecimal and hexadecimal back to binary back to decimal. So go check out that video if you are lost and confused about decimal to binary conversions. And then moving on, we have class B. So once again, this is from numbers 128 to 129. So if you see an IP address that starts with the number 128 or some other number going all the way up to 191, you're dealing with a class B. And this supports 65,000 hosts on 16,000 networks, and its subnet mask is 255.255.0.0, and it has 16 bits for the network portion represented by the 255.255, and down below you can see its binary equivalent, and then it has 16 bits for the host portion, which is represented by 0.0, and once again down below you can see its matching binary equivalent. And then we get to class C. This is 192 to 223, and this supports 254 hosts on 2 million networks, and its subnet mask is 255.255.255.0. It has 24 bits for the network, which is represented by the 255.255.255, and you can see its binary equivalent below, and it has 8 bits reserved for the host, which you can see its binary equivalent down below. And like I say, once again, if you are a little lost and confused on decimal to binary conversions, go click on the playlist on this channel for the Network Plus class, and then check out the video that comes right before this one. And now let's talk about a broadcast IP address. So a broadcast IP address, this is a special IP address used to transmit messages and data packets to network systems. Network admins verify successful data packet transmission via the broadcast address, and broadcast addresses are also the last IP address within a network, and it ends with .255. Another way to comprehend what a broadcast IP address is as follows. So just imagine that there is a host at a competition that is preparing to announce the winner of the competition, and they can use either one of the following approaches. The host can walk up to each contestant individually and quietly reveal the winner's name, or the host can announce the winner's name to all the contestants and then ask the winner to stand for recognition. option. The second option is more efficient and is essentially how broadcast addressing works in the real world. Now, as you can see on your screen here, I have provided you an example of classful subnetting to kind of explain to you guys what all of this actually means when you start looking at the numbers. All right, so let's go ahead and dissect this chart right here so we can make it all make sense as it relates to the lesson that we just got finished learning. In this chart here, you can see I have Class A, Class B, and Class C, and I have the matching IP addresses, subnet mask, network ID, IP address range, and the broadcast IP address. Basically, this chart signifies how you would take an IP address and then break it down or subdivide it so that you can figure out which IP addresses you can assign to devices within your local network. So you're like, what the heck are you talking about? All right, so let's go through this real quick. We're dealing with a Class A IP address. So we got the IP address of 102.168.212.226. As I told you guys earlier, 102, this represents a Class A IP address. Remember, this is the first octet. This number falls between the numbers 1 and 126. So that means we're dealing with a Class A IP address. And then I told you guys its subnet mask is going to be 255.0.0.0. The 255 represents the network ID host, and the 0.0.0 represents the actual host IP addresses. And the host IP addresses, these are the numbers that you are going to be using to assign to actual devices in your network, such as your laptop, printer, your phones, whatever it is that you got going on in your network. Now, before we can do that, we need to figure out what is the actual starting point of the network or the network ID. And as you can see right here, I have 102.0.0.0. This is our starting point for where this IP address is going to fall within. And we figure this out by simply zeroing out the host portion from the actual IP address. Because if we come over to our subnet mask, it's telling us that we only have bits turned on that represent the first octet, and then the second, third, and fourth octets are basically all turned off or zeroed out. So we're just going to zero out all of this right here, and this is going to give us our starting point of 102.0.0.0. This is the very first IP in this network. Then we come on over to the IP address range, and this is going to go from 102.0.0.1. The .1 is the very first IP address that we can assign to a device within our network. And this is going to take us all the way out to 102.255.255.254. .254 is the last IP address that we can assign to a device within this network. And like I told you guys earlier, a Class A network, this thing can support up to 16 million hosts or 16 million IP addresses. And that's very important as it directly relates to classful subnetting. Now, there is no way in the world you're going to use up 16 million IP addresses. In the next video, I'm going to talk about classless subnetting, where you'll be able to further subdivide this into a more manageable network to meet your specific needs. But for right now, we're just dealing with the general broad overview of dealing with Class A, B, and C IP addresses. So anyways, the IP address range, this is where we are going to pull IP addresses from to assign to devices that are within our network. Now, when we get to the broadcast IP address, I told you this is the very last IP address of the entire network. So the network ID and the broadcast IP, think of these as bookends. This is the start, this is the finish, and this is where you pull all of your IPs from to assign to devices. And this is going to end in 102.255.255.255. Now, as it relates to Class B and Class C, you're essentially just going to repeat the same process over and over again. Now, being that we're dealing with a classful subnetting scheme over here, it doesn't really matter what IP address that you put up in here, you're pretty much going to get the same answers over and over and over again, because you are dealing with an entire class. So to actually use the word subnetting is really not appropriate in this sense, because this is basically as far as you can break this thing down when dealing with Class A, B, and C classful subnetting IP addresses. But like I said, in the next video, we're going to talk about classless subnetting, which will allow for us to further break these IP downs into way more smaller, much more manageable numbers to actually deal with with that you might actually come across in the real world if you ever find yourself in a position where you're having to build a subnetting chart so that you can allocate IPs to devices within your network. But like I said, with this example, it doesn't really matter what IP address that you put in here. You're pretty much going to get the same answers over and over. All you're really going to be doing is just swapping out the first octet for whatever number starts off your IP address. But once again, to wrap this up, this is Classful subnetting. We're dealing with class A, B, and C, and you can identify that by looking at the first IP and figuring out exactly what class it falls in. That's going to tell you what your subnet mask is going to be. And then from there, you can proceed to figure out what your network ID is going to be by simply zeroing out the last 3 octets, or in this case, the last 2, or in this case, the last 1. And then to kick off the IP range, you're just going to add 1 IP to the network ID. And then to figure out what the end of the IP range is, you're simply just going to subtract 1 IP from the broadcast IP, because the broadcast IP address is going to end in .255. So this is going to be .254 by default. And this is where you will pick all your IPs to assign to all of your devices on the network. I know it sounds confusing, but it really isn't. But this is something that you got to know, and you're going to know it before you go out there and take this test. So with that being said, let's go ahead and do some of this outstanding check on learning. So the first question is, what is the leading octet value range for an IP version 4 address belonging to a class B network? Is it 128 through 191, 1 through 126, 192 to 223, or 224 to 239? So which one of these represents a class B network? And the correct answer is, it'll be 128 to 191. That will be the correct answer for a class B network. Next question. In IP version 4 addressing, the leading octet of an IP address with the value of 1 through 126 denotes that the IP address is within the range that belongs to what? Is it class A, B, C, or D? So 1 through 126, which class does this belong to? The correct answer is, this will be the class A address range. Next question. Which of the following answers lists the characteristic feature of the 192.168.0.0 through 192.168.255.255 address space? So which range does this series of IP addresses belong to? And the correct answer is, we are dealing with the class C IP range. All right. So in summary, we have talked about classful subnetting concepts such as the classful IP addressing, subnetting, subnet mask, and broadcast IP addresses. In this video, you're going to learn about IP version 4 and IP version 6 CIDR notation for classless subnetting. So let's talk about CIDR notation. So CIDR, that stands for classless interdomain routing. It's also known as prefix notation or slash notation. And this is a method for allocating IP addresses and for IP routing. CIDR notation was introduced in 1993 to replace the previous classful network addressing architecture on the internet. Its goal was to slow the growth of routing tables on routers across the internet and to help slow the rapid exhaustion of IP version 4 addresses. Because as you guys should know by now, there's only a finite number of IP version 4, and we've pretty much run out of them, which is why we switched over to IP version 6 in a lot of instances. So what you're looking at on your screen right here, this is a binary to decimal conversion table to help you guys quickly figure out what is the decimal number equivalent for the binary value or the binary value for the decimal equivalent. And this will come in handy when you are out there trying to do conversions so that you can fully understand what's going on with these IP version 4 addresses and IP version 6 addresses as well. So let's go ahead and get into some of these examples to show you IP version 4 CIDR notation. All right, guys. So if you recall from my last video where we talked about classful subnetting, we talked about three primary classes of IP addresses: Class A, Class B, and Class C. If you need a refresher, go watch the video before this one in this series. But as you can see, we have a Class A address, and that address is 101.0.0.1. Its subnet mask is going to be 255.0.0.0. When you convert this into binary, it's going to have 8 ones followed by 24 zeros, and the ones, they equal the network bits. So this represents the network, and all of these zeros, they represent the host bits on each network. So basically, these are all the bits that are reserved in this particular address that you could assign to various devices within your network. But like I stated, if you go watch my previous video talking about classful addresses that deal with Class A, B, and C addresses, you'll discover that this is way too many addresses for the average network to deal with. So that's why we got this thing called classless subnetting, which makes this pretty much more manageable to deal with. Also, and this is the CIDR notation, it's going to be represented by a /8, and this /8 just indicates that the first 8 bits have been turned on to represent the network we're dealing with. And as you can see in our handy dandy little chart down here, 8 ones, that represents 255. Let's go to the next example. All right, so here is an example of a Class B address. That's 129.0.0.1. Being that it's a Class B address, its subnet mask by default is 255.255.0.0. This is the binary equivalent to it, 16 ones, which represents the network bits, followed by 16 zeros, which represents each bit on the network that you could potentially assign to a bunch of devices within this network. And the CIDR notation is a /16 to indicate that the first 16 bits have been turned on. Let's go to the next example. And then we have a Class C address. In this one, we have 193.0.0.1. By default, its subnet mask is 255.255.255.0. This is its binary equivalent. 24 bits have been turned on to represent the network bits. And then we have the host bits, 8 bits, which represents the addresses that you could assign to potential devices within the network. And you have its CIDR notation of a /24, which once again represents the first 24 bits have been turned on to represent the network. Now, what if we're dealing with an IP version 4 address, but it doesn't have the standard default CIDR notation? So as you can see in this example, we have 198.0.0.1. Well, if you were paying attention in my last video, you would know that a 198 IP address would automatically make this a Class C address. And by default, a Class C address, its subnet mask will usually be 255.255.255.0. But in this instance, we have a /14 or a CIDR notation 14. So how would we deal with this? Well, we're just simply going to turn on the first 14 bits in the overall network so that we can get this subnet mask right here of 255.252.0.0. And if you convert this down into its binary equivalent, you will have 8 ones followed by 6 ones and 2 zeros, and then the rest of these will be zeros. Or you can just come down here, take the number 252, come down here and find out what its decimal equivalent is going to be. And then, like I said earlier, all of the ones are going to represent the network bits, and the zeros are going to represent the host bits for each network, which leaves a remainder of 18 bits. So basically, when you see a CIDR like this and it's attached to a standard A, B, or C classful IP address, basically what we're doing, we are essentially borrowing bits from the host in order to cover down for the network portion of the IP address. And this is what is going to allow for us to really, truly subdivide these IP networks into more granular, more manageable IP addresses that a typical network would be accustomed to dealing with, instead of dealing with tens of thousands, if not possibly millions of IP addresses that, you know, your average network just not be able to deal with. And so, like I say, once again, we are essentially borrowing bits from the host in order to make this CIDR notation 14 or /14 network for this IP address. We just turn the first 14 bits on and then the remaining bits are turned off. So that's how we end up with a subnet mask of 255.252.0.0. Next example. So we have IP version 4 address 201.1.0.0. Now the 201, that would normally automatically make this a Class C address. And once again, a Class C address that would normally have a subnet mask of 255.255.255.0. But being that we have a CIDR notation of /21, that means we're only going to be using the first 21 bits instead of the first 24 bits. So we're just going to turn all of these on. You got 8 ones here, 8 ones here, and then you have 5 ones here followed by 3 zeros. And that's what gets you 248, or you just go 248. Look down here at your chart, 248. You have 5 ones followed by 3 zeros down here. And once again, the ones, they equal the network bits, 21 bits, and the zeros equal the host bits on each network, 11 bits, and you have a /21 notation. All right, so in this example, we're going to figure out how to create the subnet mask if all we are presented with is the CIDR notation of /27. So being that we have a /27, that means we are going to turn on the first 27 bits. So you got 8 bits here, 8 bits here, 8 bits here, and 3 bits here. That's going to get you a 255.255.255.224. If you don't know how to convert this, you got 3 ones followed by 5 zeros. Come down to your chart. 3 ones followed by 5 zeros equals the decimal number 224. And that's how we end up with this here. And once again, the ones equal the network bits and the zeros equal the host bits on each network that you can assign IP addresses to devices for. All right, so now we're going to talk about IP version 6 CIDR notation. So an IP version 6 address, this is usually distributed by the Internet Assigned Numbers Authority, or the IANA. The IANA, they are responsible for providing address blocks to the regional internet registries, who then assign smaller blocks of IP version 6 addresses out to the ISPs, or the internet service providers. And from there, the ISP will then assign you, the end user, with an IP version 6 address that has a /48 subnet, which you can then further subnet down as needed. So basically, these are the people that create the IP addresses right here. And I'll show you on the next slide how this all breaks down. They then pass it off to another group of people who deal with a region, and then they slap on a block for their IP address identification. And then they pass it off to the ISP, who then slaps on a block for their IP address identification. And then they pass it off down to the end user, who can then begin the process of creating their own network. And then they can go ahead and try to subnet it out. And then they can go ahead and dish out IP addresses from the remaining bits that represent the host to devices within their network. Now, before we get started, you need to remember that an IP version 6 address is 128 bits long, where it is 8 blocks of 16 bits. So basically 16 times 8 equals 128. And the values and numbers, remember, they are hexadecimal numbers. These are not decimal numbers. So this is not a decimal number. This is a hexadecimal value. This is hexadecimal. All of these are hexadecimal values, not decimal numbers. And that's important if you all have to go through the conversion process of converting these back into their binary or decimal equivalent. And if you don't know how to do that, go watch the video in my playlist that came before the video that came before this one, where I talk about decimal to binary to hexadecimal conversions. I walk you guys step by step on how that whole process works. All right. So anyways, let's talk about this IP version 6 address. So this is our IP version 6 address. It is 128 bits long. And remember, it's 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8. 8 blocks, and each block has 16 bits in it. Now, The first 3 blocks, this is called your global routing prefixes, and they are 48 bits long. 16 times 3 is 48, right? Remember, this is the IANA, the Internet Assigned Numbers Authority. They are responsible for setting up the first block identification. Then they pass this IP address off to the regional internet registries, and they will go ahead and assign their IP identification address onto it. And then they pass this off to your local ISP or your internet service provider, and they will go ahead and assign their identification number to this IP address. So that is the global routing prefixes, are the first 3 blocks of an IP version 6 address. And then we get down to block number 4. This is locally assigned by the end user or you, and this is what you will use for creating your network IDs. And this thing is 16 bits long, and your network ID, it can start with a 001, and then from there you can create another network ID of 0002, 3, 4, and so on and so on. And remember, this thing has 16 subnet bits. Within this subnet, you can create a grand total of 65,536 total subnets out of this IP address if you wanted to. That's how many different addresses you can have going on up in here. But reality is you will probably never create or have a need for 65,536 total subnets. But if you wanted to, the option for you to do it is there. And this is also part of the reason as to why the switch from IP version 4 to IP version 6 is in effect, because there's almost an infinite number of possibilities that you can create with IP addresses, as opposed to IP version 4, which is capped off at around, I want to say 4 billion, if I'm not mistaken. I have to go back and check my notes, but that's why we use IP version 6, because theoretically you can never run out of IP addresses. And then we get down to the last 4 blocks, which represents the host ID of this IP version 6 address. And this host ID can support 2 to the 64 power hosts, which is approximately equal to 18 million trillion hosts per subnet. So each subnet from the previous slide can support up to 18 million trillion host IDs or IP addresses. So remember the last slide I said you had 65,000 subnets you can create, and each subnet out of the 65,000 can support 18 million trillion hosts per subnet. That's why I say theoretically you will never ever run out of IP addresses with IP version 6. And now let's talk about its actual CIDR notation. So once again, here is the IP version 6 address we have been dissecting. Here is the subnet address. It'll be 2500 AA 3333 0001, followed by a bunch of zeros. Now remember this 001, this represents the network we're dealing with. And if you remember from my previous video, when I stated what the network ID is going to be, that is normally the very first IP address within the network. So that's why we have a 0 right here instead of a 1. So this is technically the network ID for this IP address to fall up under. Now, if you want to shorten this thing out, this is how it will look. You can apply what is called removing leading zeros. So basically you would have 2500 AA 3333:1. So we just took out these first 3 zeros right here just to deal with this one. And being that we have a bunch of zeros following it, we can just go ahead and put 2 double colons in its place. Then when we put the standard /64, and this is going to represent the subnet mask options of this IP version 6 address, which is basically these last 4 blocks. And remember, 64 bits, this is 4 blocks of 16 bits apiece. 4 times 16 equals 64. So to try to help it all make a little sense as to what's going on with this IP version 6 CIDR notation, here is an image showing you a program called Packet Tracer, where the person who created this has created a grand total of 5 different networks. So I'm not going to get too deep into this, but every time you connect a router to another router, you are creating a network, because if you remember from my A+ course, or even earlier in this Network Plus course, I stated that when routers connect to routers, you were essentially connecting one one network to another. So this network right here has been assigned 2001:DB8:1 with a bunch of zeros after it to represent, I guess this is network 1. And then right here, this will be network 2 because we're connecting this router to this router. And now we're connecting this router to this switch. So this will be network 4, 3, and 5. So 1, 2, 3, 4, 5. We have a grand total of 5 different networks going on over here. And like I stated earlier, this third block represented by this 1, 2, 3, 4, and 5. This is what has been assigned to these networks from the ISP, or your internet service provider. And then from there, if we come down to here to this network, network 3 with the /64, that's where you can start kicking out IP addresses to your endpoint devices like these 2 computers, smartphones, laptops, or whatever other device is within this network. And also something to remember, the CIDR notation is always going to be /64. That is always what the CIDR notation is going to be for IP version 6. All right, so in this lesson, we have talked about IP version 4 and IP version 6 CIDR notation for classless subnetting. All right, guys, so we have been learning subnetting for the past 2 or 3 videos in this Networking Plus N10-007 certification class that I'm putting together. And some of you guys are probably lost and confused and wondering why we're doing this. Well, now I'm going to show you why we are doing this, to show you that these numbers actually mean something other than weird looking numbers written in a chart. So I'm going to show you guys a concept called a router on a stick. This is something that you will learn or apply if you go for your CCNA in the future or whatever the case may be. So the first thing you have is a router. It is represented by this circle with these lines going down the middle. It is connected to a switch, which is represented by this square with arrows going in opposite directions. And then hanging off this switch, you might have a computer over here, a computer over here, a computer over here, and a computer over here. Now, in this example, all these computers can be on the same VLAN, or we can separate them to where these guys will be representing VLAN 2, these guys will be representing VLAN 3, and the switch by default is going to represent VLAN 1. And if you don't know what a VLAN is, it stands for Virtual Local Area Network. Basically, VLANs allow for you to logically divide a switch into separate networks. So VLAN 1, 2, and 3, these would all be 3 separate networks. And in order for a computer over here in VLAN 2 to communicate with a computer over here in VLAN 3, they would have to pass their traffic through the router, come back down, and then they could receive the message. If they were all in the same VLAN, VLAN 1, if this computer wanted to communicate with this computer over here, they would only have to pass traffic through the switch to get to the other device. But being that they have been logically separated onto one physical switch, they have to use a router. Why? Because routers connect networks to networks. So if you're a little lost or confused about that, I advise you to go back and check out some of my earlier videos that explains this concept. So now what we're going to do, we're going to talk about actually subnetting an IP address. So just imagine that this router, this switch, and these computers are all in the TechG Corporation right now. And within the TechG Corporation, we have paid for some internet service from Comcast or whoever else is out there, and they said, hey, this right here is your IP address that you are going to use for your network. So basically, this IP address is essentially the public IP address for this router that is communicating with the devices owned by Comcast so that I can go out there and live my wildest fantasies surfing the internet. Okay. Now, within this network, I want to go ahead and subdivide this IP address so that I can allocate IPs for this device, this device, this device, this device, and any other device that I want. Now, within this example of the TechG Corporation, I want to have sections. Now, currently TechG doesn't make a lot of money, so all I can afford is a router and a switch, right? But I do have enough money to have a couple different departments. So let's just say that this is my marketing department over here, and this is my HR department over here, and we're all connected to the same switch, and we'll call this switch SW. And this is our router in case you need to see it. Now, I want the people in HR to only be able to access whatever devices are within the HR department. And I want the marketing people to only be able to access devices in the marketing department. So that's why these guys are in VLAN 2. These guys are in VLAN 3, but I also want them both to be able to communicate with the switch VLAN 1 as well. Like I stated earlier, in order for that to happen, you need to go through the router so you can pass traffic back and forth. Now, this IP address right here, 192.16.1.1, this is a Class C address. And if you guys recall, a Class C address is basically a classful IP address, and it ranges from 192 to 223. All right. So basically any IP address between 192.0.1.1 all the way through 223.255.255.254. That is what a Class C IP address is. So now, that is what the ISP has given me. They said, hey, this is your quote unquote street address for your router over here. Now, we all know what routers, if you've been paying attention to my class, you got a public IP address and you got your private IP address. And within the router, they perform this thing called NAT, network address translation, so that basically you can quote unquote disguise all the IP addresses within your network. So when external networks are communicating with your network, the only IP address they see is this one right here. But now within this network, I want to go ahead and subdivide or subnet this network so I can allocate IP addresses to all these random devices over here in their particular VLANs. And the reason I want to do this is because it is going to make it much more easier and manageable to deal with a smaller collection of IP addresses. So we're going to go ahead and subdivide that. So before we get started, what we need to do is this. I need to first determine how many addresses do I actually need. So let's go to our marketing department over here. Let's just say our marketing department, I need 100 IP addresses for marketing. And then for my HR department, I need 50 IP addresses. And then for my switch, I need 6 addresses. And then for my router, I need 2 addresses. And this is my starting IP address right here, which once again is a /24 CIDR notation address or Class C address, right? So now we're going to go ahead and begin the construction of what is called a VLSM chart, or a variable length subnet mask chart. This is what's going to allow for us to get back over here and figure out what IP addresses we can assign to various devices within the network. So like I said earlier, we're going to need 100 IPs for the marketing department. We're going to need 50 IPs for the HR department. Our switch is going to need 6 IPs for whatever reason. And our router is going to need 2 addresses in order to make this thing work. And once again, our starting IP address is 192.16.1.1. That is our starting IP address over here. So let's go ahead and start constructing this chart. So first thing we're going to do, we're going to put what is the name column. Then we're going to have the number of hosts that we're going to need. We're going to need to know our incremental value, also known as our positional value. And I'll explain all this as we go along. We're going to need to know our network ID. We're going to need to know our gateway address. We're going to need to know our IP range. And we're going to need to know our broadcast IP address. And we're also going to need to know our custom subnet mask. And in some cases, this is more particular to CCNA, you may need to know this thing called your wildcard mask. But we're not going to worry about the wildcard mask at this present moment. So this is the chart that we are about to build, ladies and gentlemen. Now, before we go ahead and start building this chart, let me go ahead and show you a quick little way on how to go about figuring out how many hosts you may need and what the subnet mask may be and all that wonderful stuff real quick. All right, so here's a little handy dandy chart that you can put together real quick when you're out there taking your Network Plus exam, which is going to help you figure out what the hosts are and the appropriate subnet mask that goes with the host. And all you're going to be doing is using your power of twos chart. So you're going to put 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. You can drag this thing out, 2 to the 8th, 2 to the 9th, so on and so forth. But this right here represents your 4th octet. So from there, you can calculate how many hosts you're going to need. So 2 to the 0, well, that equals 1. 2 to the 1st, 2, 4, 8, 16, 32, 64, 128. And then from there, we can go ahead and figure out what our subnet mask is going to be using slash notation. So if you got one host right here, basically that means you're going to have a slash 32 for your subnet mask. Over here, you're going to have a slash 31, slash 30, slash 29, slash 28, 27, 26, and slash 25. That's what your subnet mask is going to be. Now, if you want to know what this actually looks like in binary notation, basically this will look like this. You would just have the first 32 bits turned on, if you recall from my last video. So you have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So that's 24, 25, 26, 27, 28, 29, 30, 31, 32. What is that? 1, 2, 3, 4, 5, 6, 7, 8. All right, so all of them are turned on. I don't know why I didn't just put that together real quick. Slash 31, same deal. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and a 0. So in the slash 31, basically you have 31 bits turned on. 1 bit is reserved for the actual host. Over here, you're going to need at least 2 IP addresses that are going to be used for assigning IPs to devices. And I'll explain all that as we go along. But basically, instead of you sitting around here drawing out all of your binary, you can just go ahead and remember this slash notation in conjunction with the host, and that'll help you out and expedite this process a whole lot faster. So now let's get back to our chart over here. So like I stated, this is the IP address that has been assigned to us, 192.16.1.1/24. We need 100 devices that can have IP addresses for our marketing department. We need 50 devices for our HR department that can have IPs. Our switch needs 6 IPs for some weird reason, and our router is going to need 2 IP addresses. Now, when we begin this process, we need to start figuring out how to subdivide this network or subnet this network for the one that has the highest requirements, which will be 100. So we come over here, we put marketing, and we need 100 devices over here. Or 100 IPs, I should say. Now we need to figure out how many hosts do we need. So what we're going to do with each of these numbers, 100, 50, and 6, we're going to add the number 3 to all of these numbers. So 100 plus 3 is going to give me 103. 50 plus 3 is going to give me 53. And 6 plus 3 is going to give me 9. And the reason why we're adding 3 is because the 100, that actually represents the actual devices that are going to be assigned IP addresses within this little network that I set up over here. Now we're adding 3 because we also have to take into account for the IP address for the network ID, the gateway IP address, and the broadcast IP address. The network ID, this is basically the identification for this network right here. It's essentially almost the same thing as the main IP address that was assigned to us from the ISP, but now we are acting like our own quote unquote ISP, and we need to first and foremost identify the network that these devices are going to reside on. So that's how we get to the network ID. Then we also have to identify the gateway IP address. And the reason we're doing that, so when we're out here sending messages around, we need to tell these messages what is the gateway IP address that they need to go find in order for them to get out onto the wild internet or communicate with somebody else in another network. And typically your gateway IP address, at least within this setup, is going to be the private IP address associated with this router for this overall network. But within this little tiny network, we're creating a separate gateway IP address, which will be programmed into this router, but we're not going to go too far into that for this video because that's more of a CCNA related topic. But basically, we need that gateway IP address. So when I start pressing 1s and 0s and sending messages, these messages know, hey, I need to go find a certain gateway IP address so I can escape my network and go communicate with somebody over here or go talk to the router so I can get out to the greater internet. And then we also need to identify what is called the broadcast IP address. The broadcast IP address is essentially the last IP address before you begin the next network. And then everything in between the gateway and the broadcast is your IP range. This is where you will pull IP addresses from to assign to these 100 devices over here. And then the custom subnet mask, this basically identifies the portion of the network that all of this stuff is going to reside on. So we'll look at my previous videos where we're talking about this and I explain that in greater detail. And the wildcard mask, we're really not going to focus on this for this particular lesson. This is something that you'll need to know when you are going for your CCNA. And I'm just trying to keep this as simple as possible so that we can make sense of why we're doing this in the first place. So like I stated, we got 100 devices that need IP addresses for our marketing department, 50 devices for our HR department, 6 IPs need to be assigned to the switch for whatever reason, and then the router is going to need 2. And with the router, we're going to add another 2 to it, and I'll explain that when we get down to it. So 100 plus the 3. Remember the 3 came from, we need to set up an IP for the network ID, the gateway, and the broadcast. So we need a grand total of 103 IP addresses within this network. Now, what we're going to do next, we're going to figure out what is the positional value or the incremental value for this particular network that we are about to construct. And we come back over to this chart over here to figure that out. So when I was telling you about the hosts, I put 1, 2, 4, 8, 16, 32, 64. Then I drew a line to indicate the break between octet number 4 and octet number 3. And if you were to keep dragging this power twos thing out, you would start this positional spot all over again and just keep going down the line. But basically, these incremental values or these positional values are essentially going to tell me what spot in the octet is going to fulfill my actual host requirements so that I can have enough IP addresses to allocate to my devices. All right. So we come back over here. As I stated, I need 103 IP addresses in total for this particular network. We come back over here to our positional values, incremental values, whatever you want to call them. And we're going to figure out what number does 103 go into without going over. So does 103, does it go into 1? No. 2, no. What does it actually go into? 103 can comfortably fit inside the number 128 without going over. Now, being that we need 103 hosts, that means we're going to be just fitting comfortably inside of the 4th octet, dealing with our positional value of 128. So we're going to come down to our incremental block and we're going to put a 0.128 to indicate that we are operating out of the 4th octet because that is what 103 comfortably fits inside of, ladies and gentlemen. Now we need to figure out what is our network ID. So remember, this is our starting IP address, 192.16.1.1. With this particular network, we're operating out of the 4th octet. So that means we're just going to zero out the last octet. So our network ID for this network is going to be 192.16.1.0. That is the very first IP address for this network, which is part of the extra 3 numbers that I added here. Our gateway address is just going to be one IP address above this one. So that's going to be 192.116.1.1. And then our IP range is going to be one IP greater than the gateway. So it'll be 192.16.1.2. I'm just going to go ahead and put a .2 and we're going to stop right there. Now we're going to go ahead and start trying to figure out our requirements for the HR department that requires 50 hosts. So we come back down here, we identify HR. We said we needed 50, but we're going to add 3 to get 53 because remember, we got to create an IP address for the network ID, the gateway, and the broadcast. And then we're going to go ahead and figure out our incremental value for this particular network. So we come back over here. We said we need 53 IPs. What number does 53 go into without going over? We see it goes into the number 64. And being that we're working out of the 4th octet, our incremental value is going to be 0.64. And now we're going to go ahead and we're going to figure out the network ID. So this is what we're going to do to figure out the network ID for the HR department. We're going to take the network ID of the marketing department and add it to the incremental incremental value. So we're going to take 192.16.1.0 and add it to 0.128. Essentially, we're just going to be adding the fourth octet number. So 128 plus 0 is going to give us our starting network ID for HR department. It's going to be 192.16.1.128. That is our network ID for the HR department. Basically, this is the starting point for this network right here. And then the same thing applies with the gateway. It's going to be 192.16.1.129, just one IP address greater than the network ID. And then our IP range is going to start off with a .130. Now, we can use this number to go ahead and figure out what is the broadcast number for the marketing department, because like I told you guys, the broadcast IP address is the last IP address before you start the next network. So all we're going to do is just subtract one IP address from the network ID of the HR department, and the broadcast IP address for the marketing department is now going to be 192.16.1.127. And now we can figure out the last IP address of the IP range where we can pull IP addresses from. And in this example, it is going to be a .126. So everything between 192.16.1.2 through 192.16.1.126, this is where we can assign IP addresses to all of the devices within the marketing department. And as you can see, this is a grand total of 124 IP addresses, I believe. That is enough IP addresses to cover our requirements of 100 devices needing IP addresses. Now we can come over here and figure out our custom subnet mask, and that is real simple. All we got to do is just go back and look at our chart up here. We stated that we needed 103 hosts. 103 went into the number 128, and that gives us a /25 IP address. And if you want to write this out in this binary equivalent, it's going to look like this. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, then 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7, 8. All right, I put too many zeros on it. So that's what it's going to be. When written out in this binary equivalent, your subnet mask is going to be 255.255.255.128. So that is your actual subnet mask, 255.255.255.128. We just shortened it out and put /25. I mean, you can write it out if you want. It doesn't really matter. So there's another way you can figure this out for those of you who like math. So there's an actual formula for this. So basically the custom subnet mask, it equals the number 256 minus the network host. So 256 minus the network host equals the custom subnet mask. So basically you can just do 256 minus our network host, or our incremental value of 128 or 128. So 256 minus 128 is going to give you 128 over here. But since we're working out the fourth octet, it's going to be over here. So those of you who like math, that is a quick little easy formula. Custom subnet mask, 256 minus the network host, or the incremental value, I should say. And then that's going to tell you what your actual values are going to be for your custom subnet mask. Or you can do it the binary way, or you can just remember this easy little chart that I just showed you right here. Totally up to you. So now getting back to our chart over here. So we have pretty much solved all of our requirements for the marketing network. Now we're going to solve the IP address requirements for the HR department. So once again, we got 50 devices that need IP addresses. We add 3 because we got to account for the network ID, the gateway, and the broadcast. We figured out the network ID by taking the previous network ID and adding the incremental value to give us our current network ID, which then told us what our gateway IP address is going to be, which is just one IP greater than the network ID. Then it also told us our starting IP address, that we can start dishing IP addresses out to devices, and that's going to be a 130, which is just one IP greater than the gateway. So now we got that far. So now we need to go ahead and figure out the requirements for the switch. So we got our switch over here. I said we need 6 IP addresses addresses for whatever reason. We're going to add 3. So that means we're going to have a host requirement of 9. We're going to go ahead and figure out our incremental value. So we come back over to this chart here. What number does 9 go into without going over? And we see it goes into the number 16 without going over. So that means we're working out of the 4th octet still. So now we got a 0.16. So now we can go ahead and figure out the network ID. So we're going to take HR's network ID, add this incremental value, and that's going to give us the network ID for the switch. So 128 plus 64 equals 192. So our network ID for the switch is going to be 192.16.1.192. That's going to be our network ID. Our gateway is going to be 1 greater than the network ID. So 192.16.1.193. That is our gateway IP address. And then our IP range is going to start with 1 IP greater than the gateway. So that's going to be .194. Now we can go ahead and use this information to solve for the broadcast for the HR department. So we go to our network ID and we just subtract 1 IP address to get us 192.16.1.191. And then from there, we're just going to subtract 1 IP address from the broadcast to get our last IP address of the IP range, which is going to be 190. So right here, we're looking at 60 IP addresses that we can assign to the HR department, even though the HR department only has a requirement of 50. Well, 60 is enough to cover all to meet this requirement right here. And then also we can go ahead and figure out our custom subnet mask based off of our incremental value of .64 or our positional value. And we come back over to our chart. 64 is going to yield us a /26 custom subnet mask. So now we solved all this for the switch. So now we need to go ahead and figure out the requirements for the router. Now with the router, we got a requirement of 2, but we're going to add an additional 2 IP addresses for the router to come up with 4 total hosts. And why are we doing that? Because we need to account for the network ID of the router and the broadcast. We do not need to account for the gateway IP address. Why? Because the router is the gateway. So we come back over to our little chart over here. We need to account for 2 IP addresses for this router, the private IP address and the public IP address. That is essentially what we are accounting for in this overall network that we are constructing over here. Remember, the router by default, at least in this scenario, this is the gateway device. Everything is trying to find this gateway device so they can go out there and communicate with the internet, or this network can communicate with this network and vice versa. So that's why we don't need to account for a gateway, and we only need to add an additional 2 hosts to this. So now we need to go to our chart and figure out what does the number 4 go into without going over. So 4, it goes into the number 4 without going over. So our incremental value, since we're in octet number 4, is going to be 0.4. Now to find the network ID for the router, we're just simply going to add 192 plus 16. So our network ID for this router is going to be 192.16.1.208. That is our network ID for the router, because we simply took the network ID for the switch and added it to the incremental value 192 plus 16. We're in the 4th octet is going to yield us a 208. Now we can figure out our IP range. It's going to be 1 IP greater than the network ID. So this is going to start with a .209. And then also we can use this number to figure out the last IP address of the switch. So we're just going to subtract 1 IP, and that's going to give us a .208. So that'll be 192.16.1.207. And then from there, we can just subtract 1 IP address, and that'll give us a .206. So all these IP addresses, that's a grand total of like 12 IP addresses. That'll meet all of our requirements over here for 6 IPs, or a grand total of 9 IPs. So we can, dish out IPs all over the place if we need to. And then we get back over here to our incremental value, .16. Come back over here, 16 yields a /28 subnet mask. And now we're going to drag this thing out one more step so we can figure out this same information for the router. router. So we're going to take our network ID for the router, .208, and add 4 to it. And that's going to give us 192.16.1.212. We're going to subtract 1 from this miscellaneous network so we can figure out our broadcast. That's going to give us 192.16.1.211. And then we're going to subtract 1 from the broadcast of the router to figure out the last IP that's ending for this particular device. And that's going to give us a .210. So essentially 2 IP addresses, .209 and .210, that are going to be assigned to this device if we want. And then from there, we can also take our .4 and figure out what our custom subnet mask is. So we come back up to our chart. We see our positional value of 4 is going to yield a /30. And basically a /30 is a .252. So this will be 255.255.255.252 once you crunch out the binary and work its way all the way out. So in a nutshell, ladies and gentlemen, this is what a VLSM chart looks like when you are trying to subnet a network so that you can have IPs that are way more manageable to deal with when you are going through trying to subnet the network beyond just the initial IP address that you were assigned from your ISP. So in this example here, we have our marketing department. They represent VLAN 1 or VLAN 3 or whatever. It doesn't even matter. They represent VLAN 3. And we said we needed 100 devices to assign to IP. So let's just imagine that in this network, there are 100 computers hanging off this switch in VLAN 3. Well, from here, when we go through and start programming our computers to bring them to life, if we're doing this manually, these are the IP addresses that we are going to assign to these devices. So this device right here might be .2, and this one might be .3, .4. We have options all the way up to .126. For HR, we said we needed 50 devices to have IP addresses. So this is our HR department. So imagine there are 50 computers hanging off this switch in VLAN 2. We come to our IP range. We have everything from .130 all the way to .190, a grand total of 60 IP addresses. So this one could be .130 and this one could be .131 all the way up to 190 if we want. And then from so on and so forth. And then once we actually get inside of the computer, if we were to manually do this, it's going to ask you for the IP address, the gateway IP address for the network, and the subnet mask. So you would just easily come back to your chart. So let's just say we're programming up this computer. We give it the IP address of 192.16.1.130 because this is the HR department. Well, from this chart, we already know what the IP address for the gateway is going to be. And we also know what the subnet mask is going to be for this particular device in this network. And you would do the same thing for this one over here. And then you come over to VLAN 3, marketing. Like I said, we gave this one an IP address of 192.16.1.2. And then this guy will be .3. So if we go in here and manually program up these two computers, we already know what our gateway IP address is going to be. And we know what our custom subnet mask is going to be for this device so that it can properly communicate on the network. And then we also know what the information for the switch and for the router is going to be. Anyways, I just wanted to show you guys this real quick, even though it's probably been like a 30-minute long video or something like that, as to what all this madness means when we were going through subnetting, learning about classful subnetting, classless subnetting. Well, this is what these numbers actually represent when people start talking about subnetting. This basically allows for you to create networks inside of a grander network so you can easily manage this thing better, because yes, even though I have them logically separated on the switch, I might have another switch hanging off this router over here to create another little network. I could throw some firewalls up in here. I can get real funky out in these streets if I really wanted to. But this VLSM chart, this is what allows for you to create a manageable pool of IP addresses to deal with. That's why we go ahead and subnet this thing down based off of our specific requirements that we need for our network needs. So that is why we do subnetting in a nutshell, ladies and gentlemen. In this video, you're going to learn about network topologies such as logical versus physical topologies, star, ring, mesh, bus, ad hoc, and infrastructure topologies. And you're also going to learn about network types such as LANs, WLANs, MANs, WANs, CANs, SANs, and PANs. Let's talk about a network topology. So a network topology refers to the physical or logical layout of a network. It defines the way different nodes are placed and interconnected with each other. Alternatively, a network topology may describe how the data is transferred between those nodes. Let's talk about some wired topologies. And the first one we're going to talk about is a logical topology. And a logical topology, this is a concept in networking that defines the architecture of the communication mechanisms for all nodes in a network. Using networking equipment such as routers and switches, the logical topology of a network can be dynamically maintained and reconfigured. Next is the physical topology, and a physical topology refers to the interconnected structure of a local area network, the method employed to connect the physical devices on the network with the cables, and the type of cabling used. All of that constitutes the physical topology. So this is essentially how you wire all this stuff up. Next, we're going to talk about a star topology. This is also known as a star network. This is one of the most common network setups. In this configuration, every node connects to a central network device like a hub, switch, or a computer. The central network device acts as a server, and the peripheral devices act as clients. In a star topology setup, either a coaxial or RJ45 network cable is used, depending on the type of network card installed in each computer. And here are some of the advantages of a star topology. It has a centralized management of the network through the use of the central computer, hub, or switch. It's easy to add another computer to the network. And if one computer on the network fails, the rest of the network continues to function normally. Its disadvantages: it may have a higher cost to implement, especially when using a switch or router as the central network device. The central network device determines the performance and number of nodes the network can handle. If the central computer, hub, or switch fails, the entire network goes down and all computers are disconnected from the network. Next, we have a ring topology, and a ring topology is a network configuration where device connections create a circular data path. Each network device is connected to two others like points on a circle. Together, devices in a ring topology are referred to as a ring network. In a ring network, packets of data travel from one device to the next until they reach their destination. Most ring topologies allow packets to travel only in one direction, and this is referred to as a unidirectional ring network. Others permit data to move in either direction, and this is called bidirectional. Ring topologies may be used in either LANs or WANs. Depending on the network card used in each computer of the ring topology, a coaxial cable or an RJ45 network cable is used to connect computers together. And here are some of the advantages of a ring topology. All data flows in one direction, which reduces the chance of packet collisions. A network server is not needed to control network connectivity between each workstation. Data can transfer between workstations at high speeds, and additional workstations can be added without impacting performance at the network. Some of the disadvantages are all data being transferred over the network must pass through each workstation on the network, which can make it slower than a star topology. The entire network will be impacted if one workstation shuts down, and the hardware needed to connect each workstation to the network is more expensive than Ethernet cards and hubs and switches. Next, we have a bus topology, and this is also referred to as line topology. And this is a network setup where each computer and network device is connected to a single cable or backbone. And depending on the type of computer network card, a coaxial cable or an RJ45 network cable is used to connect them together. And some of the advantages of a bus topology are as follows. It works well when you have a small network. It's the easiest network topology for connecting computers or peripherals in a linear fashion, and it requires less cable length than a star topology. Some of the disadvantages are it can be difficult to identify the problems if the whole network goes down. It can be hard to troubleshoot individual device issues. The bus topology is not great for large networks. Terminators are required for both ends of the main cable. Additional devices will slow the network down, and if the main cable is damaged, the network will fail or split into two. Let's talk about wireless topologies, and the first one we're going to talk about is the mesh topology. So a mesh topology is a network setup where each computer and network device is interconnected with one another. This topology setup allows for most transmissions to be distributed even if one of the connections goes down. It is a topology that is commonly used for wireless networks. And there are two forms of a mesh topology. The first one is a full mesh topology. So every computer in the network has a connection to each of the other computers in that network, and the number of connections in this network can be calculated using the following formula: n by n-1 divided by 2, where n is the number of computers in the network. And then the next type is a partially connected mesh topology. And this is where at least two of the computers in the network have connections to multiple other computers in that network. It is an inexpensive way to implement redundancy in the network. If one of the primary computers or connections in the network fails, the rest of the network will continue to operate normally. And some of the advantages of a mesh topology are as follows. It can manage high amounts of traffic because multiple devices can transmit data simultaneously. A failure of one device will not cause a break in the network or transmission of data, and adding additional devices will not disrupt data transmission between other devices. And some of the disadvantages are the cost to implement is higher than other network topologies, which makes it a less desirable option. Building and maintaining the topology is difficult and time consuming, and the chance of redundant connections is high, but that can add to the high costs and potential for reduced efficiency. Next, we have an ad hoc. So an ad hoc network, this is a decentralized type of wireless network. The network does not rely on a pre-existing infrastructure such as routers and wired networks or access points in a managed or infrastructure wireless network. Instead, each node participates in routing by forwarding data for other nodes. So the determination of which nodes forward data is made dynamically on the basis of network connectivity and the routing algorithm in use. So in other words, devices, they connect on the fly to share data between them without needing a network router, network switch, or other network equipment to create the network. The devices themselves act as the network equipment, creating a network between them. And then we have infrastructure. So an infrastructure topology has specialized wireless equipment for permitting the wireless communications to take place. Many homes today, they feature a wireless local area network and a wireless access point, which allows the various computers to communicate with each other through the wireless access point, acting like a hub device. This wireless access point connects to the service provider of the home user with a wired connection. So for example, a coaxial cable could connect to the broadband cable service for high-speed internet connectivity. And now let's go on and talk about network types. So the first one we're going to talk about is a LAN, or a local area network. And a LAN, this is a computer network within a small geographical area such as a home, school, computer lab, office buildings, or a group of buildings. A LAN is composed of interconnected workstations and personal computers, which are each capable of accessing and sharing data and devices such as printers, scanners, and data storage devices anywhere on the LAN. LANs are characterized by higher communication and data transfer rates and the lack of any need for leased communication lines. LANs can be wired or wireless. Wired LANs can have high-speed connections with Ethernet, unshielded twisted pair cable, shielded twisted pair cable, or fiber, and legacy LANs were often connected by coaxial cables. The next type of network is a wireless LAN. So a wireless LAN is a wireless computer network that links two or more devices using wireless communications to form a LAN within a limited area such as a home, school, computer lab, campus, or an office building. This gives users the ability to move around within the area and remain connected to the network. Through a gateway, a wireless LAN can also provide a connection to the wider internet. Next one we have is a CAN, or a campus area network. So a CAN is a computer network made up of an interconnection of LANs within a limited geographical area. The networking equipment, such as your switches and routers, and transmission media, such as your optical fiber cables, your Cat5 cable, etc., are almost entirely owned by the campus tenant or owner, which could be an enterprise, a university, government, etc. Also, a CAN is larger than a LAN, but it is smaller than a MAN or a WAN. And next we have a MAN. This is a metropolitan area network. So a MAN is a computer network that interconnects users with computer resources in a geographic region of the size of a metropolitan area. The term MAN is applied to the interconnection of LANs in a city into a single larger network, which may then also offer efficient connections to a WAN. The term is also used to describe the interconnection of several LANs in a metropolitan area through the use of point-to-point connections between them. Then we have a WAN, or a wide area network. So a WAN is a network that exists over a large scale geographical area. A WAN connects different smaller networks, including LANs and MANs. This ensures that computers and users in one location can communicate with computers and users in other locations. WAN implementation can be done either with the help of the public transmission system or a private network. The internet is an example of a WAN, and WANs are administered by several different ISPs, and the links are usually slower than LAN connections. Next, we have a SAN, or a storage area network, and a SAN is a computer network which provides access to consolidated block-level data storage. SANs are primarily used to access data storage devices such as disk arrays and tape libraries from servers, so that the devices appear to the operating system as direct attached storage. A SAN typically is a dedicated network of storage devices that is not accessible through the LAN. And then we have a PAN, or a personal area network. So a PAN is a computer network for interconnecting electronic devices centered on an individual person's workspace. A PAN provides data transmission amongst devices such as computers, smartphones, tablets, and personal digital assistants. PANs can be used for communication amongst the personal devices themselves, or for connecting to a higher level network and the internet, where one master device takes up the role as a gateway. And examples of devices in a PAN are wireless headsets, keyboards, mice, printers, and barcode readers. A PAN may be wireless or carried over a wired interface such as a USB. Now it's time to do some of this outstanding check on learning. So the first question is, select the 4 correct network topologies. Is it A, bus star ring square? Is it B, mesh star ring bus? Is it C, star linear square and ring? Or is it D, ring bus star and LAN? So which one of these is the correct answer for the network topologies? And the correct answer is mesh, star, ring, and bus. Those are the 4 main network topologies. Next question, which answer is in the correct order from smallest to largest for network types? I know it says largest to smallest. I have a typo, but we're going from smallest to largest. So which of these is the correct answer? Is it LAN, CAN, MAN, WAN, CAN, MAN, WAN, PAN, PAN, LAN, CAN, MAN, or WLAN, WAN, LAN, and MAN? So which of these is going from smallest to largest? And the correct answer is it is PAN, LAN, CAN, and MAN. So personal area network, local area network, campus area network, and then metropolitan area network. That is going from smallest to largest. And the final question is, which is not true about a mesh topology? Is it A, it manages high amounts of traffic? Is it B, failure of one device does not cause a break in the network? Is it C, the cost to implement is higher than other topologies? Or is it D, adding additional devices will disrupt data transmissions between devices? So which of these is not true about a mesh topology? And the correct answer is Adding additional devices will disrupt data transmission between devices. That is not true. Adding additional devices will not disrupt data transmission between these devices. So in summary, we have talked about logical versus physical topologies. We've talked about star, ring, mesh, bus, ad hoc, and infrastructure topologies, LANs, wireless LANs, MANs, WANs, CANs, SANs, and PANs. In this video, you're going to learn about technologies that facilitate the Internet of Things or IoT technologies such as Z-Wave, ANT+, Bluetooth, NFC, infrared, RFID, and 802.11 Wi-Fi. So let's talk about Z-Wave. So Z-Wave, this is a wireless communications protocol used primarily for home automation. It is a mesh network using low energy radio waves to communicate from appliance to appliance, allowing for wireless control of residential appliances and other devices such as lighting control, security systems, thermostats, windows, locks, swimming pools, and garage door openers. Like other protocols and systems aimed at the home and automation market, a Z-Wave system can be controlled via the internet from a smartphone, tablet, or computer, and locally through a smart speaker, wireless key fob, or wall-mounted panel with a Z-Wave gateway or central control device serving as both the hub controller and portal to the outside. Z-Wave provides the application layer interoperability between home and control systems of different manufacturers that are a part of its alliance. Next we have is ANT+, and this is a wireless protocol for monitoring sensor data such as a person's heart rate or a car's tire pressure, as well as for controlling systems such as indoor lighting and television sets. ANT+ is designed and maintained by the ANT+ Alliance, which is owned by Garmin. Next we have Bluetooth, and this is a wireless technology standard used for exchanging data between fixed and mobile devices over short distances using short wavelength UHF or ultra high frequency radio waves in the industrial, scientific, and medical radio bands from 2.4 to 2.485 gigahertz, and it's also used for building personal area networks. And Bluetooth can be used to do the following. You can connect to wireless speakers, mice, keyboards, printers, and game controllers. You could transfer files between devices. You can control home security or automation devices, and you can integrate your smartphone with your car's audio or navigation system. And the process of connecting two Bluetooth devices to each other requires the following settings. So the first thing, the Bluetooth has to be enabled on both devices, but Bluetooth can be turned on or off on computers, tablets, and smartphones. The computer, smartphone, or tablet, they must be discoverable, and depending on the operating system and device, this option may be turned on automatically when you turn on Bluetooth, and then the device has to be paired. And there are 3 Bluetooth power classes, but most Bluetooth devices use class 2 radios, and there is a handy dandy little chart I've put together explaining the differences between class 1, class 2, and class 3 Bluetooth devices. Next, we're going to talk about NFC or near field communication. So NFC, this is a set of communication protocols that enable 2 electronic devices, one of which is usually a portable device, such as a smartphone, to establish communication by bringing them within 4 centimeters of each other. NFC enables smartphones to be used for payment services such as Apple Pay, Samsung Pay, and others. NFC also enables file transfer between supported devices, and to transfer files between smartphones with NFC, both smartphones must have NFC enabled and an NFC file transfer utility enabled, such as S-Beam for Samsung smartphones or Android Beam for Android smartphones. And once that is enabled, you can simply tap the phones together to transfer files. And also NFC can be used with compatible printers for tap to print capabilities. Next, we have infrared or infrared light, and this is an electromagnetic radiation with wavelengths longer than those of visible light. It is therefore generally invisible to the human eye, although infrared at wavelengths up to 150 nanometers from specially pulsed lasers can be seen by humans under certain conditions. If your smartphone can be used to control your TV, it has an infrared blaster on board, and normally this feature is designed for use with TV and home theater remote control apps. taps rather than data transfers. Next, we're talking about RFID, or radio frequency identification. So RFID uses electromagnetic fields to automatically identify and track tags attached to objects. An RFID tag consists of a tiny radio transponder, which is a radio receiver and a transmitter combination. When triggered by an electromagnetic interrogation pulse from a nearby RFID reader device, the tag transmits digital data, usually an identifying inventory number, back to the reader. And this can be used to inventory goods. And there are two types of RFID. The first one is a passive tag, and this is powered by energy from the RFID's reader interrogating radio waves. And then you have an active tag, and this is powered by a battery and thus can be read at a greater range from the RFID reader up to a few hundred meters. And examples of RFID technology are as follows. You have security badges that allow doors to be unlocked in a secure environment, giving access to some while denying access to others. Some items for sale have RFID tags used for identifying the item name and price. The badges on these items broadcast their information to a checkout reader, which could allow for the customer to simply walk out of the door and the items are counted, priced, and paid for by just simply walking past the reader. And then you have passports and other identification documents. They could also have RFID information embedded into them as well. So just think of an RFID chip dog collar to help you locate your missing dog. And next we're going to talk about 802.11 ABG, N, and AC Wi-Fi technology. So 802.11 and 802.11x, they refer to a family of specifications developed by the IEEE, or the Institute of Electrical and Electronics Engineers, for wireless local area network technology. 802.11 specifies an over-the-air interface between a wireless client and a base station, or between two wireless clients. These standards are commonly known as Wi-Fi or wireless Ethernet. Any Wi-Fi device contains a radio, and like an AM/FM radio, the radio in a Wi-Fi has a specific range of frequencies it can tune into. Some versions of Wi-Fi use a series of radio frequencies starting at 2.4 gigahertz, where others use a series of radio frequencies starting at 5 gigahertz. Some devices support both ranges of frequencies. Either range of frequencies are divided into 20 megahertz wide channels that can sometimes be grouped or bonded together into 40 megahertz wide or 80 megahertz wide combinations. Not all Wi-Fi devices can connect to any Wi-Fi device. The reality is that there are two wireless frequency bands used for Wi-Fi, as well as differences in the number and width of wireless carriers, differences in how signal interference is handled, and differences in security options. All of these factors must be taken into account, especially when you're adding wireless devices and network adapters to an existing network. And there are currently 5 Wi-Fi standards. So the first one is 802.11b, and that has a maximum speed of 11 megabits per second, operating in the 2.4 gigahertz frequency band with a maximum indoor range of 35 meters. You got 802.11a that has a maximum speed of 54 megabits per second, using 5 gigahertz frequency bands with a maximum indoor range of 35 meters. Next, you have 802.11g. It has a max speed of 54 megabits per second, operating in the 2.4 gigahertz frequency band with the maximum indoor range of 45 meters, and it is also backwards compatible with 802.11b. Next, you have 802.11n. This has a maximum speed of 150 megabits per second when using a single 20 megahertz channel, or it can run at up to 300 megabits per second with channel bonding, and it operates in the 2.4 gigahertz frequency by default, but it can also support 5 gigahertz frequencies as well. And 802.11n has a maximum indoor range of 70 meters, and it supports MIMO, MIMO, or multiple input, multiple output antennas to improve performance and range, although not all devices include multiple antennas. And then you have 802.11ac, and this uses only the 5 gigahertz band and supports up to 80 megahertz wide channels compared to 20 megahertz for 802.11b and G, and 40 megahertz for 802.11n using channel bonding. And it also supports multi-user MIMO, and the speed of 802.11ac is up to 433 megabits per stream when 80 megahertz wide channels are used. Now, to summarize all of that up, you can just refer to this handy dandy little chart that I have placed on your screen for your viewing pleasure. So in summary, we have talked about technologies that facilitate the Internet of Things or IoT technology. We talked about Z-Wave, ANT+, Bluetooth, NFC, infrared, radio frequency identification, and the 802.11 Wi-Fi family. In this video, you're going to learn about wireless technologies such as the 802.11 standards, cellular technologies, frequencies, channel bandwidth, channel bonding, MIMO and MU-MIMO, which I'll explain later on, unidirectional and omnidirectional antennas, and wireless site surveys. Let's talk about the 802.11 standard. So the first one we have is 802.11a, and it has a maximum speed of 54 megabits per second using the 5 gigahertz frequency band with a maximum indoor range of 35 meters. Then we have 802.11b that has a maximum speed of 11 megabits per second operating in the 2.4 gigahertz frequency band with a maximum indoor range of 35 meters. Then we have the 802.11G that has a maximum speed of 54 megabits per second, operating in the 2.4 gigahertz frequency band with a maximum indoor range of 45 meters, and it is backwards compatible with the 802.11b standard. Then we have the 802.11n standard. This has a maximum speed of 150 megabits per second when using a single 20 megahertz channel, or it can run up to 300 megabits per second with channel bonding or 40 megahertz channels. It operates in the 2.4 gigahertz frequency by default, but it can also support 5 gigahertz frequencies as well. 802.11n has a maximum indoor range of 70 meters. It supports MIMO, MIMO, or multiple input, multiple output antennas to improve performance and range, although not all devices include multiple antennas. And then we have the 802.11ac standard. This uses only the 5 gigahertz band and supports up to 80 megahertz wide channels compared to 20 megahertz for 802.11b and G and 40 megahertz for 802.11n using channel bonding. This also supports multi-user MIMO or multiple input, multiple output, and the speeds of the 802.11ac is up to 433 megabits per stream when 80 megahertz wide channels are used. Let's talk about some cellular technology. So the first one we're going to talk about is GSM. That stands for Global System for Mobile Communications. The GSM, this is a standard developed by the European Telecommunication Standards Institute to describe the protocols for second generation digital cellular networks used by mobile devices such as mobile phones and tablets. Its main task was to develop a single consistent network for all of Europe and come up with a better and more efficient technical solution for wireless communication. The GSM standard operates on 3 different carrier frequencies. The first one is the 900 megahertz band, which was used by the original GSM system. Then you have the 1800 megahertz band, which was added to support the swelling number of subscribers, and the 1900 megahertz frequency, which is used mainly in the US. And one of the main advantages of the GSM standard is the ability to roam and switch carriers by using individual mobile units if partner units are located in their destination. Next, we have TDMA, or Time Division Multiple Access. So TDMA, this is a channel access method for shared medium networks. It allows several users to share the same frequency channel by dividing the signal into different time slots. The users transmit in rapid succession, one after the other, each using its own time slot. This allows multiple stations to share the same transmission media, such as a radio frequency channel, while using only a part of its channel capacity. TDMA is used in most 2G cellular systems, while 3G systems are based on what is called CDMA, or Code Division Multiple Access. And speaking of CDMA, that stands for Code Division Multiple Access, and this is a digital cellular network standard that utilizes spread spectrum technology. This technology does not constrict bandwidths, digital signals, or frequencies, but spreads it over a fully available spectrum or across multiple channels via division. Thus, there is improved voice and data communication capabilities and more secure and private lines. Essentially, CDMA offers more airspace capacity than TDMA based on the GSM standard. Furthermore, CDMA, it uses less power. The CDMA digital standard, this is a leading communications network standard in North America and parts of Asia. Next, let's talk about frequencies. So your wireless router uses radio frequencies to transmit internet to your Wi-Fi connected devices like smartphones, laptops, tablets, etc. The differences between 2.4 gigahertz and 5 gigahertz frequencies comes down to two factors: bandwidth or speed and its range. A 2.4 gigahertz connection travels farther at lower speeds, while 5 gigahertz frequencies provide faster speeds at a shorter range. Whether you choose 2.4 gigahertz or 5 gigahertz will depend on where and how you use your Wi-Fi connection. A lot of electronic devices and appliances, they use the 2.4 gigahertz frequency, including microwave ovens, baby monitors, and garage door openers. If you have many of these in your home, or you live in an apartment or a condo surrounded by other people that use the 2.4 gigahertz frequency band, you are likely to experience congestion on the network, which can potentially damage the speed and signal quality that you are trying to get access to. So now let's talk about the 2.4 gigahertz frequency real quick. So some of the pros associated with 2.4 gigahertz are as follows: it has a larger coverage area and it is better at penetrating solid objects. Some of the cons: it has a lower data rate, it's more prone to interference, and usually you'll find a lot of devices that use this frequency. It has a maximum connection speed of approximately 150 megabits per second, and it has a maximum signal range from the router of approximately 410 feet. Also, you'll notice with the 2.4 gigahertz frequency, it has a total of 11 channels, with 3 of the channels that are not overlapping. That'll be channels 1, 6, and 11. So if you are operating on the 2.4 gigahertz frequency with your wireless router and you want the best connection possible, I highly advise you to set your channels to either channels 1, 6, or 11. Those are the only 3 channels that do not overlap with each other, which will drastically minimize your chances of dealing with interference. Let's talk about 5 gigahertz. So some of the pros associated with 5 gigahertz are: it has a higher data rate, it is less prone to interference, and usually there are fewer devices that use this frequency. Some of the cons are: it has a smaller coverage area and it is worse at penetrating solid objects. Its maximum connection speed is approximately 1 gigabit per second, and it has a maximum signal range from the router of approximately 410 feet when the signal is amplified. Let's talk about channel bandwidth. So bandwidth, this is a broad term defined as the bit rate measure of the transmission capacity over a network communication system. Bandwidth is also described as the carrying capacity of a channel or the data transfer speed of that channel. However, broadly defined, bandwidth is the capacity of a network, and bandwidth, this exists in physical or wireless communication networks. Let's talk about channel bonding, which is also known as Ethernet bonding or NIC bonding, network interface card bonding. And this is when a cable modem combines multiple channels to increase the amount of traffic that it can comfortably support. Channel bonding is a practice commonly used in 802.11 implementations in which 2 adjacent channels within a given frequency band are combined to increase throughput between 2 or more wireless devices. Let's talk about MIMO, or multiple input and multiple output. So MIMO, this is a method for multiplying the capacity of a radio link when using multiple transmission and receiving antennas to exploit multipath propagation. MIMO has become an essential element of wireless communication standards such as 802.11n and 802.11ac. Some smartphones and tablets simply use the term MIMO if they support 2 or more 802.11n and AC streams, and MIMO devices are available in the following configurations. You have a 1x1 where you have 1 transmit and 1 receive antenna. You have a 2x2 where you have 2 transmit and 2 receive antennas. You have a 2x3 configuration where you have 2 transmit and 3 receive antennas. Then you got 3x2, you have 3 transmit and 2 receive antennas. And then you got a 3x3, we have 3 transmit and 3 receive antennas. Now, the number of transmit antennas typically correspond to the number of data streams, also known as spatial streams, that the device can support. So in the case of a router that supports both 2.4 gigahertz and 5 gigahertz signals, the specifications include this information for each band. Devices that have different numbers of receiving antennas and sending antennas may be identified by the number of data streams it can send and receive. So for example, a device with a 2x3 antenna configuration can also be identified as having a 2x3:2 configuration, and that would stand for it has 2 send antennas, 3 receive antennas, and a send and receive support for 2 data streams. Multi-user, multiple input, and multiple output are multi-user MIMO. So multi-user MIMO, this allows a Wi-Fi router to communicate with multiple devices simultaneously. This decreases the time each device has to wait for a signal and dramatically speeds up your network, considering that the average household has upwards of 8 devices battling for bandwidth simultaneously. Multi-user MIMO will increasingly improve a household's Wi-Fi experience, especially when it comes to streaming and gaming. Next, let's talk about unidirectional and omnidirectional antennas. So unidirectional antennas focus radio frequency energy in 1 or 2 directions, which lowers the beam width and overall area covered, but increases the strength of the signal and distance covered in that direction. An omnidirectional antenna is able to radiate or receive equally well in all directions. From the locus, the signal is emitted in the 360-degree plane to cover a certain area. Because the signal is not focused, the distance that it reaches is generally small relative to that of a unidirectional antenna, and typical applications of these antennas include hotspots for Wi-Fi, either indoors or outdoors, where multipath environments exist. And let's talk about a wireless site survey. So a wireless site survey, this is the process of planning and designing wireless networks to provide a wireless solution that will deliver the required wireless coverage, data rates, network capacity, roaming capability, and quality of service. The survey usually involves a site visit to test for radio frequency interference and to identify optimum installation locations for access points. This requires analysis of building floor plans, inspection of the facility, and use of site survey tools. Also, feedback from IT managers and end users of the wireless network are also important in determining the design parameters for the wireless network. All right, so that is my class. Now let's go ahead and do some of this outstanding check on learning. So which 2 answers refer to characteristics of the 802.11a wireless standard? Would it be A, it has a maximum data rate of 54 megabits per second? B, would it be 5 gigahertz frequency bands? C, would it be 2.4 gigahertz frequency bands? Or would it be D, it has a maximum data rate of 11 megabits per second? So which of these 2 answers are correct as it relates to the 802.11a wireless standard? And the correct answers would be it has a maximum data rate of 54 megabits per second, and it also operates on the 5 gigahertz frequency band. That is for the 802.11a wireless standard. Next question. Which of the following refers to a channel access method used in 2G GSM networks? Would it be A, CSMA-CA, B, TDMA, C, CSMA-CD, or D, CDMA? So which of the following refers to a channel access method used in 2G GSM networks? And the correct answer is TDMA, or time division multiple access. Now, for those of you listening to my voice right now, I highly encourage you all to get familiar with these acronyms, because when you go sit down to take your exams, they are going to be loaded up with acronyms, and they are going to expect you to understand what each acronym means as it directly relates to the question that they are asking you. Next question. What 2 are the frequency bands used by 802.11 networks? So which 2 answers are correct? Would it be 5 gigahertz, 5.4 gigahertz, 2 gigahertz, or 2.4 gigahertz? So which of these 2 answers is correct in reference to 802.11 networks? And the correct answer is, for 802.11 networks, they use 5 gigahertz and 2.4 gigahertz frequencies. That is the correct answer, ladies and gentlemen. All right, so in summary, we have talked about wireless technologies such as the 802.11 standards, cellular technologies, frequencies, channel bandwidth, channel bonding, MIMO, multi-user MIMO, unidirectional and omnidirectional antennas, and wireless site surveys. In this video, you're going to learn about cloud computing concepts such as the types of cloud services, cloud delivery models, shared resources, rapid elasticity, on-demand self-service, resource pooling, measured services, metered services, off-site email applications, cloud file storage services, virtual application streaming and cloud-based applications, virtual desktops, and virtual NICs. All right, let's talk about the types of cloud services. So cloud computing, this is the on-demand availability of computer system resources, especially data storage, also known as cloud storage, and computing power without direct active management by the user. The term is generally used to describe data centers available to many users over the internet, and cloud computing comes in three main models. You have software as a service, platform as a service, and infrastructure as a service. Let's talk about software as a service. So software as a service, this is a software licensing and delivery model in which software is licensed on a subscription basis and is centrally hosted. Software as a service applications are also known as web-based software, on-demand software, and hosted software. Because software as a service processing is performed at the server, a thin client smartphone or tablet is sufficient to run the software. A browser-based service that does not require a user to download application code to use the service is an example of software as a service. And software as a service allows organizations to get quickly up and running without having to develop or deploy an application. And some examples of software as a service applications are, you have Gmail, which provides access to email services via Google. You have Google Drive that provides access to word processing, spreadsheets, presentations, and various other forms. You have Microsoft Office 365 that provides access to word processing, spreadsheets, presentations, calendars, emails, etc. And then you have something like Salesforce, which is a customer relationship management application. Next, we have platform as a service. So platform as a service, this is a category of cloud computing services that provides a platform allowing customers to develop, run, and manage applications without the complexity of building and maintaining the infrastructure typically associated with developing and launching an app. A developer using platform as a service can concentrate on software features instead of possible issues with server hardware and operating systems. And some of the major platform as a service vendors include Oracle Cloud, Google Cloud Platform, Microsoft Azure, and Salesforce Platform. Next, we have infrastructure as a service, and this is also known as cloud infrastructure services. And this is a form of cloud computing in which IT infrastructure is provided to end users through the internet. Infrastructure as a service is commonly associated with serverless computing. The infrastructure as a service vendor provides the virtualization, storage, network, servers, and allows for customers to utilize or pay for virtual resources when they are needed. This cloud computing model allows for customers to not have to have an on-premise data center and not worry about physically updating or maintaining these components themselves. Most importantly, this model allows for companies to reduce their costs of their network infrastructure by outsourcing storage and computing services to a cloud provider. Infrastructure as a service puts the user in charge of all the software used in a project, from applications and data to the operating system. Infrastructure as a service vendors supply the hardware and network support tools, and the three largest cloud providers at the time of this recording are Amazon Web Services, also known as AWS, Microsoft Azure, and IBM. And here is a handy dandy little chart showing you the cloud computing models and their separations of responsibilities, everything from on-premise to infrastructure as a service, platform as a service, and software as a service. Now, if you are still confused about how cloud computing services work, you can use this analogy known as pizza as a service, and hopefully this will make things make sense for you. So the made at home, that will be your on-premise. Then you have the take and bake, that will function as your infrastructure as a service. If you're having pizza delivered to your house, that'll be platform as a service. Or if you have dined out, that will be your software as a service. And everything in green is the things that the vendor of your pizza manages manages, and everything in blue is everything that you manage. So hopefully this will help you guys understand the differences between the various cloud platform services. Next, let's talk about cloud delivery models. So we have private cloud, public cloud, hybrid, and community clouds. So you have a private cloud. This is defined as computing services offered over the internet or a private internal network and only to select users instead of the general public. And private cloud computing is considered to be more secure than public cloud computing. Next, we have the public cloud, and this is defined as computing services offered by third-party providers over the public internet, making them available to anyone who wants to use or purchase them. They may be free or sold on demand, allowing customers to pay only per usage for the CPU cycle, storage, or bandwidth they consume. Then we have the hybrid cloud model, and this is a computing environment that combines public cloud and a private cloud by allowing data and applications to be shared between them. When computing and processing demand fluctuates, hybrid cloud computing gives organizations the ability to seamlessly scale their on-premise infrastructure up to the public cloud to handle any overflow without giving third-party data centers access to the entirety of their data. And then we have a community cloud. And this is a collaborative effort in which infrastructure is shared between several organizations from a specific community with common concerns such as security, compliance, jurisdiction, etc., whether managed internally or by a third party and hosted internally or externally. This is controlled and used by a group of organizations that have shared interests. The costs are spread over fewer users than a public cloud, but more than a private cloud. So only some of the cost savings potential of cloud computing are actually realized. Next, we have shared resources. So in computing, a shared resource is a computer resource made available from one host to other hosts on the computer network. It is a device or piece of information on the computer that can be remotely accessed from another computer transparently as if it were a resource in the local machine. Sharing equipment or data on a network to save costs is the overall reason to implement cloud computing. And there are two main ways to share devices and data over the internet. You can do it by way of an internal cloud or an external cloud. Let's talk about an internal cloud. This is also known as a corporate cloud, and this is a cloud computing service that is implemented within an organization's dedicated resources and infrastructure. Internal clouds apply virtualization mechanisms, shared storage, and network resources to facilitate full control of an organization's cloud computing environment. With an internal cloud, the company gets the virtualization services and flexibility of a commercial cloud, but with the security and reliability that comes from existing within the company's network infrastructure. The costs often associated with an internal cloud typically are higher than utilizing a commercial cloud provider, but there are still reduced costs associated with sharing resources internally. Then we have an external cloud, and this is a cloud solution that exists outside of an organization's physical boundaries. It can be private, public, or community-based as long as it is not located on an organization's property. An external cloud would involve the sourcing of any cloud solution that's available and can be used along with an internal cloud infrastructure or an internal cloud solution for any business need. The services delivered through this kind of setup matches the services offered by a private cloud. However, the primary difference is that all physical resources are essentially external to the organization. Next, we have this concept called rapid elasticity, and this is a cloud computing term for scaling, provisioning, or the ability to provide scalable services. Rapid elasticity allows users to automatically request additional space in the cloud or other types of services. Because of the setup of cloud computing services, provisioning can be seamless for the client or user. In a sense, cloud computing resources appear to be infinite or automatically available. That's very different from older systems where the limits of storage or memory were immediately visible to a user. Next, we have on-demand computing, and this is also known as on-demand self-service. And this is a business computing model in which computing resources are made available to the user on an as-needed basis. Rather than all at once, on-demand computing allows cloud hosting companies to provide their clients with access to computing resources as they become necessary. Gmail is an example of an on-demand self-service where users can access their email online from virtually any device that connects to the internet anytime that they want. Next, we have resource pooling, and this is an IT term used in cloud computing environments to describe a situation in which providers serve multiple clients, customers, or tenants with provisional and scalable services. These services can be adjusted to suit each client's needs without any changes being apparent to the client or end user. Let's talk about measured service, and this refers to how cloud services are monitored for quality and effectiveness. Measuring service metrics can help drive decisions about what services to adopt and how to calculate pricing of those services. Then we have metered services. So measured service is a term that applies to cloud computing, which is a reference to services where the cloud provider measures or monitors the provisions of service for various reasons, including billing, effective use of resources, or overall predictive planning. Cloud computing services are typically calculated on an hourly basis. Outsourcing by the hour could result in huge savings for customers. And this feature is what has driven the high growth of cloud services. So the main difference between measured services and metered services, you could think of metered services as your power bill or your water bill that gets sent to your house that shows you how much resources you have actually used, which translates into why your bill is extremely high. Measured services is kind of almost similar to thinking of a company asking to get some type of feedback in response to the product or service that they're putting out so that they can make necessary changes and adjustments in order to hopefully provide a better customer experience. So that's the main difference between measured service and metered services. Then we have off-site email applications, and these allow for organizations to pay other companies like Google to manage all the company's email in addition to managing the enormous amounts of data generated by all of this email. Google Workspace, which is formerly known as G Suite, this is an example of an off-site email application where organizations can pay Google a monthly subscription fee to essentially get an enhanced version of Google Drive and Gmail. The alternative to off-site email is an on-site email, which is also known as on-premise, which means that an organization is essentially responsible for all the costs associated with purchasing, powering, and maintaining the server equipment, and the company's LAN provides access to the on-site email applications. Then we have cloud file storage services. So this is a method for storing data in the cloud that provides servers and applications access to data through shared file systems. Cloud file storage services utilize cloud-based synchronization where apps on a mobile device send data to the cloud, which can then be downloaded by other mobile apps, web browsers, or by programs running on Windows or Mac. And examples of cloud file storage services are Google Drive, Dropbox, Apple iCloud, and Microsoft OneDrive. Next, we have virtual application streaming, cloud-based applications. So virtual application streaming refers to an on-demand software delivery model that works based on the fact that the majority of applications need just a small portion of their total programming code for operation. The applications are stored and run in the cloud and delivered to the user on almost any device, such as smartphones, tablets, laptops, and desktops. This indicates that there is no need to fully install a program on a client machine. However, portions of it could be offered across the network whenever required. To implement virtual application streaming, a user purchases a license and downloads a small app that identifies the user. The application is presented to the user as if it were locally installed, but only the essentials are brought down to the device. Adobe Creative Cloud is an example of a virtual application, which is also known as software as a service cloud-based application that allows users to utilize apps like Adobe Photoshop without actually installing the program locally to their computer. Next, we have a virtual desktop. So virtual desktop infrastructure, also known as VDI. This is defined as the hosting of desktop environments on a central server or the cloud. It is a form of desktop virtualization as these specific desktop images run within a virtual machine and are delivered to end clients over a network. Those endpoints may be PCs or other devices like tablets or thin client terminals in which the mouse and keyboard inputs are sent across the internet. And then we have a virtual NIC. So a virtual network interface card. This is an abstract virtualized representation of a computer network interface that may or may not correspond directly to a network interface controller. Virtual NICs within a virtual machine behave identical to that of a physical NIC in that it needs a physical MAC address and IP address in order to communicate with other machines. The only real difference between a virtual NIC and a physical NIC is that an administrator can assign specific MAC addresses to a virtual NIC by way of a virtual machine manager, whereas a physical NIC, the MAC address is assigned by the manufacturer. If an admin wants the virtual machine to communicate with other machines, they can create a path or a bridge between the virtual NIC and the physical NIC on the virtual machine manager hardware, and this allows the virtual machine to communicate like any other machine within the LAN. All right, now let's get into some of this outstanding check on learning, shall we? So the first question is, a cloud computing service model offering remote access to applications based on a monthly or annual subscription fee is called what? Is this platform as a service, software as a service, infrastructure as a service, or data as a service? So which of these comes with a monthly or annual subscription fee? And the correct answer is, that would be software as a service. Next question. In cloud computing, the practice of grouping together computing resources and making them available for shared access for multiple consumers is referred to as what? Broad network access, measured service, on-demand self-service, or resource pooling. So the practice of grouping together computer resources and making them available for shared access for multiple consumers is known as, this would be resource pooling. Next question. Which of the following cloud service types would be the best option for a web developer intending to create an app? Would it be data as a service, software as a service, platform as a service, or infrastructure as a service? So which of these will be the best option for a web developer who is looking to create an app? And the correct answer is, it will be a platform as a service. Why? Because the web developer doesn't have to worry about maintaining and upgrading the actual infrastructure. All he or she would have to do is just essentially log in and get busy creating an app and let their hosting company worry about maintaining everything else. So in summary, we have talked about cloud computing concepts such as everything listed on your screen in front of your eyes. In this video, you're going to learn about network services such as DNS services, DHCP services, NTP, and IPAM, also known as IP address management. Let's talk about the DNS. That stands for Domain Name System. So the DNS, this is a hierarchical and decentralized naming system for computers, services, or other resources connected to the internet or a private network. It associates various information with domain names assigned to each of the participating entities. Most prominently, it translates more readily memorized domain names to the numerical IP addresses needed for locating and identifying computer services and devices with the underlying network protocols. So in layman's terms, the DNS is essentially the phone book of the internet. Instead of memorizing a bunch of IP addresses to get to a certain website, DNS associates names to those IP addresses. And an example of this would be the IP address of 172.67.147.245. That is the IP address associated with my website, technologyg.com. If you type the IP address into the URL or the Uniform Resource Locator, it will take you straight to Technology G. Now, as a word of caution, my website is behind what is called a Content Delivery Network, or a CDN. So if you try to access my website directly by the IP address, it is going to present you an error stating direct IP access is not allowed. So you can only access my website by typing in the name technologyg.com. Let's talk about DNS records. So DNS records, also known as zone files, these are instructions that live in authoritative DNS servers and provide information about a domain, including what IP address is associated with that domain and how to handle requests for that domain. These records consist of a series of text files written in what is known as DNS syntax, and DNS syntax is essentially a string of characters used as commands that tell the DNS server what to do. You can think of a set of DNS records like a business listing on Yelp. The listing will give information about the business, such as the business's location, hours, services offered, etc. All domains are required to have at least a few essential DNS records for users to be able to access their website using a domain name. And there are several optional records that serve additional purposes. Let's talk about some of the most common DNS records. So the first one we have is the A record, and the A stands for address. And this record holds the IP address of a domain name. So an example would be the A record for the IP address of technologyg.com is 172.67.147.245. Then we have the AAAA record. So just the single A records, they only hold IP version 4 addresses, but IP version 6 addresses, they store the AAA records. Next, we have the TXT record, or the text record, and this lets a domain administrator store text notes in the record in the DNS. The TXT record was originally intended for human readable notes. However, it is possible to put machine readable data into a TXT record. And then you have the SPF, or the Sender Policy Framework. This is a type of TXT record in a DNS zone file. SPF records identify which mail servers are permitted to send email on behalf of your domain, and SPF records can help detect and prevent spammers from sending email messages with forged from addresses on your domain. And then the next type of TXT record is the DKIM, or the Domain Keys Identified Mail record. And this is an authentication standard used to prevent email spoofing. The DKIM, or the DKIM record, attempts to prevent the spoofing of a domain that's used to deliver email. Then we have the SERV, or the SRV, or the service record. This specifies a host and port for specific services such as voice over IP, instant messaging, etc. Most other DNS records only specify a server or an IP address, but the service records include a port at the IP address as well. And some internet protocols require the use of the SRV records in order to properly function. And then we have the MX, or the mail exchange record, and this directs email to a mail server, and the MX record indicates how email messages should be routed in accordance with SMTP, or Simple Mail Transfer Protocol, which is the standard for all email. Then we have the CNAME record, or the canonical name, and this is used in lieu of an A record when a domain or subdomain is an alias for another domain. And all CNAME records must point to a domain, and they can never point to an IP address. So an example of this would be, suppose you have the site blog.website.com, and that has a CNAME record with the value of website.com. This means when a DNS server hits the DNS records for blog.website.com, it actually triggers another DNS lookup to go find website.com, returning website.com's IP address via its A record. And then in this case, blog.website.com, that will be the CNAME, or the true name of blog.website.com. And then we have an NS record, or a name server record. This indicates which DNS server is authoritative for that domain, or essentially which server contains the actual DNS records. NS records tell the internet where to go to find out a domain's IP address. A domain often has multiple NS records, which can indicate primary and backup name servers for that domain. Without properly configured NS records, users will be unable to load a website or application. And as a side note, NS records, they can never point to a CNAME record. Then we have the pointer record, or the PTR, and this provides the domain names associated with an IP address. A pointer record is exactly the opposite of the A record, which provides the IP address associated with the domain name. Pointer records are used in reverse DNS lookups. So when a user attempts to reach a domain name in the browser, a DNS lookup occurs matching the domain name to the IP address. A reverse DNS lookup is the opposite of this process. It is a query that starts with the IP address and then looks up the domain name. Let's talk about cloud-hosted DNS. So cloud-hosted DNS is a high-performance, resilient, global DNS service that publishes your domain names to the global DNS in a cost-effective way. Cloud-hosted DNS lets you publish DNS zones and records without the burden of managing your own DNS servers and software. Then we have a DNS hierarchy, or the DNS root domain. So DNS, it uses a hierarchy to manage its distributed database system. The DNS hierarchy, or the domain namespace, is an inverted tree structure. The DNS tree has a single domain at the top of the structure called the root domain. A period or a dot is the designation for the root domain. Below the root domain are the top level domains that divide the DNS hierarchy into segments. Then we have domains and subdomains. So a domain is a label of the DNS tree. Each node of the DNS tree represents a domain. Domains under the top level domains represent individual organizations or entities. These domains can be further divided into subdomains to ease administration of an organization's host computers. And then a domain in a subtree, this is considered part of all domains above it. So for example, in this picture below, you have chicago.companyaa.com. This is a part of the company.com domain, and both are part of the .com domain. Next we have is DNS zones. So the DNS is broken up into many different zones. These zones differentiate between distinctly managed areas in the DNS namespace. A DNS zone is a portion of the DNS namespace that is managed by a specific organization or administrator. A DNS zone is an administrative space which allows for more granular control of DNS components, such as authoritative name servers. The domain namespace is a hierarchical tree with the DNS root domain at the top. A DNS zone starts at a domain within the tree and can also extend down into subdomains so that multiple subdomains can be managed by one entity. Next, we have forward versus reverse zones. So DNS zones contain the records for the mapping of domain names to IP addresses or other information. The resolution of a domain name to its assigned information is also referred to as a forward resolution, and the DNS zones associated with such processes are often referred to as forward zones. Reverse zones, which are used for the reverse process, they find the DNS name that is associated with an IP address. Let's talk about the DHCP, or the Dynamic Host Configuration Protocol. So the DHCP, this is a network management protocol used on IP networks whereby a DHCP server dynamically assigns an IP address and other network configuration parameters to each device, such as PCs, printers, servers, routers, etc., on a network so they can communicate with other IP networks. A DHCP server enables computers to request IP addresses and networking parameters automatically from the ISP, reducing the need for a network administrator or a user to manually assign IP addresses to all network devices. In the absence of a DHCP server, a computer or other device on the network needs to be manually assigned an IP address or to assign itself what is called an APIPA address, the latter of which will not enable it to communicate outside of its local network. If you get your address from a DHCP server, you are getting your address assigned dynamically, and it could change periodically. So let's talk about some DHCP services. And the first one we're going to talk about is MAC reservation. So some devices on the network require static addresses that do not change, such as printers, servers, which have to be assigned manually by a network administrator. This enables these devices to be more reliable and easily accessible over time. A MAC reservation, or a media access control reservation, is when a DHCP server maps a specific MAC address to a specific IP address that will not be assigned to any other device within a network. This static addressing approach is referred to as a DHCP reservation. Next, let's talk about pools. So a DHCP pool is when a DHCP server maintains a pool of IP addresses and leases an address to any DHCP-enabled client when it starts up on the network. Because the IP addresses are dynamic or leased rather than static, meaning they're permanently assigned, addresses no longer in use are automatically returned to the pool for reallocation. Next, we have IP exclusion. So a DHCP IP exclusion, this is a specified range of IP addresses residing within a DHCP range. IP addresses residing within the exclusion range are excluded from the pool of available IP addresses and are unleasable. The DHCP server is prevented from assigning IP addresses within the exclusion range to network devices. Next we have is lease time. So a DHCP assigned IP address is not permanent and they typically expire in about 24 hours. This is what's referred to as a DHCP lease time. Unless modified from default settings, DHCP servers assume that your IP address is temporary and expires after a set amount of time. This practice can be extremely beneficial as IP addresses become available for other devices to use when needed, and this creates a more streamlined system and makes staying organized a lot easier. Next, we have DHCP relay. So the DHCP relay agent operates as the interface between DHCP clients and the server. The DHCP relay agent relays DHCP messages between DHCP clients and DHCP servers on different IP networks. Let's talk about NTP, or Network Time Protocol. So the Network Time Protocol, this is a networking protocol for clock synchronization between computer systems over packet switch variable latency data networks. NTP is intended to synchronize all participating computers to within a few milliseconds of coordinated universal time. It uses the intersection algorithm to select accurate time servers and is designed to mitigate the effects of variable network latency. NTP can usually maintain a time to within tens of milliseconds over the public internet and can achieve better than 1 millisecond accuracy in local area networks under ideal conditions. Asymmetric routes and network congestion can cause errors of 100 milliseconds or more. The protocol is usually described in terms of a client-server model, but can as easily be used in peer-to-peer relationships where both peers consider the other to be a potential time source. NTP supplies a warning of any impeding leap second adjustment, but no information about local time zones or daylight savings time is transmitted. And then we have IPAM, or IP address management. So IPAM, this is a methodology implemented in computer software for planning and managing the assignment and use of IP addresses and closely related resources of a computer network. It does not typically provide DNS and DHCP services, but manages information for these components. Additional functionalities such as controlling reservations in DHCP and other data aggregation and reporting capabilities is also common. Data tracked by the IPAM system may include information such as IP addresses in use and the associated devices and their users. IPAM tools are increasingly important as new IP version 6 networks are deployed with large address pools of 128-bit hexadecimal numbers, and new subnetting techniques are implemented. All right, so that was my class. Now let's do some of this outstanding check on learning. So, which DNS record is used in lieu of an A record when a domain or subdomain is an alias for another domain? Is it the MX record, the AAA record, the DKIM record, or the CNAME record? And the correct answer is, this would be the CNAME record, or the canonical name record. Next question. What is a hierarchy used to manage a distributed database system? Is it a cloud-hosted DNS, a DNS root domain, DNS zone, or a subdomain? So what is a hierarchy used to manage a distributed database system? The correct answer is, this will be a DNS root domain. Next question. Which DHCP service allows for an IP address to be assigned to a certain network device? Is this pools, IP exclusions, MAC reservations, or NTP? So which one of these will allow for an IP address to be assigned to a specific network device? And the correct answer is, this will be a MAC reservation, or a media access control reservation. All right, so in summary, we have talked about network services such as DNS services, DHCP services, NTP, and IPAM or IP address management. In this video, you're going to learn about various networking cables, plenum versus PVC, and networking cable connector types. All right, let's talk about some media types. And the first one is copper. So we have what is called shielded twisted pair and unshielded twisted pair. So twisted pair cabling, this is a type of wiring in which two conductors of a single circuit are twisted together for the purposes of improving electromagnetic compatibility. Twisted pair cabling is the most common of the major cabling types. Twisted pair cabling typically consists of 4 twisted pairs of wires surrounded by a flexible jacket, also known as untwisted pair cabling, or various types of metal foil or braid known as shielded twisted pair. Shielded twisted pair and unshielded twisted pair use the same RJ45 connector, but shielded twisted pair includes a metal shield for electrical insulation between the wires and the outer jacket. Shielded twisted pair is also stiffer and more durable, yet more expensive and harder to loop through tight spaces than unshielded twisted pair. It is used where electromagnetic interference prevents the use of untwisted pair cable, and both cables can be purchased in pre-built assemblies or can be built using bulk cables and connectors. Next, we have coaxial, and with that, we have the RG6 and the RG59 coaxial cable. So coaxial cable, this is the oldest type of networking cable. Its data wires are surrounded by a wire mesh for insulation, and prior to the advent of fiber optics, the fastest internet service available to home and business customers was cable internet. And cable internet, this is a form of broadband internet access, which uses the same RG6 coaxial cable as a cable television, but adds a device called a cable modem to convert the signal for use by computers in home and business networks. RG6 has a 75 ohm resistance and uses an 18 gauge center conductor and is available in quad shielded versions, and it can carry signals up to 1.5 gigahertz, making it much better for HD TV signals. And then we got the RG59, and this is used in older cable TV or satellite TV installations, as well as in closed circuit television security installations. It has a 75 ohm resistance. RG59 uses a 22 gauge center conductor and a single outer shield, and it is designed for signals up to 50 megahertz. Next, we have fiber. So fiber optics, this is the technology that uses glass or plastic threads to transmit data. A fiber optic cable consists of a bundle of glass threads, each of which is capable of transmitting messages modulated onto light waves. And fiber optics is the fastest type of internet service, which is primarily used as a backbone between networks. In fiber optic cabling, it comes in 2 major types. You have single mode and multi-mode. So single mode fiber, it has a thin core between 8 to 10 microns and is designed to carry a single light ray long distances up to 60 kilometers or further. And single mode cable uses a laser diode as a light source, and the typical uses include cable TV and telephone companies. And then you have multi-mode fiber, and this has a thicker core of 62.5 microns, and it carries multiple light rays for short distances up to 10 kilometers. And multi-mode fiber uses an LED light source, and typical uses include local and metropolitan area networks. Next, we have plenum versus PVC. So there are 2 categories of twisted pair cabling in terms of their fire rating. The first one is standard, and this is suitable for patch cables between network interface cards and a network jack or in a patch panel. And typically PVC jackets can create a lot of smoke when they are burned. And then you have plenum, and this is designed for use in plenum space, which is a part of a building that can facilitate air circulation for heating and cooling, such as ventilator shafts or under the floors or between suspended ceilings and the permanent ceilings. And plenum cables, they produce less smoke and lower levels of toxic chemicals when burned, and they are also commonly self-extinguishing. And plenum cables may be made from Teflon or from a modified version of PVC that produces less smoke when burned than a standard PVC cable. All right, let's talk about connector types. And the first one we're going to talk about is RJ45. So the RJ45 connector, this is an 8-pin connection used for Ethernet network adapters. The connector resembles the RJ11 connector, which is used with telephones in the United States. And this connector most commonly connects to the end of a Cat5 cable, which connects between a computer network card and a network device, such as a network router. And then we have the RJ11, and this is the telephone interface that uses a cable of twisted wire pairs and a modular jack with 2, 4, or 6 contacts. And RJ11 is the most common connector for plugging a telephone into the wall and the handset into the telephone. Next, we have the BNC connector, or the Bayonet Neo Consolement connector. And this is a miniature quick connect disconnect radio frequency connector used for coaxial cable. After the BNC connector is inserted, it is turned, causing pins in the socket to be pinched into a locking groove on the plug. And then we have the DB9 connector, and this is a 9-pin serial connector, once common on PCs that was used for connecting peripherals like mice and keyboards. The DB9 connector can also be used for serial communications to networking equipment and can be used with DB9 to USB adapters to connect to modern PCs without DB9 ports. Then we have the DB25 connector, and this is an analog socket with 25 pins from the D Subminiatures connector family. And the DB25 connector is mainly used in serial and parallel ports, allowing for asynchronous data transmissions. Then we have the F connector, and this is a coaxial radio frequency connector used for over-the-air terrestrial television, cable television, and universally for satellite television and cable modems. The F connector can be crimped or attached via compression to the coaxial cable. In high-quality cables, they use a threaded connector. And then we have fiber. So fiber optic devices and cables, they use one of the several connector types. You have the LC connector that uses a square connector. You got the ST that uses a round connector, and then you got the SC that uses a square connector. And then you have the MTRJ connector, and this is very popular for use in small form factor devices due to its small size. All right, so in summary, we have talked about various networking cables, plenum versus PVC, and networking cable connector types. In this video, you're going to learn about various fiber optic transceivers and various cabling termination points. Let's talk about a transceiver. So a transceiver, this is an electronic device which is a combination of a transmitter and a receiver, hence the name. It can both transmit and receive digital signals for communication purposes. These two related functions are often combined in a single device to reduce manufacturing costs. Let's talk about a fiber transceiver. So a fiber transceiver, this is a single package device that uses fiber optic technology to transmit and receive data. The fiber optic transceiver comprises of both a transmitter and a receiver, which are combined and share circuitry or a single housing. It is an important part of an optical network equipment that has electronic components to condition and encode and decode data into light pulses and then sends them to the other end as electrical signals. And the first type we have is called bidirectional or BIDI, and this usually consists of 2 different wavelengths to achieve transmission in both directions on just one fiber, whether it's single mode or multi-mode. In a bidirectional transceiver, it enables the signal to be sent and received in both directions by different center wavelengths. And then the next one we have is duplex. A duplex fiber cable consists of 2 strands of glass or plastic fiber, typically found in a zip cord construction format. This cable is most often used for complex communication between devices where separate transmit and receive are required. Next, we have an SFP, or a small form factor pluggable. The SFP, this is a compact, hot pluggable network interface module used for both telecommunication and data communication applications. An SFP interface on networking hardware. This is a modular slot for a media-specific transceiver in order to connect a fiber optic cable or sometimes a copper cable. The advantage of using SFPs compared to fixed interfaces such as modular connectors and Ethernet switches is that the individual ports can be equipped with any suitable type of transceiver as needed. Next, we have a GBIC or gigabit interface converter. A GBIC, this is a standard hot swappable electrical interface, single gigabit port that can support a wide range of physical media from copper to long wave single mode optical fiber at lengths of hundreds of kilometers. Then we have SFP Plus or Enhanced Small Form Factor Pluggable. The SFP Plus takes the benefit of the SFP design and improves on their data capacity. SFP Plus still functions with copper and optical cabling, but it can achieve much higher speeds. Data rates at 10 gigabits per second, and on the newer fiber channel design, SFP connections can hit speeds up to 32 gigabits per second. Then we have the QSFP or the Quad Small Form Factor Pluggable, and this is another expansion of the original SFP concept. The QSFP uses double fiber pairs. The QSFP allows for substantially more powerful data transmissions, and the QSFP connector, they are still small and hot pluggable, and they still support Ethernet and fiber optics. All right, let's talk about termination points. And the first one we're going to talk about is the 66 block. So a 66 block, this is a type of punch down block used to connect sets of wires in a telephone system. They have been manufactured in 3 sizes. You have A, B, and M. A and B have 6 clips in each row, while M only has 4. The A blocks have the rows spaced further apart and have been obsolete for many years. The B style is used mainly in distribution panels where several destinations need to connect to the same source, and the M blocks are often used to connect a single instrument to such a distribution block. Next, we have the 110 block. So a 110 block, this is a type of punch down block used to terminate runs on premises wiring in a structured cabling system. The designation 110 is also used to describe a type of insulation displacement contact connector used to terminate twisted pair cables, which use a punch down tool similar to the type used for the older 66 block. Then we have a patch panel, and this is the device or unit featuring a number of jacks, usually of the same or similar type, for the use of connecting and routing circuits for monitoring, interconnecting, and testing circuits in a convenient, flexible manner. Patch panels are typically built into a wiring closet or added to equipment racks, and patch panels are primarily designed as a termination point for twisted pair and fiber cables used in networks. And then we have a fiber distribution panel. So a fiber distribution panel, also known as a fiber optic patch panel. This is mainly used for accommodating fiber cable terminations, connections, and patching. With fiber optic distribution panels, network technicians can control massive fiber cables and connection points in a standard panel or enclosure structure. Therefore, fiber distribution panels make it simple and convenient for us to do cable management and maintenance. All right, so this was my quick little video. So in summary, we have talked about various fiber optic transceivers and various cabling termination points. In this video, you're going to learn about various copper cable and termination standards. So let's talk about copper cable standards. You got Cat 3, Cat 5, Cat 5e, Cat 6, Cat 6a, and Cat 7. Also, you have various 10 base T, 1000 base T network types and their supported speeds, along with some notes about it. I'm not going to go over all this in detail. That's why I created this handy dandy little chart for you to reference. So go ahead and hit the pause button, take a screenshot, do whatever you got to do, or go ahead on over to my website, technologyg.com, where this particular lesson is posted and this handy dandy little chart will be available for you. Next, let's talk about RG6 and RG59 coaxial cables. So coaxial cabling, this is the oldest type of networking cabling. Its data wires are surrounded by a wire mesh for insulation, and prior to the advent of fiber optics, the fastest internet service available to home and business customers was cable internet. And cable internet, this is a form of broadband internet access which uses the same RG6 coaxial cable as a cable television, but adds a device called a cable modem to convert the signal for use by computers and home business networks. RG6 has a 75 ohm resistance. It uses an 18 gauge center conductor. It's available in quad shielded versions and can carry signals up to 1.5 gigahertz, which makes it much better for HD TV signals. The RG59, this is used in older cable TV or satellite TV installations, as well as closed circuit television security installations, and it has a 75 ohm resistance. The RG59 uses a 22 gauge center conductor and a single outer shield, and it is designed for signals up to 50 megahertz. And now let's talk about some copper termination standards. So the first one we're going to talk about is the T568B, also known as a straight through cable. So the wiring standard for all types of Ethernet unshielded twisted pair cables is known as the T568B. And this type of cable is also known as a straight through cable, which is most commonly used to connect a host to a client, such as the RJ45 wire connected from a PC to a home router. So basically this wire connects dissimilar devices. And the wire order from left to right when looking at the top of the connector is as follows. You have pin 1, that's orange with a white stripe. Pin 2 is just an orange wire. Pin 3 is green with a white stripe. Pin 4 is blue. Pin 5 is blue with a white stripe. 6 is green. 7 is brown with a white stripe. And 8 is brown. And then we have the T568. And this standard swaps the positions of the orange and green wires that are used in the T568B. This type of cable is also known as a crossover cable, which are most commonly used to connect two hosts directly, such as a PC directly connecting to another PC or a switch connecting to another switch. So basically this wire connects similar devices. And the wire order from left to right when looking at the top of the connector is as follows. You have pin 1, that's green with a white stripe. 2 is green. 3 is orange with a white stripe. 4 is blue. 5 is blue with a white stripe. 6 is orange. 7 is brown with a white stripe. And 8 is brown. Also, you can create a crossover cable by building one end of the cable to be the T568B standard and the other to be the T568A standard. And that was my quick little class talking about copper cable and termination standards. In this video, you're going to learn about various networking devices such as firewalls, routers, switches, hubs, bridges, modems, wireless access points, media converters, wireless range extenders, and VoIP endpoints. Let's talk about a firewall. So a firewall, this is a network security system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. A firewall typically establishes a barrier between a trusted internal network and an untrusted external network, such as the internet. And firewalls can be either software or hardware, and firewalls are frequently incorporated into wireless routers, Microsoft Windows and Mac OS, and software firewalls. They are also known as host firewalls. And firewalls work like this. A computer from outside the network attempts to gain access to a server on the network that has a firewall. The firewall blocks the incoming traffic from the computer because no computer from inside the network has sent a request to the outside computer. A computer on the network sends a request to a remote server hosting a website. The remote server responds back to the computer on the network. Because the remote server is responding to a request from the network, the firewall permits the incoming traffic. Next, let's talk about a router. So a router, this is a networking device that forwards data packets between computer networks. Routers perform the traffic directing functions on the internet. Data sent through the internet, such as a web page or email, is in the form of data packets. A packet is typically forwarded from one router to another router through the networks that constitute an internetwork, also known as the internet, until it reaches its destination node. Devices that are connected to a LAN via a router connected to a cable modem or DSL modem allow for these devices to share a broadband connection to the internet. A router has at least 2 network connections that use RJ45 cables. The port labeled WAN or wide area network, this connects the router to a modem. The port labeled LAN or local area network connects the router to a switch. If the router has a built-in switch, it has multiple LAN ports numbered starting at 1. one. And most routers today are wireless routers that use the 802.11 Wi-Fi standards that combine a router, a switch, and an access point. A router has two IP addresses because it has two network connections. One network connection uses a private IP address and is used to attach to the LAN ports, and the other network connection is the one used to connect to the internet via a modem. And this is called your public IP address. And here are two pictures of two different types of routers. On the left, you have a Cisco networking router. This is a dedicated router machine. And on the right, you have a SOHO router, or a small office, home office router. And this is the type of wireless router you more than likely have in your house of some sorts if you have Wi-Fi in your house. And that SOHO router, once again, that combines the elements of a switch, a router, and an access point all into one device. Let's talk about a switch. So a switch is a high-speed device that receives incoming data packets and redirects them to their destination on a local area network. Essentially, switches are the traffic cops of a simple local area network. A switch enables direct connections between any two computers or devices on the network. A switch makes a direct connection between the sending and receiving devices by identifying the MAC address or the media access control address of each device. Switches are available with as few as 4 or 5 RJ45 ports or with dozens of ports. And switches can be connected to each other, which is called stacked or daisy chain, so that a small network can grow without needing to replace existing switches. And most switches support at least fast Ethernet signaling, or 100 megabits per second, with gigabit Ethernet 1000 megabits per second becoming common in home and small office networking. 10 gig Ethernet switches are now used in enterprise networks, and low-cost switches used in SOHO networks cannot be configured to perform complex switching functions and are also considered unmanaged switches. And then we have a managed switch, and that can organize its switch ports into several logical networks, also known as VLANs, or virtual local area networks, that cannot interfere with each other, which enables different companies or departments to have independent networks in the same physical location to keep their traffic separated. And managed switches, they also support SNMP, or Simple Network Management Protocol, for diagnostics and performance measurements. To enable a switch network to connect to the internet, you would connect a switch to a router, and many routers made for home or small offices, they include a multi-port switch and a wireless access point. Next, we have a hub. And a hub, this is a network hardware device for connecting multiple Ethernet devices together and making them act as a single network segment. Hubs are used to connect computers together and to boost the communication signal between computers. It has multiple input-output ports in which a signal introduced at the input of any port appears at the output of every port except the original incoming. A network hub is considered an unsophisticated device in comparison with a switch. A hub cannot examine or manage any of the traffic that comes through it. A hub has no memory to store data. It can handle only one transmission at a time. It splits the bandwidth of any connection amongst all computers connected to it and broadcasts data to all computers connected to it. When it comes to the splitting of bandwidth, a 5-port Ethernet hub will divide 100 megabits per second speeds of the fast Ethernet amongst the 5 ports, therefore only providing 20 megabits per second of bandwidth to each port for fast Ethernet. With that being said, hubs have become rare in networks. Next, we have a wireless bridge, and a wireless bridge, or a setting or many access points. This thing connects two wired networks together over Wi-Fi. The wireless bridge acts as a client, logging into the primary router and getting an internet connection, which it passes on to the devices connected to its LAN. Next, we have a modem, and a modem, which stands for modulate, demodulate, or modulator, demodulator. This is a hardware device that converts data into a format suitable for a transmission medium so that it can be transmitted from one computer to another, historically along telephone wires. And a modem modulates one or more carrier wave signals to encode digital information for transmission and demodulates signals to decode the transmitted information. The goal is to produce a signal that can be transmitted easily and decoded reliably to reproduce the original digital data. Modems connect a LAN to an ISP. Dial-up modems allow computers to gain gain access to the internet by converting the computer's digital signals to analog signals used by a LAN-based phone line. And the issue with dial-up modems is that they are slow devices and are typically used if no internet option is available. And the most common modems in use today are cable and DSL modems. Next, we have a wireless access point. So a wireless access point, this is a networking hardware device that allows other Wi-Fi devices to connect to a wired network based on the 802.11 standards. The wireless access point usually connects to a router via a wired network as a standalone device, but it can also be an integral component of the router itself. Wireless access points act as central connecting points for computers equipped with wireless network adapters by identifying each computer by its MAC address. To connect the wireless network to a wired network, you would need to connect the RJ45 port on the wireless access point to a switch on a wired network. If the wired network is connected to a router with internet access, the wireless network will also have internet access. Next, we have a media converter. So a fiber media converter. This is a simple networking device that makes it possible to connect two dissimilar media types, such as twisted pair with fiber optic cabling. They were introduced to the industry in the 1990s and are important in interconnecting fiber optic cabling based systems with existing copper-based structured cabling systems. They are used in metropolitan area network access and data transport services to enterprise customers. Then we have a wireless range extender. So a repeater or an extender. This is an electronic device that receives a signal and retransmits it. Repeaters are used to extend transmissions so that the signal can cover longer distances or be received on the other side of an obstruction. Wireless signals can be blocked by a variety of objects such as bricks, steel, and concrete walls. Distance also weakens signals as well. Wireless repeaters can look similar to wireless routers, and some even include a switch component, but instead of connecting a cable or DSL modem, a repeater connects wirelessly to a wireless router. And then we have a VoIP endpoint. So voice over internet protocol. This is a method and group of technologies for the delivery of voice communications and multimedia sessions over IP networks, such as the internet. VoIP and SIP are session initiation protocol phones. They are examples of VoIP endpoints. All right, and that was my class. So let's go ahead and get into some of this handy dandy check on learning. So the first question is, what type of network switch supports plug and play style usage and does not support custom configurations? Is it a POP switch, a level 5 switch, a managed switch, or an unmanaged switch? So which of these supports plug and play and does not support custom configurations? And the correct answer is, this would be an unmanaged switch. They do not support, or they have very limited configuration options, and they are meant to work for most networks right out of the box. Managed switches, they require more configuration to properly function, but offer more features and functionality. Next question. You've just installed a wireless access point upstairs in your new home. However, when you go down into the basement, you lose your signal and can no longer surf the internet. What type of equipment could you buy if you did not want to purchase another access point, but you wanted to keep wireless connectivity? Would you use a wireless range extender, a switch, a router, or a hub? And the correct answer would be a wireless range extender. This will allow for you to keep a wireless connection across your house at a greater distance. Next question. Which network device is used to connect networks to other networks? Would it be a hub, a wireless bridge, a router, or a media converter? And the correct answer would be a router. Routers are used to connect networks to other networks. And in summary, ladies and gentlemen, we have talked about various networking devices such as firewalls, routers, switches, hubs, bridges, modems, wireless access points, media converters, wireless range extenders, and voice over IP endpoints. In this video, you're going to learn about advanced networking devices such as multi-layer switches, wireless controllers, load balancers, IDS and IPS, proxy servers, VPN concentrators, AAA radius servers, UTM appliances, NGFW layer 7 firewalls, VoIP PBXs, VoIP gateways, and content filters. Let's talk about the multi-layer switch. So a multi-layer switch, this is a computer networking device device that switches on OSI layer 2 like an ordinary network switch and provides extra functions on higher OSI layers. Multi-layer switching combines layers 2, 3, and 4 switching technologies and provides high-speed scalability with low latency. Multi-layer switching can move traffic at wire speed and also provide layer 3 routing. There is no performance difference between forwarding at different layers because the routing and switching is all hardware based, and multi-layer switching can make routing and switching decisions based on the following. You have MAC addresses in the data link frame, protocol fields in the data link frame, IP addresses in the network layer header, the protocol field in the network layer header, and port numbers in the transport layer header. Next, we have a wireless controller. So a wireless LAN controller, this is used in combination with the lightweight access point protocol to manage lightweight access points in large quantities by the network administrator or network operations center. The wireless LAN controller manages network access points that allow wireless devices to connect to the network. Next, we have a load balancer. So in computing, load balancing, this refers to the process of distributing a set of tasks over a set of resources or computing units with the aim of making their overall processing more efficient. Load balancing can optimize the response time and avoid unevenly overloading some compute nodes while other compute nodes are left idle. A load balancer is a device that acts as a reverse proxy and distributes network or application traffic across a number of servers. Load balancers are used to increase capacity or concurrent users and reliability of applications. Intrusion detection system. So an intrusion detection system, this is a device or software application that monitors a network or systems for malicious activity or policy violations that might not be detected by a firewall. Typical threats detected by an IDS include attacks against services, malware attacks, data-driven attacks, and host-based attacks. To detect these threats, a typical IDS uses signature-based detection of unusual activities or anomalies, and stateful protocol analysis. Any intrusion activity or violation is typically reported either to an administrator or collected centrally using a security information and event management or a SIEM system. A SIEM system combines outputs from multiple sources and uses alarm filtering techniques to distinguish malicious activity from false alarms. A true IDS does not block attacks, but some products and services referred to as an IDS actually have characteristics of an IPS or an intrusion prevention system. So the easiest way you can think about an intrusion detection system is to think of the Ring doorbell if you have that on your house. Basically, the Ring doorbell has a security camera that can see somebody that is trying to break into your house, but it cannot prevent the person from breaking into your house. All it can do is just send you the video feed and alerts to your phone, but it cannot actively stop somebody from trying to break into your house. Then we have the intrusion prevention system. So an intrusion prevention system, this is also known as an intrusion detection prevention system. And this is a technology that keeps an eye on a network for any malicious activities attempting to exploit a known vulnerability. An IPS's main function is to identify any suspicious activity and either detect and allow it or prevent and block the threat. So getting back to the Ring doorbell analogy, once again, a Ring doorbell can only monitor and witness somebody trying to break into your house, but it cannot actively stop it. Now, if you had a pit bull on the other side of that door that decided it was going to take a bite out of crime, that would be an intrusion prevention system, meaning that the dog is actually doing something to prevent the intruder from coming into your house. A proxy server. This is a server application or appliance that acts as an intermediary for requests from clients seeking resources from servers that provide those resources. A proxy server thus functions on behalf of the client when requesting service, potentially masking the true origin of the request to the resource server. Instead of connecting directly to a server that can fulfill a requested resource, such as a file or a web page, the client directs the request to the proxy server, which evaluates the request and performs the required network transactions. If the proxy server does not have the requested page, it downloads the page on behalf of the client, sends the page to the client, and retains a copy of the page in its cache. This serves as a method to simplify or control the complexity of the request or provide additional benefits such as load balancing, privacy, or security. Also, proxy servers can be used for anonymous web surfing. Next, we have a VPN concentrator. So a VPN concentrator, this is a type of networking device that provides secure creation of VPN connections and delivery of messages between VPN nodes. A VPN concentrator primarily adds the capabilities of a VPN router by adding advanced data and network security to the communications. It has the ability to create and manage a large quantity of VPN tunnels. VPN concentrators are typically used for creating site-to-site VPN architectures where they can do the following. They can establish and configure tunnels. They can authenticate users. They can assign tunnels and IP addresses to users. They can encrypt and decrypt data, and they can ensure end-to-end delivery of data. Next, we have a AAA radius server. So remote authentication dial-in user service. This is a network protocol operating on ports 1812 and 1813 that provides centralized authentication, authorization, and accounting management for users who connect and use a network service. Users who want access to a network or an online service can contact the radius server and provide a username and password to attempt to gain access. The server would then authenticate or decline access to the network or service. UTM appliance, so Unified Threat Management. This is an approach to information security where a single hardware software installation provides multiple security functions. UTM devices provide firewall, remote access, VPN support, web traffic filtering with anti-malware, and network intrusion prevention. This contrasts with the traditional method of having point solutions for each security function. UTM simplifies information security management by providing a single management and reporting point for the security administrator rather than managing multiple products from different vendors. UTM devices may be specialized boxes that are placed between the organization's network and the internet, but they can also be virtual machines using cloud-based services. UTM appliances have gained popularity since 2009, partly because the all-in-one approach simplifies installation, configuration, and maintenance. Such a setup saves time, money, and people when compared to the management of multiple security systems. New generation firewall. So this is a part of firewall technology combining a traditional firewall with other network device filtering functions, such as an application firewall using line-in deep packet inspection, intrusion prevention system packet filtering, network and port address translation, stateful inspection, and VPN support. Other techniques might also be employed, such as TLS SSL encrypted traffic inspection, website filtering, QoS bandwidth management, antivirus inspection, and third-party identity management integration, which uses stuff like LDAP, Radius, and Active Directory. VoIP PBX. So an IP PBX or Internet Protocol Private Branch Exchange. This is a system that connects telephone extensions to the public switch telephone network and provides internal communication for a business. An IP PBX is a PBX system with IP connectivity and may provide additional audio, video, or instant messaging communication utilizing the TCP/IP protocol stack. Voice over IP gateways can be combined with traditional PBX functionality to allow businesses to use their managed intranet to help reduce long distance expenses and take advantage of the benefits of a single network for voice and data, also known as a converged network. Then we have a VoIP gateway. So this is a hardware device that converts telephony traffic into packets of data for transmission over the internet, bridging the analog, cellular, and IP network. Depending on where the voice signal originates from, the gateway will convert the voice signal into the proper form for receipt by the destination network. If the voice signal originates from the PSTN, a VoIP gateway can convert the analog signal into packets of data and send it to the IP-based phone system and vice versa. And then we have a content filter. So content filtering, this is the use of a program to screen and or exclude access to web pages or email that is deemed objectionable. Content filtering is used by companies as part of their firewalls and also by Soho personal computers. Content filtering works by specifying content patterns such as text strings or objects within images that, if matched, indicate undesirable content that is to be screened out. A content filter will then block access to this content. All right, that is my quick little class on advanced networking devices. So let's go ahead and get into some of this check on learning. So the first question is, which network device enables centralized management of wireless access points? Would it be a VPN concentrator? Would it be a load balancer, a multi-layer switch, or a wireless LAN controller? And the correct answer is, this would be a wireless local area network controller. That is the correct answer. Next question. A network device designed for managing the optimal distribution of workloads across multiple computing resources is referred to as what? Is this a content filter, network attached storage, load balancer, or a domain controller? And the correct answer is, that will be a load balancer. And the final question is, a computer system or application that acts as an intermediary between another computer and the internet is commonly referred to as what? Is this a bridge, active hub, server, or a proxy? This would be a proxy, ladies and gentlemen. So in summary, we have talked about advanced networking devices such as multi-layer switches, wireless controllers, load balancers, IDS, IPS proxy servers, VPN concentrators, AAA radius servers, UPN appliances, next generation firewalls, VoIP PBXs, VoIP gateways, and content filters. In this video, you're going to learn about virtualization and network storage technologies such as virtual switches, virtual firewalls, virtual NICs, virtual routers, hypervisors, network attached storage, storage area networks, fiber channel over Ethernet, fiber channel, iSCSI, InfiniBand, and jumbo frames. Let's talk about virtual networking components. So the first one is a virtual switch. So a virtual switch, this is a software application that allows communication between virtual machines. A virtual switch does more than just forward data packets. It intelligently directs the communication on the network by checking data packets before moving them to a destination. Virtual switches are usually embedded into installed software, but they may also be included in a server's hardware as part of its firmware. A virtual switch is completely virtual and can connect to a network interface card. The virtual switch merges physical switches into a single logical switch. This helps to increase bandwidth and create an active mesh between servers and switches. Let's talk about a virtual firewall, and this is a network firewall service or appliance running entirely within a virtualized environment and which provides the usual packet filtering and monitoring provided via a physical network firewall. The virtual firewall can be realized as a traditional software firewall on a guest virtual machine already running, or a purpose-built virtual security appliance designed with virtual network security in mind, or a virtual switch with additional security capabilities, or a managed kernel process running within the host hypervisor. Next, we have a virtual NIC. So a virtual NIC uses the host physical network adapter to initiate and manage network communications. It is created by the operating system or a purpose-built software application. Once created, it can be used for different applications and networking services. So for instance, a virtual NIC enables a computer to connect to a VPN while being simultaneously connected to another network. Each of the virtual NICs is considered a unique device, and each has its own separate IP address and network configuration. In virtualization environments, each virtual machine is generally installed with a virtual network adapter for communication between other virtual machines or with the network itself. Let's talk about a virtual router. So this is a software function that replicates in software the functionality of a hardware-based layer 3 internet protocol router, which has traditionally used a dedicated hardware device. Virtual routing is a form of network functions virtualization in which the functions of traditional hardware-based network appliances are converted to software that can be run on standard commercial off-the-shelf hardware. This has the advantages of lowering hardware costs and allowing more hardware interoperability rather than requiring a proprietary hardware platform. Let's talk about a hypervisor. So a hypervisor, also known as a virtual machine monitor. This is a computer software, firmware, or hardware that creates and runs virtual machines. A computer on which a hypervisor runs one or more virtual machines is called a host machine, and each machine is called a guest machine. A virtual machine is a software emulation of the hardware in a working computer. The VMM sets up emulated motherboard chipsets, USB controllers, hard disk disk, host adapters, video cards, and other components of an actual computer as part of the virtual machine, along with setting aside either an expandable or fixed amount of hard disk space. After a hypervisor creates and configures a virtual machine, you install the operating system and apps desired into the virtual machine to have a working emulated computer or virtual machine. The hypervisor is used to start the virtual machine, and depending on the RAM, processor speed, and features, and available hard disk space in the physical computer, the hypervisor can run several virtual machines at the same time. Now, there are two types of hypervisors. The first one is called a Type 1 hypervisor, and this is a virtual machine monitor that works directly with the host computer hardware rather than being installed inside of an existing operating system. And Type 1 hypervisors are often referred to as bare metal hypervisors. So you have a Type 2 hypervisor, and this is a virtual machine monitor that runs inside of an operating system and carves out RAM and disk space for an already running system. So the main difference between the Type 1 and Type 2 is as follows. Type 1, you turn on the machine and it automatically boots into the hypervisor, so you can go about the process of creating the VMs. Type 2, you turn on your computer, it loads your normal operating system, then you have to load the hypervisor or the virtual machine software, which will then allow for you to create the virtual machines. Let's talk about network storage types. So the first one is NAS, or network attached storage. So a network attached storage system, this is a storage device connected to a network that allows storage and retrieval of data from a centralized location for authorized network users and clients. Network attached storage is a self-contained storage device that contains one or more drives, a network interface, and is bundled with software to enable computers on the network to access the device. A network attached storage device built for use in business may have two or more drive bays, permit easy upgrading of drives, and might also provide automatic mirroring, known as copying, of the contents of one drive to another, and that is also known as RAID 1. Then we have a storage area network, and these are sometimes referred to as networks behind the servers and historically developed out of a centralized data storage model, but with its own data network. A storage area network is, at its simplest, a dedicated network for data storage. In addition to storing data, storage area networks allow for the automatic backup of data and the monitoring of the storage, as well as the backup process. A storage area network is a combination of hardware and software. Storage area networks are primarily used to access data storage devices such as disk arrays and tape libraries from servers, so that the devices appear to the operating system as direct attached storage. A storage area network typically is a dedicated network of storage devices not accessible through the LAN. Although a storage area network provides only block level access, file systems built on top of a storage area network do provide file level access and are known as shared disk file systems. Next, let's talk about connection types. And the first one is fiber channel over Ethernet. Yes, it is pronounced fiber, even though it is spelled F-I-B-R-E. For some reason, they decided to spell it F-I-B-R-E instead of F-I-B-E-R, but they are the same word. So fiber channel over Ethernet, this is a computer network technology that encapsulates fiber channel frames over Ethernet networks. This allows fiber channels to use 10 gigabit Ethernet networks or higher speeds while preserving the fiber channel protocol. Also, fiber channel is designed as a channel interface. That is, it guarantees lossless delivery of frames with a predictable latency. Since classical Ethernet had no priority-based flow control, unlike fiber channel over Ethernet required enhancements to the Ethernet standard to support a priority-based flow control mechanism to reduce frame loss from congestion. And then let's talk about fiber channel. So this is a high-speed data transfer protocol providing in-order, lossless delivery of raw block data. Fiber channel is primarily used to connect computer data storage to servers and storage area networks in commercial data centers. Fiber channel networks form a switch fabric because the switches in a network operate in unison as one big switch. Fiber channel typically runs on optical fiber cables within and between data centers, but can also run on copper cabling. Supported data rates include 1, 2, 4, 8, 16, 32, 64, and 128 gigabits per second, resulting from improvements in successive technology generations. And then we have iSCSI, or Internet Small Computer Systems Interface. So in computing, iSCSI is an IP-based storage networking standard for linking data storage facilities. It provides block-level access to storage devices by carrying SCSI commands over a TCP/IP network. iSCSI is used to facilitate data transfers over intranets and to manage storage over long distances. It can be used to transmit data over LANs, WANs, or the internet, and can enable location-independent data storage and retrieval. The protocol allows clients, which are called initiators, to send SCSI commands to storage devices, which are called targets, on remote servers. It is a storage area network protocol, allowing organizations to consolidate storage into storage arrays while providing clients, such as database and web servers, with the illusion of locally attached SCSI disks. It mainly competes with fiber channel, but unlike traditional fiber channel, which usually requires dedicated cabling, iSCSI can be run over long distances using existing network infrastructure. Then we have InfiniBand. So InfiniBand, this is a computer networking communication standard used in high performance computing that features very high throughput and very low latency. It is used for data interconnect both among and within computers. InfiniBand is also used as either a direct or switch interconnect between servers and storage systems, as well as an interconnect between storage systems. It is designed to be scalable and uses a switched fabric network topology. InfiniBand offers throughput of up to 2.5 gigabytes per second and support for up to 64,000 addressable devices. Because it is also scalable and supports quality of service and failover, InfiniBand is often used as a server connection in high performance computing environments. And then we have a jumbo frame. So in computer networking, jumbo frames are Ethernet frames with more than 1,500 bytes of payload. Commonly, jumbo frames can carry up to 9,000 bytes of payload, but smaller and larger variations do exist. Many gigabit Ethernet network interface controllers and some fast Ethernet switches and fast Ethernet network interface cards can support jumbo frames. Each Ethernet frame must be processed as it passes through the network. Processing the contents of a single large frame is preferable to processing the same content broken up into smaller frames, and this makes better use of available CPU time by reducing interruptions. This also minimizes the overhead byte count and reduces the number of frames needed to be processed. This is analogous to physically mailing a packet of papers instead of several single envelopes with one sheet each, saving envelopes and cutting sorting times. All right, so that is my quick little class on virtualization and network storage technologies, where we talked about all of this wonderful stuff, such as virtual switches, virtual firewalls, virtual NICs, virtual routers, hypervisors, network attached storage, storage area networks, fiber channel over Ethernet, fiber channel iSCSI, InfiniBand, and jumbo frames. In this video, you're going to learn about wide area network services such as ISDN, T1, T3 circuits, E1, E3 circuits, OC3 and OC192 circuits, DSL, Metropolitan Ethernet, cable broadband, dial-up, PRI, and various transmission mediums. Talk about the first service type, ISDN, or Integrated Services Digital Network. So ISDN, this is a set of communication standards for simultaneous digital transmission of voice, video, data, and other network services over the traditional circuits of the public switch telephone network. ISDN is used on PSTN lines with a terminal adapter on multiple channels of 64 kilobits per second each, and a terminal adapter, this resembles a conventional analog modem. Internal modems plug into the same PCIe or PCI slot used by analog modems, and external modems are USB or serial ports. And there are two types of ISDN connections provided by local telephone companies, in which both types of connections enable the use of the internet, talk, or fax communications through a phone line at the same time. The first one you have is PRI, or the primary rate interface. So a PRI connection, this provides 1.536 megabits per second of bandwidth, whereas a BRI interface provides 64 kilobits per second or 128 kilobits per second dual channel of bandwidth. And PRI is also sold to large organizations. Then BRI, or basic rate interface, this is sold to small businesses and home offices before DSL and cable became widely available. And BRI, it offers up to 128 kilobits per second of bandwidth. Also, most telephone companies have largely phased out ISDN in favor of DSL, which is much faster and less expensive for internet connections. Then we have a T1 circuit. So a T1 carrier, this is a dedicated phone connection supporting data rates of 1.544 megabits per second. A T1 line consists of 24 individual channels, each of which supports 64 kilobits per second. Each 64 kilobit per second channel can be configured to carry voice or data traffic. Most telephone companies allow you to buy just some of these individual channels, which are known as fractional T1 access. And T1 lines are a popular lease line option for businesses connecting to the internet and for ISPs connecting to the internet backbone. The internet backbone itself consists of faster T3 connections, and T1 lines are sometimes referred to as DS1 lines. So when someone says they are running T1, they may be saying a few different things, such as they may mean that they have a network that is passing data at 1.544 megabits per second, or they may mean that they have a network that conforms to the T1 electrical interface specification, or that they have a network that passes data that conforms to one of the several framing rates such as D4, ESF, etc. But more likely than not, they mean all three, but their concentration may be only one of these items. And a T3, this is a dedicated phone connection supporting data rates of about 43 megabits per second. A T3 line actually consists of 672 individual channels, each of which supports 64 kilobits per second, and T3 lines are used mainly by ISPs connecting to the internet backbone and for the backbone itself, and T3 lines are sometimes referred to as DS3 lines. Next, we have the E-carrier lines, and the first one is the E1. So the E-carrier system, this enables the transmission of several multiplex voice and data channels simultaneously on the same transmission facility or line. Of the various levels of the E-carrier system, the E1 and E3 levels are the only ones that are used. An E1 circuit contains 32 channels in contrast to the 24 channels on a T1 circuit. Only 30 of those 32 channels, however, can transmit data such as voice and video. Specifically, the first of those 32 channels is reserved for framing and synchronization, and the 17th channel is reserved for signaling, that is, setting up, maintaining, and tearing down a call. And E1 circuits also have a bandwidth capacity of 2.048 megabits per second, and E1 circuits, they are typically popular outside of North America and Japan. And just as a T3 circuit provides more bandwidth than a T1 circuit, and E3 circuits available bandwidth of 34.4 megabits per second is significantly more than the 2.046 megabits per second of bandwidth offered by an E1 circuit. Next, we have OC3 and OC192. So optical carrier transmission rates, they are a standardized set of specifications of transmission bandwidth for digital signals that can be carried on synchronous optical networking or SONET fiber optic networks. Transmission rates are defined by rate of the bit stream of the digital signal and are designated by a hyphenation of the acronym OC and an integer value of the multiple of the basic unit of rate, such as OC-3. So OC-3, this is a network line with transmission data rates of up to 155.52 megabits per second with a payload of 148 megabits per second and overhead of 6 megabits per second, including the path overhead using fiber optics. And then OC192, this is a network line with transmission speeds of up to 9,953 megabits per second with a payload of 9,510 megabits per second and an overhead of 442 megabits per second. Let's talk about DSL, or digital subscriber line. And this is a communications medium used to transfer digital signals over standard telephone lines. Along with cable internet, DSL is one of the most popular ways ISPs provide broadband internet access. DSL is used by telephone companies to provide internet services at speeds much faster than that allowed by analog or dial-up internet services, while allowing traditional analog telephones and devices such as fax machines to share the same connection. To make this possible, devices called DSL microfilters are attached between telephones and telephony devices such as answering machines, voicemail, and fax machines to prevent interference with DSL signals. And traditional DSL runs over telephone lines originally developed for voice services only. It is far slower than a cable internet connection, and traditional DSL speeds range from 768 kilobits per second down to 384 kilobits per second up, all the way to 6 megabits down, 768 up. Speeds decrease as the distance between the DSL service location and the central office or the central switch providing the DSL connection increases. And most DSL providers do not have data caps. Some of the disadvantages of DSL are as follows. It has inconsistent internet connection speeds. It's available in limited distances from the service provider, and speeds drop the greater the distance from the connection to the internet, which is also known as, once again, the central office or the central switch, and it is slower than cable or fiber connections. Next, we have Metropolitan Ethernet. So a metropolitan area Ethernet, also known as Metro Ethernet. This is a metropolitan area network that is based on Ethernet standards. It is commonly used to connect subscribers to a larger service network or the internet, and service providers, they use Metro Ethernet to do the following things, such as interconnect business offices or data centers, where Metro Ethernet can connect 2 sites or hundreds of sites. It can connect residential subscribers or businesses to the internet. It can provide connectivity to public or private cloud data centers. It can provide wholesale mobile backhaul services, and it can provide multicast delivery used by business customers for video conferencing and used by residential subscribers for IPTV and video applications. Then we have cable broadband. So cable internet access, or simply cable internet. This is a form of broadband internet access which uses the same infrastructure as cable television. Like DSL and fiber, cable internet access provides network edge connectivity, which is also known as last mile access, from the ISP to an end user. It is integrated into the cable television infrastructure, just like how DSL is integrated into the existing telephone network. And data signals, they can be sent over a network in 2 ways, either by baseband or broadband. In baseband signaling, this sends a signal at any given instance, whereas broadband signaling sends multiple signals on separate frequencies. A single piece of coaxial cable carrying multiple signals comes into your home, and a small box enables you to select specific channels. Broadband creates these separate channels through a process called frequency division multiplexing. The term broadband is widely used to refer to high-speed internet access, and broadband provides users with an always-on, high-speed connections to access the internet and transfer data. Unlike narrowband, broadband does not tie up a consumer's phone lines. Plus, it enables access to high-speed bandwidth applications such as voice and video calling, online video streaming, interactive gaming, and much more. Then we have dial-up. So dial-up internet access. This is a form of internet access that uses the facilities of the public switch telephone network to establish a connection to an ISP by dialing a telephone number on a conventional telephone line. Dial-up connections use modems to decode audio signals into data to send to a router or computer, and to encode signals from the latter 2 devices to send to another modem. Until the late 1990s, dial-up networking was the most common way for home and small businesses to connect to the internet. Today, dial-up connections are used when no other internet connection is available. Dial-up has rates ranging from 28.8 kilobits per second to 56 kilobits per second and is available any place that has a landline telephone system. A disadvantage of telephone dial-up is that voice and data cannot share the wire at the same time. And then we have PRI, and this stands for Primary Rate Interface. So PRI, this is a telecommunications interface used mostly in an ISDN or Integrated Services Digital Network. A PRI is a form of time division multiplexing, allowing you to send up to 23 separate communications via voice, data, or video. And channels are typically used by larger enterprise companies with a PBX system to help with access to the public switch telephone networks. And then finally, transmission mediums. Now, we have already covered this topic where we discussed various wide area network transmission mediums such as satellite, copper, fiber, and wireless. And you can go find those if you look for my CompTIA A+ course. Look for video 2.7, which is titled Internet Connections and Network Types. And in summary, we have talked about all of this wonderful stuff pertaining to wide area network services such as ISDN, T1, T3 circuits, E1, E3 circuits, OC3 and OC192 circuits, DSL, Metro Ethernet, cable broadband, dial-up, PRI, and I told you exactly where you can go to find out more information about various transmission mediums pertaining to wide area network services. In this video, you're going to learn about the characteristics of wide area network services such as MPLS, ATM, frame relay, PPPoE, PPP, DM, VPN, SIP trunk, in addition to learning about wireless area network termination such as the demarcation point, CSU, DSU, and the smart jack. Now, I know it's a lot of acronyms in here, but the quicker you get to learn what these acronyms stand for, the better off you will be when it is time for you to take this exam. Let's talk about MPLS, and that stands for multi-protocol label switching. So MPLS, this is a routing technique in telecommunication networks that directs data from one node to the next based on short path labels rather than long network addresses, thus avoiding complex lookups in a routing table and speeding traffic flows. The labels identify virtual links, also known as paths, between distant nodes rather than endpoints, and MPLS can encapsulate packets of various network protocols, hence the multi-protocol reference on its name. And MPLS supports a range of access technologies, including T1, E1 circuits, ATM, frame relay, and DSL. Next, we have ATM, and that stands for asynchronous transfer mode. So asynchronous transfer mode, this is a telecommunications standard for digital transmission of multiple types of traffic, including telephony or voice, data, and video signals in one network without the use of separate overlay networks. ATM was designed to integrate telecommunication networks. It can handle both traditional high throughput data traffic and real-time low latency content such as voice and video. ATM provides functionality that uses features of circuit switching and packet switching network. It uses asynchronous time division multiplexing. In the OSI reference model, data link layer or layer number 2, the basic transfer units are generically called frames. In ATM, these frames are of fixed length or 53 octets or bytes, and they are specifically called cells. This differs from approaches such as IP or Ethernet that uses variable size packets of frames. ATM uses a connection-oriented model in which a virtual circuit must be established between two endpoints before the data exchange begins. These virtual circuits may be either permanent, i.e. dedicated connections that are usually pre-configured by the service provider, or they can be switched, such as setting up on a per-call basis using signaling and disconnected when the call is terminated. Next, we have frame relay, and this is a standardized wide area network technology that specifies the physical and data link layers of digital telecommunication channels using a packet switching methodology. Originally designed for transport across ISDN or integrated services digital network infrastructures, it may be used today in the context of many other network interfaces. Network providers commonly implement frame relay for voice and data as an encapsulation technique used between LANs over a WAN. Each end user gets a private line or a leased line to a frame relay node. The frame relay network handles the transmission over a frequently changing path transparent to all end user extensively used WAN protocols. It's less expensive than leased lines, and that is one reason for its popularity. The extreme simplicity of configuring user equipment in a frame relay network offers another reason for frame relay's popularity. With the advent of Ethernet over fiber optics, MPLS, VPN, and dedicated broadband services such as cable modems and DSL, frame relay has become less popular in recent years. Then we have point-to-point protocol over Ethernet. So point-to-point protocol over Ethernet, this is a network protocol for encapsulating point-to-point protocol frames inside Ethernet frames. It originally appeared in the context of the boom of DSL in 1999 as the solution for tunneling packets over the DSL connection to the ISP's IP network, and from there to the rest of the internet. Typical use of point-to-point protocol over Ethernet involves leveraging the point-to-point protocol protocol facilities for authenticating the user with a username and password. On the customer premises equipment, point-to-point protocol over Ethernet may be implemented either in a unified residential gateway device that handles both DSL modem and IP routing functions, or in the case of a simple DSL modem without routing support, point-to-point protocol over Ethernet may be handled behind it on a separate Ethernet-only router or even directly on a user's computer. Let's talk about point-to-point protocol. So this is a data link layer or layer 2 communication protocol between two routers without any host or any networking in between. It can provide connection authentication, transmission encryption, and data compression. Point-to-point protocol is used over many types of physical networks, including serial cable, phone links, trunk lines, cellular telephones, specialized radio links, ISDN, and fiber optic links. Since IP packets cannot be transmitted over a modem line on their own without some data link protocol that can identify where the transmitted frames start and where it ends, ISPs have used point-to-point protocol for customer dial-up access to the internet. Next, we have dynamic multi-point virtual private network. So DMVPNs, this is a dynamic tunneling form of a VPN supported by Cisco iOS-based routers, ARG3 routers, and on Unix-like operating systems. DMVPN provides the capability for creating a dynamic mesh VPN network without having to pre-configure all possible tunnel endpoint peers. Next, we have a SIP trunk. So SIP trunking is a voice over internet protocol or VoIP technology and streaming media service based on the session initiation protocol by which internet telephony service providers deliver telephone services and unified communications to customers equipped with SIP-based private branch exchange and unified communication facilities. Most unified communication applications provide voice, video, and other streaming media applications such as desktop sharing, web conferencing, and shared whiteboards. All right, let's talk about terminations. And the first one we're going to talk about is called the demarcation point. So the demarcation point, this is the point at which the public switch telephone network ends and connects with the customer's on-premises wiring. It is the dividing line which determines who is responsible for installation and maintenance of wiring and equipment, such as a customer, subscriber, or the telephone company / provider. The demarcation point varies between countries and has changed over time. Next, we have the CSU DSU, or the Channel Service Unit Data Service Unit. So a CSU DSU, this is a digital interface device used to connect data terminal equipment, such as a router, to a digital circuit, such as a T1 line. The CSU DSU implements two different functions. The Channel Service Unit is responsible for the connection to the telecommunication network, while the Data Service Unit is responsible for managing the interface with the data terminal equipment. A CSU DSU can have an external connection point, or it can be integrated into a modular card installed in a router. A CSU DSU is the equivalent of the modem for an entire LAN. The DCE, commonly a modem or CSU DSU, this is the device used to convert the user data from the DTE or the data terminal equipment into a form acceptable to the wide area network service provider transmission link. And then we have a smart jack. So a smart jack, this is a smart and intelligent device placed right between the telephone company's demarcation and customer premises that performs connectivity checks and diagnostic tests. A very common capability provided by a smart jack is loopbacking, such that the signal from the telephone company is transmitted back to the telephone company. This allows the telephone company to test the line from the central office without the need to have test equipment at the customer site. All right, that is my quick little class. So let's go ahead and do some of this outstanding check on learning, shall we? So the first question is, which of the following enables VoIP calls between PBXs? Would it be VTP, PTSN, SIP trunks, or PPPoE? So which of the following enables VoIP calls between PBXs? And the correct answer is, that will be a SIP trunk, or a session initiation protocol trunk. That is the correct answer. Next question. Which of the following devices would be used for connecting a router to a T1 line? Would it be a CSU, DSU, a media converter, an IDF, or an F-type connector? So which of the following devices would be used for connecting a router to a T1 line? And the correct answer is, this will be a CSU, DSU, also known as a channel service unit, data service unit. Next question. A remote line diagnostic device placed at the joining point between an ISP's line and customer premises wiring is known as what? Is this an OTDR, a line tester, a loopback adapter, or a smart jack? And the correct answer is, this would be a smart jack, ladies and gentlemen. All right, so in summary, we have talked about all of this wonderful stuff as it directly relates to the characteristics of wide area network services. In this video, you're going to learn about network documentation such as diagram symbols, standard operating procedures, logical versus physical diagrams, rack diagrams, change management documentation, wiring and port locations, IDF, MDF documentation, labeling, network configuration and performance baselines, and inventory management. Let's talk about diagram symbols. So diagram symbols are useful for mapping the connections in a computer or telecommunications network. Network diagrams can show everything from high-level networks, such as connectivity across cities, to more granular networks, such as an office building's network. Your IT department should utilize standard templates to represent objects in network diagrams consistently, in addition to providing legends that clearly delineate one network device from another. Standard operating procedures. So an SOP, this is a set of step-by-step instructions compiled by an organization to help workers carry out routine operations. SOPs aim to achieve efficiency, quality, output, and uniformity of performance while reducing miscommunication and failure to comply with industry regulations. Whenever possible, it is important to document the procedures your IT staff are to follow given certain network conditions. For example, steps for dealing with an internet outage could aid staff members in taking quick action and minimizing disruptions. Logical diagram. So a logical network diagram depicts how information in the network flows. In a logical diagram, the following elements in a logical network topology are typically displayed. You have things such as subnets, which may show the IP addresses, the VLAN IDs, and the subnet mask. Network objects such as routers and firewalls, specific routing protocols, routing domains, voice gateways, traffic flow, and network segments. Logical diagrams also make network management easier in the following ways. So first example is troubleshooting. So if service is out somewhere between two IP addresses, using a logical network diagram can quickly rule out an issue caused by a firewall. Now the next example is a firewall. So with logical network diagrams, you can ensure firewall rule bases remain accurate. It can eliminate redundancy. So logical network diagrams will clearly help determine what isn't redundant and what is. It can help with capacity planning. So although physical network diagrams are instrumental in capacity planning, logical diagrams also help with them. You can map out expanding or changing the network and see what impact that will have, and also sharing network information. So if you need to share information about the network but want to conceal physical information about the network, you can use a logical network diagram to accomplish that. We have physical diagrams. So a physical network diagram illustrates the interconnection of the devices in the network with wires and cables. The physical network diagram reveals the network topology with all the physical aspects such as ports, cables, racks, servers, specific models, etc., usually used by IT professionals. They are used to visualize the communication scheme of the network arrangement in residences or offices. Next we have is rack diagram. So a rack diagram, also known as a rack elevation. This is a visual representation of the organization of IT equipment within a server rack used to track and manage data center assets. We have change management documentation. So it is critical that change controls be in place in your organization, as well as careful documentation when changes actually take place. This helps ensure the accuracy of network information and can improve critical insecurity response and troubleshooting operations. And change management also does the following. It can process to coordinate the change needed by business, authorize changes and coordinates change timelines to avoid conflict. It's responsible for the governance, not the execution activities, and ultimately it is there to support the change owner in the implementation of a successful change. Then we have wiring and port location. So wiring and port location documentation allows you to track cable runs from switches and map them to the actual wall jacks where users connect to your network. These connections might also represent trunks to additional network devices, such as wireless access points. And we have IDF, MDF documentation. So an intermediate distribution frame. This is a distribution frame in a central office or customer premises, which cross connects the user cable media to individual user line circuits and may serve as a distribution point for multi-pair cables from the main distribution frame to individual cables connected to equipment in areas remote from those frames. Diagrams are also crucial for IDFs and MDFs. These distribution and core facilities house critical network data and devices, and proper documentation can aid in all forms of maintenance and security. Next, we have labeling. So proper labeling and diagrams, as well as on physical equipment, can ensure that such documentation is as useful as possible. Today's networks and data centers house a large number of diverse bandwidth-related devices. These devices are interconnected by networking equipment. So a systematic labeling scheme will provide transmission pathways for mission-critical data to flow across the entire network infrastructure. Then we have network configuration and performance baseline. So documenting base configurations for network devices, as well as capturing data utilization and bandwidth consumption during normal business operations, might also include taking service level agreement measurements during this time. Without this baseline information, it could be nearly impossible to gauge subtle performance problems. Then we have inventory management. So network inventory management, this is the process of keeping records of all the IT or network assets that make up the network. It enables network administrators or businesses to have a physical record of all IT and network equipment within the organization. And network inventory may include the following. It can include the number of routers, their make, type, and place of installation, and their serial numbers, IP addresses of all devices and nodes, IP addressing schemes that are used, number and type of software, along with the license keys and expiration dates. And this data helps businesses with the following. It can help with the network size estimation, network capacity planning, network cost ROI estimations, and physical network administrations to deal with device and equipment loss and theft. So in summary, we have talked about network management, documentation, and diagrams, where we discussed all of this wonderful information. In this video, you're going to learn about business continuity and disaster recovery concepts such as fault tolerance, high availability, load balancing, NIC teaming, port aggregation, clustering, power management, battery backup ups, dual power supplies, and redundant circuits. Let's talk about fault tolerance. So fault tolerance is the property that enables a system to continue operating properly in the event of the failure of one or more faults within some of its components. If its operating quality decreases at all, the decrease is proportional to the severity of the failure as compared to a naively designed system in which even a small failure can cause total breakdown. Fault tolerance is particularly sought after in high availability or life critical systems. A fault tolerance design enables a system to continue its intended operation, possibly at a reduced level rather than failing completely when some part of the system fails. The term is most commonly used to describe computer systems designed to continue more or less full operational with perhaps a reduction in throughput or an increase in response time in the event of some partial failure. That is, the system as a whole is not stopped due to problems either in the hardware or the software. Next, we have high availability, and this means that an IT system, component, or application can operate at a high level continuously without intervention for a given time period. High availability infrastructure is configured to deliver quality performance and handle different loads and failures with minimal or zero downtime. There are three principles of systems design and reliability engineering which can help achieve high availability. The first one is the elimination of a single point of failure. This means adding or building redundancy into the system so that failure of a component does not mean failure of the entire system. The next is reliable crossover. In redundant systems, the crossover point itself tends to become a single point of failure. Reliable systems must provide for reliable crossover. And the third is detection of failures as they occur. If the two principles above are observed, then the user may never see a failure, but the maintenance activity must. Next, we have load balancing, and this refers to the process of distributing a set of tasks over a set of resources, also known as computing units, with the aim of making their overall processing more efficient. Load balancing can optimize the response time and avoid unevenly overloading some compute nodes while other compute nodes are left idle. A load balancer may be one of the following. It could be a physical device, a virtualized instance running on specialized hardware, or a software process. It could be incorporated into application delivery controls designed to more broadly improve performance and security of three-tier web and microservices-based applications, regardless of where they're hosted. And it can be able to leverage many possible load balancing algorithms, including round robin, server response time, and the least connection method to distribute traffic in line with current requirements. Next, we have NIC teaming, so network interface card teaming. This allows you to combine multiple physical network adapters into a virtual NIC, which will then be presented to the operating system as a single NIC. All the traffic being sent from the OS will pass through the virtual NIC and be load balanced across the assigned physical network connections. The benefit of NIC teaming stem from its load balancing capabilities, efficiently breaking up network traffic across multiple connections, better utilizes network resources, ensures the availability of servers, and increases bandwidth. It also helps simplify network configuration. Next, we have port aggregation, also known as link aggregation, and this is the combining of multiple network connections in parallel by any of several methods in order to increase throughput beyond what a single connection could sustain to provide redundancy in case one of the links should fail or both. A link aggregation group is the combined collection of physical ports. Other umbrella terms used to describe the concept include trunking, bundling, channeling, or teaming. Essentially, port link aggregation increases the bandwidth and resilience of Ethernet connections. Next, we have clustering, and this refers to the interconnection of servers in a way that makes them appear to the operating environment as a single system. As such, the cluster draws on the power of all the servers to handle the demanding processing requirements of a broad range of technical applications. It also takes advantage of parallel processing in program execution. Shared resources in a cluster may include physical hardware devices, such as disk drives and network cards, TCP/IP addresses, entire applications, and databases. The cluster service is a collection of software on each node that manages all cluster-specific activity, including traffic flow and load balancing. The nodes are linked together by standard Ethernet, FIDI, ATM, or fiber channel connections. Now, the advantages of clustering are as follows. You have performance. So throughput and response time are improved by using a group of machines at the same time. The next is availability. If one node fails, the workload is redistributed among the other nodes for uninterrupted operation. You have incremental growth. Performance and availability can be enhanced by adding more nodes to the cluster. You have scaling. Theoretically, there is no limit on the number of machines that can belong to the cluster. And then you have price and performance. The individual nodes of a cluster typically offer very good performance for their price because clustering does not involve the addition of expensive high-performance processors, buses, or cooling systems. The cluster retains the price performance advantage of its individual members. Next, we have power management, and this is a feature of some electrical appliances, especially copiers, computers, CPUs, GPUs, and computer peripherals, such as monitors and printers that turn off the power or switches the system to a low power state when inactive. active. In computing, this is known as PC power management. Power management for computer systems is desired for many reasons, such as the reduction in overall energy consumption, prolonging the battery life for portable and embedded systems, a reduction in cooling requirements, a reduction in noise, and a reduction in operating costs for energy and cooling. Then we have battery backups and ups, or uninterruptible power supply. So an uninterruptible power supply, this is an electrical apparatus that provides emergency power to a load when the input power source or mains power fails. And ups is typically used to protect hardware such as computers, data centers, telecommunication equipment, or other electrical equipment where an unexpected power disruption could cause injuries, fatalities, serious business disruptions, or data loss. And ups differ from an auxiliary or emergency power system or standby generator in that it will provide near instantaneous protection from input power interruptions by supplying energy stored in batteries. Next, we have a dual power supply, and this is a regular direct current power supply. It can provide a positive as well as a negative voltage. It ensures stable power supply to the devices as well as it helps to prevent system damage. Many electronic circuits require a source of DC power. A dual power supply is used to power the electronic as well as electrical equipment. The dual power supply provides positive as well as negative potential with the ground. Many electronic circuits consist of tubes or transistors, and they require a DC power source. And then we have redundant circuits. So redundant circuits, also known as network redundancy, this is the process through which additional or alternate instances of network devices, equipment, and communication mediums are installed within network infrastructure. It is a method for ensuring network availability in case of a network device or path failure and unavailability. As such, it provides a means of network failover. Typically, network redundancy is achieved through the addition of alternate network paths, which are implemented through redundant standby routers and switches. When the primary path is unavailable, the alternate path can be instantly deployed to ensure minimal downtime and continuity of network services. So in summary, this was my quick little class on business continuity and disaster recovery, where we talked about fault tolerance, high availability, load balancing, NIC teaming, port aggregation, clustering, power management, battery backups and ups, dual power supplies, and redundant circuits. In this video, you're going to learn about business continuity and disaster recovery concepts such as cold sites, warm sites, hot sites, various types of backups, snapshots, MTTR, MTBF, and SLA requirements. Let's talk about disaster recovery. So disaster recovery sites are sites where IT functions can be set up when a disaster prevents the use of the original location. These fall into three categories. You have a cold site. A cold site, it has power, HVAC, and network connections, but would need equipment and data before it could be used for IT functions. This is the least expensive to maintain before a disaster, but takes the longest time to set up during a disaster. Next, we have a warm site, and this is a site that has power, HVAC, network, and hardware that are suitable for IT functions. Systems at a warm site might need to have operating systems, apps, and data restored, or operating systems and apps that could already be installed to save time. A warm site costs more than a cold site and will require ongoing maintenance of hardware and possibly software, but could be made ready in hours rather than days compared to a cold site. And then we have a hot site, and this is a duplicate of your primary IT functions with hardware, apps, and data ready to run in minutes or less in the event of a disaster. This is the most expensive of the three disaster recovery plans, but for an organization that cannot afford any downtime, it might be the only one that is worth considering. Let's talk about backup. So when hardware fails, you can purchase replacements, but when storage devices fail, the data is lost unless you have backup copies. A backup is a copy of information stored on a computing device, such as a laptop, desktop, server, or a mobile device, and a backup can be restored in the event of data loss. A backup copy of information on a system can be used by the system in case the original is lost or corrupted. And there are many backup methods designed for different requirements, and the following are some type of backup methods that are used. And the first type of backup is a full backup, and this backs up all files, whether they are backed up previously or not. When the file is backed up, a file attribute known as the archive bit is changed to indicate the file has been backed up. Next, we have a differential backup, and this backs up all files that have been changed since the last full backup. And then you have an incremental backup, and this backs up only the files that have been changed since the last full or incremental backup. Now, understand a differential backup and an incremental backup are two different methods of backing up only changed files. If incremental backups are used between full backups, in the event that a full restoration is needed, the last full backup and all incremental backups must be restored. However, if differential backups are used between full backups, only the last full backup and the last differential backup must be restored. Let's talk about snapshots. So a snapshot, this is a record comprised of metadata that indicates the state of blocks and files in a unit of storage. Often snapshots come as a feature of NAS or network attached storage or SAN storage area networks, and are created and held on that storage. They allow the user to roll back to previously existing versions of a volume, drive, file system, database, etc. Snapshots are like a point-in-time copy or table of contents that shows which blocks and or files existed and where. In the case of rolling back, the volume or unit of storage in question will be changed to a state that reflected the snapshot by removal and movement of blocks, etc. Also, snapshots are not backups because they are not copies. They don't take up as much space individually, but their total volume can grow, especially if there are lots of deleted blocks and files. And so suppliers usually limit the amount of snapshots that can be retained. Next, we have MTTR, or mean time to repair. So mean time to repair, this is a basic measure of the maintainability of repairable items. It represents the average time required to repair a failed component or device. Expressed mathematically, it is the total corrective maintenance time for failures divided by the total number of corrective maintenance actions for failures during a given period of time. Next, we have MTBF, or mean time between failures. So mean time between failures, this is the predicted elapsed time between inherent failures of a mechanical or electronic system during normal system operation. MTBF can be calculated as the average time between failures of a system. The term is used for repairable systems, while MTTF, or mean time to failure, denotes the expected time to failure for a non-repairable system. The definition of MTBF depends on the definition of what is considered a failure. For complex repairable systems, failures are considered to be those out of design conditions which place the system out of service and into a state of repair. Failures which occur that can be left or maintained in an unrepaired condition and do not place the system out of service are not considered failures under this definition. In addition, units that are taken down for routine scheduled maintenance or inventory control are not considered within the definition of failure. The higher the MTBF, the longer a system is likely to work before failing. And then we have service level agreement. So an SLA, this is a commitment between a service provider and a client. Particularly aspects of the service such as quality, availability, and responsibilities are agreed between the service provider and the service user. The most common component of an SLA is that the services should be provided to the customer as agreed upon in the contract. As an example, ISPs will commonly include SLAs within the terms of their contracts with customers to define the levels of service being sold in plain language terms. In this case, the SLA will typically have a technical definition and mean time between failures, mean time to repair, or mean time to recovery, identifying which party is responsible for reporting faults or paying fees, responsibility for various data rates, throughput, jitter, or similar measurable details. All right, so this was my quick little class on business continuity and disaster recovery, where we have talked about things such as cold, warm, and hot sites, various types of backups, snapshots, MTTR, MTBF, and SLA requirements. In this video, you're going to learn about network process monitoring, such as log reviewing, port scanning, vulnerability scanning, patch management and rollbacks, reviewing baselines, and packet traffic analysis. Let's talk about log reviewing. So log analysis, this is the process of reviewing, interpreting, and understanding computer-generated records called logs. Logs are generated by a range of programmable technologies, including networking devices, operating systems, applications, etc. A log consists of a series of messages and time sequence that describe activities going on within a system. Log files may be streamed to a log collector through an active network, or they may be stored in files for later review. Either way, log analysis is the delicate art of reviewing and interpreting these messages to gain insight into the inner workings of the system. Next, we have port scanning, and this is a method of determining which ports on a network are open and could be receiving or sending data. It is also a process for sending packets to specific ports on a host and analyzing responses to identify vulnerabilities. This scanning can't take place without first identifying a list of active hosts and mapping those hosts to their IP addresses. This activity, which is also called host discovery, starts by doing a network scan. The goal behind port and network scanning is to identify the organization of IP addresses, hosts, and ports to properly determine open or vulnerable server locations and diagnose security levels. Both network and port scanning can reveal the presence of security measures in place, such as a firewall between the server and the user's device. Next, we have vulnerability scanning. So a vulnerability scanner, this is a computer program designed to assess computers, networks, or applications for known weaknesses. These scanners are used to discover the weaknesses of a given system. They are utilized in the identification and detection of vulnerabilities arising from misconfigurations or flawed programming within a network-based asset such as a firewall, router, web server, application server, etc. Modern vulnerability scanners allow for both authenticated and unauthenticated scans. Modern scanners are typically available as a software as a service, which is provided over the internet and delivered as a web application. The modern vulnerability scanner often has the ability to customize vulnerability reports, as well as the installed software, open ports, certificates, and other host information that can be queried as part of its workflow. Then we have patch management, and this is the process of distributing and applying updates to software. These patches are often necessary to correct errors such as vulnerabilities or bugs in the software. Common areas that will need patches include operating systems, applications, and embedded systems like network equipment. When a vulnerability is found after the release of a piece of software, a patch can be used to fix it. Doing so helps ensure that assets in your environment are not susceptible to exploitation. And then you have this thing called a rollback. This gives you the mechanism to remove patches after they have been installed on the system. And not all patches may be uninstalled, and the system will only list patches that support a rollback. Next, we have network baseline. So network baselining, this is the act of measuring and rating the performance of a network in real-time situations. Providing a network baseline requires testing and reporting of the physical connectivity, normal network utilization, protocol usage, peak network utilization, and average throughput of the network usage. Such in-depth network analysis is required to identify problems with speed and accessibility, and to find vulnerabilities and other problems within the network. Once a network baseline has been established, this information is then used by companies and organizations to determine both present and future network upgrade needs, as well as assist in making changes to ensure their current network is optimized for peak performance. And then we have packet and traffic analysis. So a packet analyzer or a packet sniffer, this is a computer program or computer hardware, such as a packet capture appliance, that can intercept and log traffic that passes over a computer network or part of a network. Packet capture is the process of intercepting and logging traffic. As data streams flow across the network, the analyzer captures each packet and, if needed, decodes the packet's raw data, showing the values of various fields in the packet, and analyzes its contents according to the appropriate RFC or other specifications. A packet analyzer used for intercepting traffic on wireless networks. This is known as a wireless analyzer or a Wi-Fi analyzer, and a packet analyzer can also be referred to as a network analyzer or protocol analyzer, though these terms also have other meanings. All right, so in summary, that was my quick little class on process monitoring, where we talked about network process monitoring, such as log reviewing, port scanning, vulnerability scanning, patch management and rollbacks, reviewing baselines, and packet and traffic analysis. In this video, you're going to learn about network event management, SIEM, SNMP monitors, and network performance metrics such as bandwidth, throughput, packet drops, error rate, and utilization. Let's talk about event management. This is the process that monitors all events that occur through the IT infrastructure. It allows for normal operations and also detects and escalates exception conditions. An event can be defined as any detectable or discernible occurrence that has significance for the management of the IT infrastructure or the delivery of IT service and evaluation of the impact a deviation might cause to the services. Events are typically notifications created by an IT service or monitoring tool, and the purpose of event management is the following. It has the ability to detect events, investigate, and determine the correct control action. The events, such as warnings and exceptions, can be used to automate many routine activities. It can provide mechanisms for early detection of incidents, and some types of automated activities can be monitored by exception, which reduces downtime. Next, let's talk about SIEM. So, Security Information and Event Management Technology supports threat detection, compliance, and security incident management through the collection and analysis, both near real-time and historical, of security events, as well as a wide variety of other event and contextual data sources. The core capabilities are a broad scope of log event collection and management, the ability to analyze log events and other data across disparate sources, and operational capabilities such as incident management, dashboards, and reporting. Let's talk about SNMP, which stands for Simple Network Management Protocol. So SNMP, this is an internet standard protocol for collecting and organizing information about managed devices on IP networks and for modifying that information to change device behavior. Devices that typically support SNMP include cable modems, routers, switches, servers, workstations, printers, etc. SNMP is widely used in network management for network monitoring. SNMP exposes management data in the form of variables on the managed systems organized in the management information base, which describe the system status and configuration. These variables can then be remotely queried and in some circumstances manipulated by managing applications. Let's talk about network performance metrics. So network performance monitoring, this is the process used to track, evaluate, and diagnose the performance of a network. With the variety of devices, technologies, and network environments continuing to expand, the definition of optimal performance can vary significantly. Network performance metrics are the measurable outputs that indicate how the infrastructure and services are operating as a part of a short-term and long-term network performance evaluations. Real-time analysis of these metrics allows teams to identify potential problems on the network and prioritize IT resources in response according to impact. Over time, network performance metrics support a long-term understanding of end-user demands and help in building an adaptive network that meets future business needs. And some of the network performance metrics that you need to become familiar with are bandwidth. And this is the maximum data transmission rate possible on a network. For optimal network operations, you want to get as close to your maximum bandwidth as possible without reaching critical levels. This indicates that your network is sending as much data as it can within a period of time, but it is not being overloaded. And the next one is throughput. And this measures your network's actual data transmission rate, which can vary widely through different areas of your network. While your network's bandwidth measures the theoretical limit of data transfer, throughput tells you how much data is actually being sent. Specifically, throughput measures the percentage of data packets that are successfully being sent. A low throughput means there are a lot of failed or dropped packets that need to be sent again. And the next one is packet drops. And this examines how many data packets are dropped during data transmissions on your network. The more data packets that are lost, the longer it takes for a data request to be fulfilled. And then we have error rate, and this is the frequency with which errors or noise are introduced into the channel. Error rates may be measured in terms of erroneous bits received per bits transmitted. And then finally, we have utilization. Network utilization, this is the proportion of the current network traffic to the maximum amount of traffic that can be handled. It indicates the bandwidth consumption in the network. While high network traffic means the network is overloaded, low network traffic means that the network is not busy. If the network load reaches or exceeds the threshold under normal conditions, this will result in low network speed, interruptions, timeouts, etc. The network load is an indicator of the network utilization. All right, so that was my short little class on network event management and metrics, where we talked about network event management, SIEM, SNMP monitors, and network performance metrics such as bandwidth, throughput, packet drops, error rate, and utilization. In this video, you're going to learn about remote access methods such as VPN, RDP, SSH, VNC, Telnet, HTTPS, URL management, remote file access, and out-of-band management. Let's talk about a VPN. So, a virtual private network. This extends a private network across a public network and enables users to send and receive data across shared or public networks as if their computing devices were directly connected to the private network. A VPN connection requires a VPN server at the remote site and a VPN client at the client site. VPN traffic between client and server is encrypted and encapsulated into packets suitable for transmission over the network. VPN connections are often referred to as tunnels, and the process of setting up a VPN is known as tunneling. And a VPN connection has several benefits compared with a standard connection. The first benefit is a VPN connection enables insecure public Wi-Fi to provide a secure private connection to a website that supports VPNs. A VPN connection enables the user to bypass blocks on websites in certain areas. By using a VPN, a user can access social networks or search tools in countries where access is restricted, or can use media subscription sites for areas other than where they live, such as a different country's Netflix or other streaming service. And a VPN connection hides activity from the user's normal ISP because their internet traffic, including P2P torrents or peer-to-peer torrents, is tunneling through the ISP's connections and is therefore invisible. Next, we have IPsec, or Internet Protocol Security. So IPsec, this is a secure network protocol suite that authenticates and encrypts the packets of data to provide secured encrypted communication between two computers over an internet protocol network. It is used in VPNs. IPsec includes protocols for establishing mutual authentication between agents at the beginning of a session and negotiation of cryptographic keys to use during the session. IPsec can protect data flows between a pair of hosts, between a pair of security gateways, or between a security gateway and a host. IPsec uses cryptographic security services to protect communications over IP networks. It supports network level peer authentication, data origin authentication, data integrity, data confidentiality, also known as encryption, and replay protection. Next, we have SSL, or Secure Sockets Layer. So SSL, this is an encryption-based internet security protocol. It was first developed by Netscape in 1995 for the purpose of ensuring privacy, authentication, and data integrity in internet communications. SSL is the predecessor to the modern TLS encryption that is used today. A website that implements SSL TLS has the HTTPS in the URL instead of HTTP. Then we have TLS, or Transport Layer Security. So TLS, this is a widely adopted security protocol designed to facilitate privacy and data security for communications over the internet. A primary use of TLS is encrypting the communication between web applications and servers, such as web browsers loading a website. TLS can also be used to encrypt other communications such as email, messaging, and voice over IP. As previously mentioned, TLS evolved from an encryption called Secure Sockets Layer, or SSL, SSL, and due to this history, the terms TLS and SSL are sometimes used interchangeably. Next, we have DTLS, or Datagram Transport Layer Security. So DTLS, this is a communications protocol providing security to datagram-based applications by allowing them to communicate in a way designed to prevent eavesdropping, tampering, or message forgery. The DTLS protocol is based on the stream-oriented TLS protocol and is intended to provide similar security guarantees. The DTLS protocol datagram preserves the semantics of the underlying transport, which is the application does not suffer from the delays associated with stream protocols, but because it uses UDP or SCTP and not TCP, the application has to deal with packet reordering, loss of datagram, and data larger than the size of a datagram network packet. Site-to-site VPN. So this is a connection between two or more networks, such as a corporate network and a branch office network. Many organizations use site-to-site VPNs to leverage an internet connection for private traffic as an alternative to using private MPLS circuits. Site-to-site VPNs are frequently used by companies with multiple offices in different geographic locations that need to access and use the corporate network on an ongoing basis. With a site-to-site VPN, a company can securely connect its corporate network with its remote offices to communicate and share resources with them as a single network. Then we have client-to-site VPN. So in a client-to-site VPN connection, clients from the internet can connect to the server to access the corporate network or LAN behind the server, but still maintain the security of the network and its resources. This feature is very useful since it creates a new VPN tunnel that would allow teleworkers and business travelers to access your network by using a VPN client software without compromising privacy and security. Then we have RDP, or Remote Desktop Protocol. So this is a proprietary protocol developed by Microsoft, which provides a user with a graphical interface to connect to another computer over a network connection. The user employs RDP client software for this purpose, or remote desktop services, while the other computer must run RDP server software, or remote desktop connection. In RDP, it uses port 3389. Next, we have SSH, or Secure Shell. So SSH, this is a cryptographic network protocol for operating network services securely over an unsecured network. SSH is more secure than FTP and Telnet. Typical applications include remote command line, login, and remote command execution, but any network service can be secured with SSH. SSH servers housing data a client wants to retrieve uses port 22 and we need to have that port open to get access to that data. As previously mentioned, regular FTP is an insecure port, whereas secure FTP, or SFTP, is secure by way of utilizing TCP port 22 as it runs over an SSH session. VNC, or Virtual Network Computing. So VNC, this is a graphical desktop sharing system that uses the Remote Frame Buffer protocol to remotely control another computer. It transmits the keyboard and mouse input from one computer to another, relaying the graphical screen updates over a network. VNC is platform independent, meaning there are clients and servers for many GUI-based operating systems, and for Java, multiple clients may connect to a VNC server at the same time. Popular uses for this technology include remote technical support and accessing files on one's work computer from one's home computer, or vice versa. Next, we have Telnet, and this is an application protocol used on the internet or local area network to provide a bidirectional, interactive, text-oriented communication facility using a virtual terminal connection. A Telnet emulation enables a user to connect to a remote host or device using a Telnet client over port 23. A Telnet connection allows for a user to Telnet into a computer that hosts their website to manage their files remotely versus simply downloading pages and files as he or she would with an HTTP or FTP connection. Before a Telnet connection from a client can be established, a remote computer must already be configured to accept the Telnet login on port 23, and that port must be open before a login can take place. To utilize the Telnet command prompt on Windows or Linux computers by way of a command line Telnet program, you would have to open a connection to a remote computer, followed by opening a command prompt in Windows or a terminal session in Linux, and then typing telnet and then pressing the enter key. HTTPS, or Hypertext Transfer Protocol Secure. So HTTPS, this is an extension of the Hypertext Transfer Protocol, or HTTP. It is used for secure communication over a computer network and is widely used on the internet. In HTTPS, the communication protocol is encrypted using TLS, or the formerly SSL. The protocol is therefore also referred to as HTTP over TLS or HTTP over SSL. The principal motivations for HTTPS are authentication of the access website and protection of the privacy and integrity of the exchange data while in transit. It protects against man-in-the-middle attacks, and the bidirectional encryption of communications between the client and server protect the communications against eavesdropping and tampering. Next, we have management URL, and URL stands for Uniform Resource Locator. So a URL, which is also known as a web address, this is a reference to a web resource that specifies its location on a computer network and a mechanism for retrieving it. A URL is a specific type of Uniform Resource Identifier, although many people use the two terms interchangeably. URLs occur most commonly to reference web pages such as HTTP, but are also used for file transfer or FTP, emails, database access, and many other applications. In URL management, it controls the technical configuration of a domain, such as the assignments of URLs to websites, the redirection from one URL to another, a change to a URL, and vanity host names through third-party vanity URLs, which basically redirect the visitor from one URL website to another link. Remote file access. So this is a service that lets you access files anywhere, anytime, and with whatever device you like, as long as you're connected to the internet. The types of remote file access that you need to be concerned about for the Network Plus N10-007 exam are the following. You have FTP and FTPS, or File Transfer Protocol, or FTP secured with SSL or TLS. The File Transfer Protocol, this is a standard network protocol used for the transfer of computer files between a client and a server on a computer network. FTP is also used by web browsers. To access an FTP site, you would use the prefix FTP. Windows, Linux, and Mac, they contain a command line FTP program. You would just simply type FTP, press enter, and then type help at the FTP prompt to see the commands that you can use. Also, FTP sites with downloads available to any user, they support anonymous FTP. An anonymous FTP is a means by which archive sites allow general access to their archives of information. These sites create a special account called Anonymous, and user Anonymous has limited access rights to the archive host, as well as some operating restrictions. Some FTP sites require the user to log in with a specified username and password. One drawback to FTP is that it is not considered secure due to FTP login credentials being transmitted and authenticated in clear text. To increase security, you would use FTP secured with SSL or TLS, also known as FTPS, or Secure File Transfer Protocol, SFTP, and also FTP, it uses port 21. Next, you have SFTP, or SSH File Transfer Protocol, or Secure FTP. So SFTP, this is a network protocol that provides file access, file transfer, and file management over any reliable data stream. It was designed as an extension of the SSH protocol to provide secure file transfer capabilities. This protocol is used in a number of different applications, such as secure file transfer over TLS and transfer of management information in VPN applications. The SFTP protocol allows for a range of operations on remote files, which makes it more like a remote file system protocol. And SFTP client's extra capabilities include resuming interrupted transfers, directory listings, and remote file removal. Then we have TFTP, or Trivial File Transfer Protocol. And this is a simple lockstep file transfer protocol which allows a client to get a file from or put a file onto a remote host. And one of its primary uses in the early stages of nodes booting from a LAN, TFTP has been used for this application because it is very simple to to implement. Due to its simple design, TFTP can be easily implemented by code with a small memory footprint. It is therefore the protocol of choice for the initial stages of any network booting strategy like BootP, PXE, BSDP, etc. when targeting from highly resourced computers to very low resource single board computers and systems on a chip. It is also used to transfer firmware images and configuration files to network applications like routers, firewalls, IP phones, etc. Today, TFTP is virtually unused for internet transfers. And then we have out-of-band management. So out-of-band management involves the use of management interfaces or serial ports for managing and dealing with networking equipment. Out-of-band management allows the network operator to establish trust boundaries in accessing the management function to apply it to network resources. It can also be used to ensure management connectivity, including the ability to determine the status of any network component independent of the status of other in-band network components. One form of out-of-band management is sometimes called lights out management, or LOM, and involves the use of a dedicated management channel for device maintenance. It allows a system administrator to monitor and manage servers and other network attached equipment by remote control, regardless of whether the machine is powered on or whether it is installed or functional. All right, so this was my class on remote access methods, where we talked about VPNs, RDP, SSH, VNC, Telnet, HTTPS, URL management, remote file access, and out-of-band management. In this video, you're going to learn about network policies and best practices such as privileged user agreements, password policies, onboarding and offboarding procedures, licensing restrictions, international export controls, data loss prevention, remote access policies, incident response policies, bring your own device, acceptable user policies, system life systems, and safety procedures and policies. Let's talk about privileged user agreements. So a privileged user agreement, this enables an individual to take actions that may affect computing systems, network communications, or other accounts, files, data, and processes of other users. Privileged access is typically granted to system administrators, network administrators, staff performing computing, account administration, or other such employees whose job duties require special privileges over a computing system or network. A privileged user agreement might stipulate the following, such as privileged access should be granted only to authorized individuals who read and sign the agreement. Privileged access may be used only to perform assigned job duties. If methods other than using privileged access will accomplish an action, those other methods must be used unless the burden of time or other resources required clearly justifies using privileged access. Privileged access may be used to perform standard system-related duties only on machines and networks whose responsibility is part of the assigned job duties, and privileged access may be used to grant, change, or deny resources, access, or privilege to another individual only for authorized account management activities under exceptional circumstances. Next, we have a password policy, and this is a set of rules designed to enhance computer security by encouraging users to employ strong passwords and use them properly. A password policy is often part of an organization's official regulations and may be taught as part of security awareness training. Either the password policy is merely advisory or the computer systems force users to comply with it. A strong password policy should include the following elements, such as education for end users, strong password requirements such as minimum password lengths, restrictions on the use of proper names, password expirations, no previously used passwords allowed, no words spelled out completely within the password, and the use of characters from the following groups such as upper and lowercase letters, numbers and special characters, and implementing the use of a password manager should also be considered. This software can store passwords for different resources and can even help users generate complex passwords across these resources. Let's talk about onboarding, offboarding procedures. So employee onboarding is a series of tasks that help a chosen candidate become an integrated and functioning member of an organization. Good employee onboarding goes beyond conventional paperwork. It should provide the tools and resources new employees need to become satisfied and productive team members quickly. A good employee onboarding program maximizes productivity by outlining job and organization expectations, reducing errors, and saving time and frustration. A standard employee onboarding might include the following, such as an ID number and PIN assignment, username and password assignment, ID card and access assignments, email mailbox setup, email client setup, workstation setup, workstation network access verification, IT security and best practices training, phone and bring your own device setup, and time management and other HR software training. Employee offboarding. This is the strategic process of disengaging an employee from your workforce. In other words, it initiates the formal separation between the employer and the employee. The process begins with an exit interview conducted by the HR team. Although the HR team is the one that initiates the offboarding process, the IT department is the one who needs to see it through to prevent an outgoing employee from turning into a malicious insider. Next, we have licensing restrictions. So you may also need to provide training in the proper licensing and use of corporate hardware and software. As networks have become more complex, so have licensing agreements. It is important that users remain in compliance with all existing licensing agreements and restrictions. International export controls. So another important best practice is to educate IT staff and end users on the international export rules your organization must observe. Using the U.S. government as an example, specific agencies regulate the transfer of information, commodities, technology, and software considered to be strategically important to the U.S. in the interest of national security, economic, and/or foreign policy concerns. Your management must understand that non-compliance with export controls can result in severe monetary and criminal penalties against both an individual in your company as well as the organization itself. Next, we have data loss prevention, and this is software that detects potential data breaches or data exfiltration transmissions and prevents them by monitoring, detecting, and blocking sensitive data while in use, which is known as endpoint actions, in motion or network traffic, and at rest, which is known as data storage. Most DLP policies focus on the use of content level scanning and deep content inspection to identify sensitive data and protect it. The following actions should be considered when designing a DLP policy, such as consider any risk assessments your company has performed, incorporate key members of management from the various departments of your organization, identify the most sensitive data of the organization, outline a phased implementation of DLP, and incorporate guidelines for tracking success of the initiative, attempt to minimize any negative impacts on the business caused by the policy implementation, periodically review the DLP policy, and include the appropriate event monitoring specifics as they apply to the policy. Next, we have remote access policies. So a remote access policy, this is a document which outlines and defines acceptable methods of remotely connecting to the internal network. It is essential in large organizations where networks are geographically dispersed and extend into insecure network locations, such as public networks or unmanaged home networks. A remote access policy should cover all available methods to remotely access internal resources such as dial-in, ISDN, frame relay, telnet access from the internet, and cable modems. Other remote access policies that you should consider are the scope of the policy should be clear and may include applicable targets such as employees, contractors, vendors, and agents with company-owned or personally owned computers or workstations used to connect to the corporate network. Clearly detailed requirements of the policy itself, which might include encryption and security standards, as well as the acceptable areas of network access. Sections regarding compliance, which could include exceptions to the policy, the measurements for compliance, and the consequences of non-compliance, and a section that indicates what other security policies for the network closely relate to this policy. Incident response policy. So an incident, as defined in the National Institute of Standards and Technology, also known as NIST, NIST, this is a violation or imminent threat of violation of computer security policies, acceptable use policies, or standard computer security practices. An incident response capability is necessary for rapidly detecting incidents, minimizing loss and destruction, mitigating the weaknesses that were exploited, and restoring computing resources. Because security issues are inevitable for a network, it is critical to prepare a comprehensive incident response policy. And such a policy might outline various phases of an an incident response plan, including the following. So the first one is you want to prepare, and this involves being able to identify the start of an incident, preparing a recovery plan, how to get everything back to normal, and creating established security policies. Next, you want to identify. This is identifying the actual security incident. Next, you want to contain. This involves protecting and keeping available critical and computing resources and determining the operational status of the infected computer, system, or network. The goal is to limit the security incident from spreading. Next, you want to eradicate. This deals with the removal of the attack or infection. Next is recover. This involves service restoration as well as recertification of network devices and systems. And then you want to review. So all phases should be analyzed in the review to gauge their effectiveness and modify the incident response policy as needed for the future. And then we have BYOD, or bring your own device. And this refers to being allowed to use one's personally owned device rather than being required to use an official provided device. There are two major contexts in which this term is used. One is in the mobile phone industry, where it refers to carriers allowing customers to activate their existing phone on the network rather than being forced to buy a new device from the carrier. The other is in the workplace, where it refers to a policy of permitting employees to bring personally owned devices such as laptops, tablets, smartphones, etc. to work, and to use those devices to access privileged company information and applications. And a BYOD policy should incorporate the following. It should have an explicit and detailed list of what devices are actually permitted, an explicit security policy for each device or device category, the appropriate corporate support policy for each device or device category, a clear delineation of what applications and data are owned by the corporation versus that owned by the user and or employee, an explicit list of applications permitted in the BYOD environment, an integration of the BYOD policy and the acceptable use policy, and a detailed presentation of the exit policies for employees as they relate to BYOD. Next, we have an AUP, or an acceptable use policy. So an acceptable use policy, this is a set of rules applied by the owner, creator, or administrator of a network, website, or service that restricts the ways in which the network, website, or system may be used and sets guidelines as to how it should be used. AUP documents are written for corporations, businesses, universities, schools, internet service providers, and website owners, often to reduce the potential for legal action that may be taken by a user, and often with little prospect of enforcement. An AUP should be the following. It should be clear, concise, detailed regarding acceptable and unacceptable use of the network, congruent with the associated overall security policies of the organization, concrete regarding consequences of AUP violations. Also, it should be updated and reviewed regularly. Next, we have an NDA, or a non-disclosure agreement. So an NDA, this is a legal contract or part of a contract between at least two parties that outlines confidential material, knowledge, or information that the parties wish to share with one another for certain purposes, but wish to restrict access to. In other words, it is a contract through which the parties agree not to disclose any information covered by the agreement. An NDA creates a confidential relationship between the parties, typically to protect any type of confidential and proprietary information or trade secrets. In NDAs, they are quite common for employees to sign during the onboarding process. Next, we have the system lifecycle. So a system lifecycle, this is also referred to as the application development lifecycle. And this is a process for planning, creating, testing, and deploying an information system. The systems development lifecycle concept applies to a range of hardware and software configurations, as a system can be composed of hardware only, software only, or a combination of both. And the usual stages of this life cycle are the following. You have the requirement analysis, design, development and testing, implementation, documentation, and evaluation. And then we have safety procedures and policies. So some safety policies and procedures for the networking equipment in your organization should include the following commonalities. You should be following the installation and maintenance guides for the equipment as closely as possible. You need to keep all work areas as clean and organized as possible. You need to wear appropriate safety equipment. You need to seek assistance when lifting heavy network objects. You need to exercise caution when interacting with electricity, and you need to avoid other risks of electric shock. All right, so in summary, ladies and gentlemen, this has been my class on network policies and best practices, where we talked about privileged user agreements, password policies, onboarding and offboarding procedures, licensing restrictions, international export controls, data loss prevention, remote access policies, incident response policies, BYOD, AUP, NDA, system life cycles, and safety procedures and policies. In this video, you're going to learn about physical security devices such as motion detectors, video surveillance, asset tracking tags, tamper detection, badges, biometrics, smart cards, key fobs, and locks. Let's talk about motion detection. So motion detection, this is the process of detecting a change in the position of an object relative to its surroundings, or a change in the surroundings relative to an object. It can be achieved by either mechanical or electronic methods, and motion can be detected by monitoring changes in the following, such as infrared light by way of passive and active sensors, visible light by way of video and camera systems, radio frequency energy such as radar and microwave motion detection, sound such as microphones or other acoustic sensors, kinetic energy such as seismic sensors, magnetism where you have magnetic sensors, and by way of Wi-Fi signals. Next, we have video surveillance, and this is also known as closed circuit TV. And this is the use of video cameras to transmit a signal to a specific place on a limited set of monitors. It differs from broadcast television in that the signal is not openly transmitted, though it may employ point-to-point, point-to-multipoint, or mesh wired or wireless links. Even though almost all video cameras fit this description, the term is most often applied to those used for surveillance in areas that require additional security or ongoing monitoring. Next, we have asset tracking tags. So asset tracking, this refers to the method of tracking physical assets, either by scanning barcode labels attached to the assets or by using tags using GPS or RFID, which broadcast their location. These technologies can also be used for indoor tracking of persons wearing a tag. Passive RFID tags broadcast their location but have limited transmission range, which is typically only a few meters. Longer range smart tags, they use active RFID, where a radio transmitter is powered by a battery and can transmit up to about 2,000 meters in optimum conditions. RFID-based asset tracking requires an infrastructure to be put in place before the whereabouts of tags may be ascertained. An asset tracking system can record the location and usage of the assets and generate various reports. Next, we have tamper detection, and this is the ability of a device to sense that an active attempt to compromise the device integrity or the data associated with the device is in progress. The detection of the threat may enable the device to initiate an appropriate defense action as well. Let's talk about badges. So an access badge, this is a credential used to gain entry to an area having automated access control entry points. Entry points may be doors, turnstiles, parking gates, or other barriers. Access badges use various technologies to identify the holder of the badge to an access control system. The most common technologies are magnetic stripes, proximity cards, barcode readers, smart cards, and various biometric devices. Biometrics. So a biometric device is a security identification and authentication device. Such devices use automated methods of verifying or recognizing the identity of a living person based on physiological or behavioral characteristics. These characteristics include fingerprints, facial images, iris, and voice recognition. Smart cards, and this is a physical electronic authorization device used to control access to a resource. It is typically a plastic credit card sized card with an embedded integrated chip. Many smart cards include a pattern of metal contacts to electrically connect to the internal chip. Others are contactless and some are both. Smart cards can provide personal identification, authentication, data storage, and application processing. Applications include identification, financial, mobile phone, public transit, computer security, schools, and healthcare. Smart cards may provide strong security authentication for single sign-on within organizations. organizations as well. Then we have a key fob. So a key fob, this is also known as a hardware token. And this is an electronic lock that controls access to a building or vehicle without using a traditional mechanical key. They can contain RFID chips and may be used as part of a two-step authentication protocol that works as follows. The key fob generates a code every 30 to 60 seconds. Every time the code changes on the fob, it is also matched in an authentication server. The user logs into the system or restricted area using the generated access code displayed on the key's fob LCD display. The authentication server matches the current code and grants access. And then we have locks. So oftentimes the simplest forms of security are the most effective. And this is often the case with locks on all network areas and equipment. Door locks, biometric locks, laptop cable locks, server locks, USB locks are all simple yet effective mechanisms for helping to secure network devices. All right, so that was my little quick class on physical security devices where we talked about things such as motion detectors, video surveillance, asset tracking tags, tamper detection, badges, biometric smart cards, key fobs, and locks. In this video, you're going to learn about authentication and access controls such as Radius, TACACS Plus, Kerberos, SSO, local authentication, LDAP, certificates, auditing and logging, multi-factor authentication, and various access controls such as 802.1x, NAC, port security, MAC filtering, captive portals, and access control lists. So let's talk about Radius, and this stands for Remote Authentication Dial-In User Service. And this is a network protocol operating on ports 1812 and 1813 that provides centralized authentication, authorization, and accounting management for users who connect and use a network service. Users who want access to a network or an online service can contact a Radius server and provide a username and password to attempt to gain access. The server would then authenticate or decline access to the network or service. TACACS Plus, and this stands for Terminal Access Controller Access Control System, and this refers to a family of related protocols handling protocols for remote authentication and related services for network access control through a centralized server. The original TACACS protocol, which dates back to 1984, was used for communicating with an authentication server, which is common in older Unix networks. A user already authenticated via TACACS into the network was automatically logged into other resources in the system as well. TACACS in its original form is not very secure and has been updated and replaced by TACACS Plus, which is a proprietary form by Cisco Systems. Let's talk about Kerberos. So this is a computer network authentication protocol that works on the basis of tickets to allow nodes communicating over a non-secure network to prove their identity to one another in a secure manner. Kerberos was designed primarily for a client-server model to provide mutual authentication where both the user and server verify each other's identity. The client authenticates itself to the authentication server, which forwards the username to a key distribution center. The KDC issues a ticket granting ticket or TGT, which is time-stamped and encrypts it using the ticket granting service's secret key and returns the encrypted result to the user's workstation. This is done infrequently, typically at user login. The TGT expires at some point, although it may be transparently renewed by the user's session manager while they are logged in. Kerberos also uses UDP port 88 by default. Single sign-on, or SSO, and this is a property of access control of multiple related yet independent software systems. Some SSO implementations require the user to sign in just once, whereas others can detect the correct credentials when the user connects and performs a silent or promptless login. And some of the benefits and risks of SSO include the following. So some of the benefits are users have fewer username and password combinations to remember. Users get to work faster because they spend less time entering passwords. Users don't need to ask for assistance from help desk employees because of lost passwords. And SSO makes managing the security profiles of individual users easier. And some of the risks are as follows. A compromised SSO password puts all resources accessible with SSO at risk. A disgruntled employee with SSO access can cause problems with all resources accessible via SSO, and a lost or forgotten SSO password prevents the employee from doing any work until a new password is set up. Next, we have local authentication, and this refers to the network device authenticating the user with with a database of user account information stored on the device itself. This is often an important fallback method of authentication should another external method fail. Then we have LDAP. This stands for Lightweight Directory Access Protocol, and this is an open, vendor-neutral, industry-standard application for accessing and maintaining distributed directory information services over an IP network. Domain directory services play an important role in developing intranet and internet applications by allowing the sharing of information about users, systems, network services, and applications throughout the network. As such, directory services may provide any organized set of records, often with a hierarchical structure such as that of a corporate email directory, and Microsoft often refers to this as directory services, and LDAP, it uses port 389. Next, we have certificates. So in cryptography, a certificate authority, also known as a CA, this is an entity that issues digital certificates. A digital certificate certifies the ownership of a public key by the named subjects of the certificate. This allows others or relying parties to rely upon signatures or on assertions made about the private key that corresponds to the certified public key. A CA acts as a trusted third party, trusted by both the subject, who is the owner of the certificate, and by the party relying upon the certificate. Trusted certificates can be used to create secure connections to a server via the internet. A certificate is essential in order to circumvent a malicious party, which happens to be on the route to a target server, which acts as if it were the target. Such a scenario is commonly referred to as man-in-the-middle attacks. The client uses the CA certificate to authenticate the CA signature on the server certificate as part of the authorizations before launching a secure connection. Auditing and logging. So network auditing, this is the process of mapping and inventorying your network in terms of hardware and software. It's a fairly complex task that involves manually identifying network elements. In some cases, network auditing tools can provide automation support to identify the devices and services connected to the network. In addition to hardware and software, auditing should include security documentation, such as user accounts and groups, as well as permissions. A network log is typically a file that contains a record of events that occurred in an application. It contains the records of user and process access calls to objects, attempts to authentication, and other activities. Multi-factor authentication. This is an authentication method in which a computer user is granted access only after successfully presenting two or more pieces of evidence or factors to an authentication mechanism. Typically, multi-factor authentication works with some combination of the following, such as what the user knows, such as a password or a PIN, what the user has, a smart card or a fob, what the user is, biometric data, something the user does, such as handwriting or a signature, and where the user is, either a trusted or an untrusted location. Let's talk about some access controls, and the first one is 802.1x. So IEEE 802.1x, this is a port-based network access control. It provides authentication mechanisms to devices wishing to attach to a LAN or a wireless LAN. 802.1x authentication involves three parties. You have a supplicant, an authenticator, and an authentication server. The supplicant is a client device, such as a laptop, that wishes to attach to the LAN or the wireless LAN. The term supplicant is also used interchangeably to refer to the software running on the client that provides credentials to the authenticator. The authenticator is a network device that provides a data link between the client and the network and can allow or block network traffic between the two, such as Ethernet switch or wireless access point. And the authentication server is typically a trusted server that can receive and respond to requests for network access and can tell the authenticator if the connection is to be allowed, and various settings that should apply to the client's connection or setting. Authentication servers typically run software supporting the Radius and EAP protocols. In some cases, the authentication server software may be running on the authenticator's hardware. Next, we have NAC, or Network Access Control. So NAC, this is an approach to computer security that attempts to unify endpoint security technologies such as antivirus, host intrusion prevention, and vulnerability assessment, user or system authentication, and network security enforcement. NAC uses a set of protocols to define and implement a policy that describes how to secure access to network nodes by devices when they initially attempt to access the network. NAC might integrate the automatic remediation process process such as fixing non-compliant nodes before allowing access into the network system, allowing the network infrastructure such as routers, switches, and firewalls to work together with back office servers and end user computing equipment to ensure the information system is operating securely before interoperability is allowed. And a basic form of NAC is the 802.1x standard. Port security. So by default, all interfaces on a switch are turned on. That means that an attacker could connect to a network through a wall socket and potentially threaten the network. If you know which devices will be connected to which ports, a network admin can implement port security. By using port security, a network admin can associate specific MAC addresses with the interface, which can prevent an attacker from connecting his device. This way, an admin can restrict access to an interface so that only the authorized devices use it. If an unauthorized device is connected, an admin can decide what action the switch is to take, for example, discarding the traffic and shutting down the port. MAC filtering. So MAC, which stands for Media Access Control, MAC filtering refers to a security access control method whereby the MAC address assigned to each network card is used to determine access to the network. MAC addresses are uniquely assigned to each card, so using MAC filtering on a network permits and denies network access to specific devices through the use of blacklists and whitelists. While MAC filtering does give a network some additional protection, it can be circumvented by using a packet analyzer to find a valid MAC address and then using MAC spoofing software to access the network using that MAC address because MAC addresses are not encrypted. Next, we have Captive Portal, and this is a web page access with a web browser that is displayed to newly connected users of Wi-Fi or a wired network before they are granted broader access to network resources. Captive portals are commonly used to present a landing or login page, which may require authentication, payment, acceptance of an end-user license agreement, acceptable use policy, survey completion, or other valid credentials that both the host and user agree to adhere to. Captive portals are used for a broad range of mobile and pedestrian broadband services, including cable and commercially provided Wi-Fi and home hotspots. A captive portal can also be used to provide access to enterprise or residential wired networks, such as apartment houses, hotel rooms, and business centers. A captive portal is not a secure connection. However, if the terms of service listed are enforced by network configuration settings, for example, settings that block the use of a keyboard logger or remote control apps, then this will make it slightly more secure than an open network. And then we have an access control list. So an ACL, this is a list of permissions associated with a system resource or object. An ACL specifies which users or system processes are granted access to objects, as well as what operations are allowed on given objects. And there are two types of ACLs. The first one is a file system ACL, and this filters access to files and or directories. File system ACLs tell operating systems which users can access the system and what privileges the users are allowed. Then you have a networking ACL, and this filters access to the network. Networking ACLs tell routers and switches which type of traffic can access the network and which activity is allowed. All right, so that is my quick class on network authentication and access controls, where we talked about things such as Radius, TACACS Plus, Kerberos, SSO, local authentication, LDAP, certificates, auditing and logging, multi-factor authentication, and various access controls such as 802.1x, NAC, port security, MAC filtering, captive portal, and access control lists. In this video, you're going to learn about the basics of wireless network security, such as WPA, WPA2, TKIP, CCMP, EAP, and geofencing. Let's talk about Wi-Fi protected access. And this is an encryption standard that replaced WEP or wired equivalent privacy with the introduction of the 802.11g Wi-Fi standard. Software and firmware updates were made available by many vendors from the older 802.11b and 802.11a devices to add WPA support. WPA also uses a pre-shared key, but unlike WEP, they can be of varying length up to 63 ASCII characters, including punctuation, and the original key is used as the basis for frequent changes, and it is encrypted using TKIP encryption or temporal key integrity protocol encryption. And TKIP has many features that make it stronger than WEP, and as a side note, in cryptography, a pre-shared key is a shared secret, which was previously shared between the two parties using some secret channel before it needs to be used. So in other words, a pre-shared key is essentially the password that you would use to get access to a Wi-Fi network. Wi-Fi protected access 2, and this is the improved version of WPA. The WPA2 uses the even stronger advanced encryption standard encryption technology, or AES technology. When possible, you want to use WPA2, which can also show up as WPA/AES on your wireless network. If your wireless router or access point has WPA/WPA2 settings, it can support either type of encryption on the same network. You want to use this option if you have devices that support WPA but do not support WPA2. Then we got TKIP, or Temporal Key Integrity Protocol, and this is a security protocol used in the 802.11 wireless network standard. TKIP was designed as an interim solution to replace WEP without requiring the replacement of legacy software. And this was necessary because the breaking of WEP had left Wi-Fi networks without viable link layer security, and a solution was required for already deployed hardware. However, TKIP itself is no longer considered secure and was deprecated in the 2012 revision of the 802.11 standard. Next, we have CCMP, and this stands for Counter Mode Cipher Blockchaining Message Authentication Code Protocol. And this is an encryption protocol designed for wireless LAN products that implements the standards of the 802.11 standard. CCMP is the standard encryption protocol for use with the WPA2 standard and is much more secure than the WEP protocol and TKIP of WPA. And CCMP provides the following security services. It can offer data confidentiality, which ensures only authorized parties can access the information. It can provide authentication, which provides proof of genuineness of the user. And it provides access control in conjunction with layer management. Next, we have Extensible Authentication Protocol. So EAP, this is a protocol for wireless networks that expands the authentication methods used by the point-to-point protocol, a protocol often used when connecting a computer to the internet. EAP is used on encrypted networks to provide a secure way to send identifying information to provide network authentication. It supports various authentication methods, including as token cards, smart cards, certificates, one-time passwords, and public key encryption. We have a couple iterations of EAP, and the first one is PEEP, or Protected EAP. And PEEP authenticates clients using server-side certificates. It creates a TLS tunnel from the server to the client, so the client can be authenticated through that encrypted tunnel. Next, we have EAP Fast, and this stands for Flexible Authentication via Secure Tunneling. So EAP Fast uses a tunnel to provide mutual authentication like PEEP. EAP Fast does not have the server authenticate itself with a digital certificate. Instead, it uses a protected access credential, which creates a one-time provisioning exchange with a shared key or a PAC key, and the PAC key handles the authentication. And then we have EAP TLS, and that stands for Transport Layer Security. So EAP TLS, this provides certificate-based mutual authentication of the network and the client. Both the client and the server must have certificates to perform this authentication. EAP TLS randomly generates session-based, user-based web keys. These keys secure communications between the access point and the wireless LAN client. One disadvantage of EAP TLS is the server and client side both must manage the certificates. And let's talk about geofencing. So a geofence, this is a virtual perimeter for a real world geographic area. A geofence could be dynamically generated, as in a radius around a point location, or match a predefined set of boundaries, such as school zones or neighborhood boundaries. The use of a geofence is called geofencing, and one example of its use involves a location-aware device of a location-based service user entering or exiting a geofence. This activity could trigger an alert to the device's user, as well as messaging to the geofence operator. This info would contain the location of the device, and that could be sent to a mobile telephone or an email account. And some examples of geofencing applications include things such as child location services that can notify parents if a child leaves a designated area, location-based messaging for tourist safety and communication, sending an alert if a vehicle is stolen. And this could be used by the Human Resources Department to monitor employees working in special locations, especially those doing field work. All right, that is my quick little class on wireless network security, where we talked about WPA, WPA2, TKIP, CCMP, EAP, and geofencing. In this video, you're going to learn about networking attacks such as denial of service, social engineering, insider threats, logic bombs, rogue access points, evil twins, war driving, phishing, ransomware, DNS poisoning, ARP poisoning, spoof, deauthentication, brute force attacks, VLAN hopping, man in the middle, and exploits versus vulnerabilities. Let's talk about denial of service. So a denial of service attack occurs when legitimate users are unable to access information systems, devices, or other network resources due to the actions of a malicious cyber threat actor. Services affected may include email, websites, online accounts, or other services that rely on the affected computer or network. A DOS condition is accomplished by flooding the target host or network with traffic until the target cannot respond or simply crashes, preventing access for legitimate users. DOS attacks can cost an organization both time and money while their resources and services are inaccessible. And we have three types of DOS attacks that you need to be familiar with. The first one is called a reflective denial of service. So a reflective DOS attack, this makes use of a potentially legitimate third-party component to send attack traffic to a victim, ultimately hiding the attacker's own identity. The attackers send packets to a reflector server with a source IP set to their victim's IP, therefore indirectly overwhelming the victim with response packets. Reflector servers used for this purpose could be ordinary servers, not obviously compromised, which makes this kind of attack particularly difficult to mitigate. The next one we have is called an amplified denial of service. So an amplified DOS attack uses legitimate DNS servers that are tricked into flooding responses toward a targeted system by sending small queries that result in large responses, which allows for a malicious user to send more smaller requests that result in larger responses that hit the target. And then we have a distributed denial of service. So a DDoS attack, this is a malicious attempt to disrupt the normal traffic of a targeted server, service, or network by overwhelming the target or its surrounding infrastructure with a flood of internet traffic. DDoS attacks achieve effectiveness by utilizing multiple compromised computer systems as sources of attack traffic. Exploited machines can include computers and other network resources such as IoT devices. From a high level, a DDoS attack is like an unexpected traffic jam clogging up the highway, preventing regular traffic from arriving at its destination. Next, let's talk about social engineering. And this is the psychological manipulation of people into performing actions or divulging confidential information. This differs from social engineering within social sciences, which does not concern the divulging of confidential information. A type of confidence trick for the purpose of information gathering, fraud, or system access. It differs from a traditional con in that it is often one of many steps in a more complex fraud scheme. And here are some examples of social engineering that you need to be concerned with. The first one is called pretexting, and this is gaining users' trust by claiming to be from the IT department or the internet provider or the phone company, etc., followed by asking the user to enter or provide a password to a system so that the quote-unquote tech can make changes to the system. The next one is called phishing, and this is the fraudulent attempt to obtain sensitive information such as username, passwords, and credit card details, often for malicious reasons, by disguising oneself as a trustworthy entity in an electronic communication. Next, we have spear phishing, and this is a form of phishing such as a fake email message that appears to come from another department in the company and requests information from a specific targeted individual or department. And then we have compromised passwords, and this is when users who don't change their passwords after an IT technician or outside contractor tests their system, they leave their systems vulnerable. Also understand that training users to understand, detect, and reject social engineering and other types of deceit is essential to protecting important information. Let's talk about an insider threat. So an insider threat, this is a malicious threat to an organization that comes from people within the organization, such as employees, former employees, contractors, or business associates who have insider information concerning the organization's security practices, data, and computer systems. The threat may involve fraud, the theft of confidential or commercially valuable information, the theft of intellectual property, or the sabotage of computer systems. And the insider threat comes in three categories. You have malicious insiders, and these are people who take advantage of their access to inflict harm on an organization. Then you have negligent insiders, and these are people who make errors and disregard policies which place their organization at risk. And then you have infiltrators, and these are external actors that obtain legitimate access credentials without authorization. Next, we have a logic bomb. And a logic bomb, this is a piece of code intentionally inserted into a software system that will set off a malicious function when specified conditions are met. So for example, a programmer may hide a piece of code that starts deleting files, such as a salary database trigger, should they ever be terminated from the company. Software that is inherently malicious, such as viruses and worms, they often contain logic bombs that execute a certain payload at a predefined time or when some other condition is met. This technique can be used by a virus or worm to gain momentum and spread before being noticed. Some viruses attack their host systems on specific dates, such as Friday the 13th or April Fool's Day. Trojans and other computer viruses that activate on certain dates are often called time bombs. To be considered a logic bomb, the payload should be unwanted and unknown to the user of the software. Next, we have a rogue access point, and this is a wireless access point that has been installed on a secure network without explicit authorization from a local network administrator, whether added by a well-meaning employee or by a malicious attacker. To prevent the installation of rogue access points, organizations can install wireless intrusion prevention systems to monitor the radio spectrum for unauthorized access points. Next, we have an evil twin. An evil twin, this is a fraudulent Wi-Fi access point that appears to be legitimate, but is set up to eavesdrop on wireless communications. The evil twin is the wireless LAN equivalent of the phishing scam. This type of attack may be used to steal the passwords of unsuspecting users, either by monitoring their connections or by phishing, which involves setting up a fraudulent website and luring people there. The attacker snoops on internet traffic using a bogus wireless access point. Unwitting web users may be invited to log into the attacker's server, prompting them to enter sensitive information such as usernames and passwords. Often users are unaware they have been duped until well after the incident has occurred. Next, we have war driving, and this involves attackers searching for wireless networks with vulnerabilities while moving around an area in a moving vehicle. The attackers use hardware and software to discover unsecured Wi-Fi networks, then gain unauthorized access to the network by cracking passwords or decrypting the router. The attacker then records vulnerable network locations on digital maps, known as access point mapping, and may share that information with third-party applications and websites. War driving can have several variations depending on the mode of transport the hacker has used, such as war biking, war cycling, war railing, war jogging, and war walking. Ransomware. This is a type of malware from cryptovirology that threatens to publish the victim's personal data or perpetually block access to it unless a ransom is paid. While some simple ransomware may lock the system so that it is not difficult for a knowledgeable person to reverse, more advanced malware uses a technique called cryptoviral extortion. It encrypts the victim's files, making them inaccessible, and demands a ransom payment to decrypt them. In a properly implemented cryptoviral extortion attack, recovering the files without the decryption key is an intractable problem and difficult to trace digital currencies such as Bitcoin or other cryptocurrencies that are used for the ransoms. They make tracing and prosecuting the perpetrators extremely difficult. Next, we have DNS poisoning, and this is also known as DNS cache poisoning or DNS spoofing. And this is a highly deceptive cyber attack in which hackers redirect web traffic towards a fake web server and phishing websites. These fake sites typically look like the user's intended destination, making it easy for hackers to trick visitors into sharing sensitive information. In a DNS poisoning attack, hackers alter a domain name system to a spoof DNS so that when a legitimate user goes to a website, instead of landing on their intended destination, they actually end up at an entirely different website. Usually this happens without users even knowing, as the fake sites are often made to look like the real ones. Then we have ARP poisoning or address resolution protocol poisoning. So ARP poisoning, this is a technique by which an attacker sends spoof ARP messages onto a LAN. Generally, the aim is to associate the attacker's MAC address with the IP address of another host, such as the default gateway, causing any traffic meant for that IP address to be sent to the attacker instead. ARP spoofing may allow an attacker to intercept data frames on the network, modify the traffic, or stop all traffic. Often the attack is used as an opening for other attacks such as denial of service, man in the middle, or session hijacking attacks. The attack can only be used on networks that use ARP and requires the attacker to have direct access to the local network segment to be attacked. Next, we have spoofing. Spoofing, this is the act of disguising a communication or identity so that it appears to be associated with a trusted, authorized source. Spoofing attacks can take many forms, from the common email spoofing attacks that are deployed in phishing campaigns to caller ID spoofing attacks that are often used to commit fraud. Attackers may also target more technical elements of an organization's network, such as an IP address, DNS server, or ARP service as part of a spoofing attack. Spoofing attacks typically take advantage of trusted relationships by impersonating a person or organization that the victim knows. In some cases, such as whale phishing attacks that feature email spoofing or website spoofing, these messages may even be personalized to the victim in order to convince that person that the communication is legitimate. If the user is unaware that internet communications can be fake, they are especially likely to fall prey to a spoofing attack. Next, we have deauthentication. So a Wi-Fi deauthentication attack is a type of denial of service attack that targets communication between a user and a Wi-Fi wireless access point. Unlike most radio jammers, deauthentication acts in a unique way. The IEEE 802.11 or the Wi-Fi protocol contains the provision for a deauthentication frame. Sending the frame from the access point to a station is called a sanction technique to inform a rogue station that they have been disconnected from the network. An attacker can send a deauthentication frame at any time to a wireless access point with a spoofed address for the victim. The protocol does not require any encryption for the frame, even when the session was established with WEP for data privacy, and the attacker only needs to know the victim's MAC address, which is available in the clear through wireless network sniffing. One of the main purposes of deauthentication used in the hacking community is to force clients to connect to an evil twin access point, which can then be used to capture network packets transferred between the client and the access point. The attacker conducts a deauthentication attack to the target client, disconnecting it from its current network, thus allowing the client to automatically connect to the evil twin access point. Next, we have brute force. So in cryptography, a brute force attack consists of an attacker submitting many passwords or passphrases with the hope of eventually guessing a combination correctly. The attacker systematically checks all possible passwords and passphrases until the correct one is found. System and network administrators setting up password rules that require a system to lock after a specified number of incorrect passwords or input is one way to prevent a brute force attack. Also, longer passwords, they aid in the fight against brute force attacks as well. Next, we have VLAN hopping, and this is a computer security exploit, a method of attacking network resources on a VLAN. The basic concept behind all VLAN hopping attacks is for an attacking host on a VLAN to gain access to traffic on other VLANs that would normally not be accessible. And there are two primary methods of VLAN hopping, and they are switch spoofing and double tagging. Switch spoofing, this is when the attacker will send packets to try to negotiate a trunk with the switch. Once you have a trunk trunk to your computer, you will have access to all the VLANs. The other method is called double tagging. And this is when the attacker is connected to an interface in access mode with the same VLAN as the native untagged VLAN on the trunk. The attacker sends two tags, the inner VLAN tag for the VLAN that the attacker wants to reach and the outer VLAN tag for the native VLAN. When the switch receives the frame, it will remove the first native VLAN tag and forward the frame with the second tag on its trunk interface. The attacker will now have jumped from the native VLAN to the victim's VLAN. Then we have man in the middle. In cryptography and computer security, a man in the middle attack is a cyber attack where the attacker secretly relays and possibly alters captured communications between two parties who believe that they are directly communicating with each other. Then we have exploits, and an exploit, this is a code that takes advantage of a software vulnerability or security flaw. It is written either by security researchers as a proof of concept threat or by malicious actors for use in their operations. When used, exploits allow an intruder to remotely access a network and gain elevated privileges or move deeper into the network. In some cases, an exploit can be used as part of a multi-component attack. Instead of using a malicious file, the exploit may instead drop another malware, which can include backdoor Trojans and spyware that can steal user information from the infected systems. And then we have a vulnerability, and this is a weakness which can be exploited by a threat actor, such as an attacker to cross privileged boundaries or perform unauthorized actions within a computer system. To exploit a vulnerability, an attacker must have at least one applicable tool or technique that can connect to a system weakness. In this frame, vulnerabilities are also known as the attack surface. All right, and that is my quick little class on network attacks. So let's go ahead and get into some of this outstanding check on learning. So the first question is, what is the type of attack that is used to redirect web traffic towards fake web servers and phishing websites? Would it be ARP poisoning, DNS poisoning, war driving, or spoofing? So which one of these is going to redirect web traffic to a fake website? And the correct answer is... that will be DNS poisoning or domain name system poisoning. Next question. Which is not a form of social engineering? Is it pretexting, phishing, compromised passwords, or brute force? So which one of these is not a form of social engineering? And the correct answer would be a brute force attack. This is not a form of social engineering. Remember, social engineering is designed to get somebody else to do something for you under the guise of some type of fraud or whatever the case may be. A brute force attack is simply a person entering a password and a passphrase over and over again until they get the right combination to gain unauthorized access. Next question. Which is an attack that uses an illegitimate wireless access point to eavesdrop on wireless communications to steal passwords? Would it be an evil twin, a rogue access point, war driving, or deauthentication? So which one of these uses an illegitimate wireless access point to eavesdrop and steal passwords? And the correct answer is... this would be an evil twin. An evil twin is an access point somebody would set up explicitly for the purposes of trying to capture packets to get access to username and passwords. A rogue access point could be an access point that somebody sets up on the network without getting permission to set the access point up on the network, whether for illegitimate reasons or maybe somebody simply just didn't know what the rules were. All right, so in summary, we have talked about networking attacks such as denial of service, social engineering, insider threats, logic bombs, rogue access points, evil twins, war driving, phishing, ransomware, DNS poisoning, ARP poisoning, spoofing, deauthentication, brute force attacks, VLAN hopping, man-in-the-middle attacks, exploits, and vulnerabilities. In this video, you're going to learn about network device hardening best practices such as changing default credentials, avoiding common passwords, upgrading firmware, patching and updating, file hashing, disabling unnecessary services, using secure protocols, generating new keys, and disabling unused ports. Let's talk about network hardening. So hardening, this is the process of securing a system by reducing its surface of vulnerability, which is larger when a system performs more functions. So in principle, a single function is more secure than a multi-purpose one. And in order to reduce the available ways of attack, you can implement the following. So the first one is you want to change your default credentials. So at a minimum, this should be done because the first thing an attacker will try is to utilize default username and passwords, which oftentimes can be found on the internet. You also want to avoid common passwords, so organizations should prevent employees from using basic dictionary words in isolation because every English language word can be found in a cracking dictionary. You want to upgrade the firmware and then patch and do some updates as well. So you want to update unpatched or outdated software and firmware weaknesses immediately. You want to implement file hashing. So a cryptographic hash, this is a mathematical algorithm that maps data of an arbitrary size, which is often called the message, to a bit array of a fixed size, which is often called the hash value or the message digest. It is a one-way function that is practically infeasible to invert or reverse the computation. Cryptographic hash functions are used to achieve a number of security goals like message authentication, message integrity, and are also used to implement digital signatures by way of non-repudiation and entity authentication. Next, you want to disable unnecessary services. So many computer break-ins are a result of people taking advantage of security holes or programs with these programs. The more services that are running on your computer, the more opportunities there are for others to use them, break into, or take control of your computer through these programs. Next, you want to use secure protocols. So security protocols and encryption, they prevent an attacker from tapping into the air and reading data as it passes by. Then you want to generate new keys. So you want to generate new cryptographic private keys periodically, if possible, to prevent an attacker from getting access to those keys, which could lead to the attacker gaining unauthorized access to private information. And you want to disable unused ports. So disabling unused ports can stop attackers from plugging a malicious device into an unused port and getting unauthorized access to the network. This includes ports running IP and physical ports themselves. All right, so in summary, this was my quick little class on network device hardening best practices, where we talked about things such as changing default credentials, avoiding common passwords, upgrading firmware, patching and updating, file hashing, disabling unnecessary services, using secure protocols, generating new cryptographic keys, and disabling unused ports. In this video, you're going to learn about network mitigation techniques such as signature management, changing native VLANs, switch port protection, network segmentation, privileged user accounts, file integrity monitoring, role separation, restricting access via ACLs, honeypots and honeynets, and penetration testing. Let's talk about signature management. So a signature is a set of rules that an IDS and an IPS use to detect typical intrusion activity, such as DOS attacks. Signatures can be easily installed using IDS, IPS management software. Sensors enable you to modify existing signatures and define new ones. As sensors scan network packets, they use signatures to detect known attacks and respond with predefined actions. A malicious packet flow has a specific type of activity and signature, and an IDS or IPS sensor examines the data flow using many different signatures. When an IDS or IPS sensor matches a signature with a data flow, the sensor takes action, such as logging the event or sending an alarm to IDS or IPS management software. Let's talk about change native VLAN. So a native VLAN exists in the case of the 802.1q encapsulation, which supports untagged traffic. This makes it possible for your VLAN to support legacy devices that do not tag their traffic, like some wireless access points and simple network attached devices. Traffic that arrives at a trunk port without an existing VLAN tag gets associated with the native VLAN. When it comes to the management aspect of a native VLAN, it is recommended requirement that a network admin configure the VLAN to another number other than VLAN 1, because typically VLAN 1 is the default configuration of a Cisco switch for management protocols. So configuring the native VLAN to be another number other than 1, like VLAN 999, this will help to separate user traffic from network management traffic. Let's talk about switch port protection. And the first one we're going to talk about is called spanning tree protocol. So spanning tree protocol prevents loops from being formed when switches or bridges are interconnected via multiple paths. To avoid the problems associated with redundant links in a switch LAN, STP is implemented on switches to monitor the network topology. Every link between switches, and in particular redundant links, are cataloged. The STP algorithm then blocks forwarding on redundant links by setting up one preferred link between switches in the LAN. This preferred link is used for all Ethernet frames unless it fails, in which case a non-preferred redundant link is enabled. When implemented in a network, STP designates one layer 2 switch as a root bridge. All switches then select their best connection towards the root bridge for forwarding and blocking other redundant links. All switches constantly communicate with their neighbors in the LAN using bridge protocol data units. Next, we have a flood guard, and these are tools that you can use to prevent DOS attacks. This technology is typically built into network equipment such as routers and intrusion prevention equipment. It is designed to detect network floods and then block this traffic. Flood guards help block malicious traffic from entering a network. Then we have the BPDU guard, or the Bridge Protocol Data Unit Guard. So a BPDU, this is a data message transmitted across a LAN to detect loops in network topologies. A BPDU contains information regarding ports, switches, port priority, and addresses. BPDUs contain the information necessary to configure and maintain spanning tree protocol. They are not forwarded by switches, but the information is used by the switches to calculate their own BPDUs for information passing. Then we have a root guard. So root guards are useful in avoiding layer 2 loops during network anomalies. The root guard forces an interface to become a designated port to prevent surrounding switches from becoming a root switch. In other words, a root guard provides a way to enforce the root bridge placement in the network. The root guard feature prevents a designated port from becoming a root port. If a port on which the root guard features receives a superior BPDU, it moves the port into a root inconsistent state, which is effectively equal to a listening state, thus maintaining the current root bridge status. Then we have DHCP snooping. So DHCP snooping, this is a series of techniques applied to improve the security of a DHCP infrastructure. DHCP servers allocate IP addresses to clients on a LAN. DHCP snooping can be configured on LAN switches to exclude rogue DHCP servers and remove malicious or malformed DHCP traffic. In addition, information on hosts which have successfully completed a DHCP transaction is accrued in a database of bindings, which may then be used by other security or accounting features. Let's talk about network segmentation. So the first one we're going to talk about is the DMZ, and this stands for demilitarized zone. So a DMZ, which is also known as a perimeter network or a screen subnet, this is a physical or logical subnetwork that contains and exposes an organization's external facing services to an untrusted, usually larger network such as the internet. The purpose of a DMZ is to add an additional layer of security to an organization's LAN to where an external node can access only what is exposed in the DMZ, while the rest of the organization's network is firewalled. The DMZ functions as a small isolated network positioned between the internet and the private network, and if its design is effective, allows the organization extra time to detect and address breaches before they would further penetrate into the internal networks. Then we have a VLAN, or a virtual local area network. So a VLAN, this is any broadcast domain that is partitioned and isolated in the computer network at the data link layer, or OSI layer 2. So LAN, this is the abbreviation for local area network, and in this context, virtual refers to a physical object created and altered by additional logic. VLANs work by applying tags to network frames and handling these tags in networking systems, creating the the appearance and functionality of network traffic that is physically on a single network but acts as if it is split between separate networks. In this way, VLANs can keep network applications separate despite being connected to the same physical network and without requiring multiple sets of cabling and networking devices to be deployed. Privileged user accounts. So a privileged user account, this is an account that has more privileges than ordinary users. Privileged accounts might be able to install or remove software, upgrade the operating system, or modify system or application configurations. They might also have access to files that are not normally accessible to standard users. And there are many kinds of privileged user accounts, and some of them are as follows. You have a root and administrator account, also known as a super user, and this is typically used for installing and removing software and changing configurations. You have service accounts. These are used for running processes such as web servers, database servers, and application servers. And then you have system accounts. These are used for running operating system components and owning related files. File integrity monitoring. So this is an internal control or process that performs the act of validating the integrity of operating systems and application software files using a verification method between the current file state and a known good baseline. This comparison method often involves calculating a known cryptographic checksum of the file's original baseline and comparing it with the calculated checksum of the current state of the file. Other file attributes can also be used to monitor integrity. Generally, the act of performing file integrity monitoring is automated using internal controls such as an application or process. Such monitoring can be performed randomly at defined polling intervals or in real time. Changes to configurations, files, and file attributes across the IT infrastructure are common, but hidden within a large volume of daily changes can be the few that impact file or configuration integrity. These changes can also reduce security posture and in some cases may be leading indicators of a breach in progress. And values monitored for unexpected changes to files or configuration items include the following. You have credentials, privilege and security settings, content, core attributes and size, hash values, and configuration values. Let's talk about role separation, which is also known as separation of privileges. And this is an IT best practice applied to organizations to broadly separate users and processes based on different levels of trust, needs, and privilege requirements. And separation of privileges refers to both the segmentation of user privileges across various separate users and accounts and compartmentalization of privileges across various applications or system components, tasks, and processes. And similar to the concept of network segmentation, role separation essentially creates barriers around specific parts of an IT environment. It helps contain intruders close to the point of compromise and restricts lateral movement while also ensuring that employees, applications, and system processes do not have access to more data than they need. Segmenting privileges and the tasks associated with them also provides the benefit of a cleaner audit trail and simplifying compliance. Restricting access via ACLs or access control lists. So an access control list, this is a set of rules that is usually used to filter network traffic. ACLs can be configured on network devices with packet filtering capabilities, such as routers and firewalls. ACLs contain a list of conditions that categorize packets and help determine when to allow or deny network traffic. They are applied on the interface basis to packets leaving or entering an interface. ACLs also can list permissions associated with a system resource or object. These types of ACLs specify which users or system processes are granted access to objects, as well as what operations are allowed on given objects. Then we have honeypots and honeynets. So honeypots, these are a type of deception technology that allows network and system administrators to understand attacker behavior patterns. Security teams can use honeypots to investigate cybersecurity breaches to collect intel on how cyber criminals operate. They also reduce the risk of false positives when compared to traditional cybersecurity measures because they are unlikely to attract legitimate activity. A honeynet is a decoy network that contains contains one or more honeypots. It looks like a real network and contains multiple systems, but is hosted on one or only a few servers, each representing one environment. So for example, a Windows honeypot machine, a Mac honeypot machine, and a Linux honeypot machine. A quote-unquote honey wall, this monitors the traffic going in and out of the network and directs it to the honeypot instances. There, vulnerabilities can be injected into the honeynet to make it easy for an attacker to access the trap. And then we have penetration testing. So a penetration test, also known as a pen test or ethical hacking, this is an authorized simulated cyber attack on a computer system performed to evaluate the security of the system, and this is not to be confused with a vulnerability assessment. The test is performed to identify weaknesses, including the potential for unauthorized parties to gain access to the system's features and data, as well as strengths, enabling a full risk assessment to be completed. The process typically identifies the target system in a particular goal, then reviews available information and undertakes various means to attain that goal. A penetration test may be a white box, which is about which background and system information are provided in advance to the tester, or it may be a black box in which only basic information, if any, other than the company name is provided. A gray box penetration test, this is a combination of the two, where limited knowledge of the target is shared with the auditor, and a penetration test can help identify systems vulnerabilities to attack and estimate how vulnerable the system actually is. All right, now it's time for some of this outstanding check on learning. So the first question is, which is a mitigation technique that uses fake systems to attract attackers to collect intel on how cyber criminals operate? Would it be an ACL, a honeynet, VLAN, or a DMZ? So which one of these is a fake system that is designed to attract cyber criminals? And the correct answer is, this would be a honeynet. So remember, a honeynet is basically a fake network comprised of a bunch of honeypots, where a honeypot are just individual systems. Next question. Which mitigation technique is used to prevent loops from being formed within a network? Would it be STP, BPDU, DHCP, or VLAN? So which one of these is used to prevent loops from being formed within a network? And the correct answer is, this will be STP, or Spanning Tree Protocol. Next question. Which mitigation technique purposely hires people to break into a network to find vulnerabilities? Would this be DHCP snooping, network segmentation, file integrity monitoring, or penetration testing? So which one of these hires people to break into a network to find issues with the network? And the correct answer is, this would be penetration testing. So in summary, we have talked about network mitigation techniques such as signature management, changing native VLANs, switch port protection, network segmentation, privileged user accounts, file integrity monitoring, role separation, restricting access via ACLs, honeypots and honeynets, and penetration testing. In this video, you're going to learn about the troubleshooting methodology, where you will learn how to identify a problem, establish a theory of probable cause, test the theory to determine the cause, establish a plan of action to resolve the problem and identify potential effects, implement the solution or escalate as necessary, verify full system functionality, and if applicable, implement preventative measures, and finally, document your findings, lessons learned, actions, and outcomes. First step is identifying the problem. So the first thing you need to be aware of when troubleshooting a problem is understanding that the symptoms are not the problem. The actual problem is what's causing the symptoms to manifest. And to identify the problems, you will use the following as needed. You want to gather information. You want to duplicate the problem if possible. You want to question users. You want to identify symptoms. You want to determine if anything has changed. And then you want to approach multiple problems individually. Step 2, you want to establish a theory of probable cause. So once you think you successfully research solutions and identify potential issues that may be causing the problem, it is now time for you to establish a theory of probable cause by doing the following. First thing you want to do, you want to question the obvious. So sometimes the solution to a problem could be something very simple that just goes unnoticed, and you want to consider multiple approaches. So a rule you should abide by is the KISS rule, or the keep it simple, stupid rule. Sometimes there are multiple approaches to solving a problem, but it is best to go with the simplest and most easy to implement during your approach. Also, you want to think about solving the problem in terms of moving top to bottom or bottom to top within the OSI model. And then you want to divide and conquer. Sometimes problems arise that may deal with components and their various subsystems. Dividing and conquering allows for you to fix problems in a systematic manner. So step 3, you want to test the theory to determine the cause. So once you believe you have established probable cause, it is now time to test the theory to determine that cause. This can include things like checking to make sure the correct IP addresses, subnet masks, and default gateways have been assigned to an end device in order to verify that the end device is able to reach the correct default gateway. If the theory is confirmed, then it's time to resolve that problem. If you come to the conclusion that the theory is incorrect, the next thing you should do is develop a new theory and then test that theory. Next step, you want to establish a plan of action to resolve the problem and identify potential effects. So once you have identified the problem and discovered a solution, it's now time to establish a plan of action to resolve the problem and identify the potential effects. And if time permits, you should document your action plan. The documentation of your action plan could be used as a backup plan if your hypothesis is incorrect. Next step, you want to implement the solution or escalate as necessary. So if you are responsible for implementing the plan of action, you need to follow it carefully. Be sure to note any problems with the plan or any additional problems you observe. If you are not responsible for implementing the plan of action, you need to escalate it to the department that is responsible for solving the problem. Next, you want to verify full system functionality and, if applicable, implement preventative measures. So once you have implemented the solution, the next step is to check to make sure that the system or network is fully functional as it is supposed to be, with all of the original symptoms gone. Also, attempt to determine whether your action plan has caused any other issues on the network. And if they have, you need to go back and solve those problems so that system or network can be fully functional. And then finally, you want to document your findings, actions, and outcomes. So when it comes to problems arising in IT, more than likely you are going to encounter similar problems over and over again. Instead of approaching each problem as if it's the first time you've seen the problem, the best approach is to document your findings, lessons learned, actions, and outcomes from each problem you have solved so that you can build a repository of solutions for future problems you are bound to encounter again in the future. Also, be sure to add any figures such as screen captures, diagrams, photos, etc. that will help you or others solve similar problems next time. Remember, detailed documentation is your friend when it comes to solving problems in IT. All right, that was my quick little class on network troubleshooting methodology. So let's go ahead and get to some of this outstanding check on learning. So the first question is, identifying the symptoms is a part of which troubleshooting step? Is it step 2, establishing a theory of probable cause? Step 3, testing the theory? Step 1, identifying the problem? Or step 5, implementing the solution or escalating it? So identifying symptoms, this is a part of which troubleshooting step? And the correct answer is, this would fall up under step 1, identifying the problem. Remember, symptoms are not the problem. Symptoms are a manifestation of the problem. Next question. Building a repository of solutions is a part of which troubleshooting step? Would it be step 2, establishing a theory of probable cause? Step 7, documenting your findings, actions, and outcomes? Step 6, verifying full system functionality and implementing preventative measures? Or step 4, establishing a plan of action to resolve the problem? So building a repository of solutions is a part of which troubleshooting step? And the correct answer is, that will be step 6. 7, documenting your findings, actions, and outcomes. So remember, proper documentation is your friend in IT. It will help you solve problems very quickly because chances are you're going to come across the same problems over and over and over again. Next question. Applying the keep it simple, stupid strategy is a part of which troubleshooting step? Would this be step 1, identifying the problem? Step 2, establishing a theory of probable cause? Step 3, testing the theory to determine the cause? Or step 4, establishing a plan of action to resolve the problem? So applying the KISS strategy is a part of which troubleshooting step? The correct answer is this will be part of step 2, establishing a theory of probable cause. Remember, keep it simple, stupid is basically an acronym that tells you just to look for the easiest and simplest explanation as to why something may have went wrong, because 9 times out of 10, that is going to be what has caused your problem. So in summary, we have talked about the troubleshooting methodology where you learned how to identify a problem, establish a theory of probable cause, test the theory to determine the cause, establish a plan of action to resolve the problem and identify potential effects, implement the solution or escalate as necessary, verify full system functionality, and if applicable, implement preventative measures, and finally, documenting your findings, lessons learned, actions, and outcomes. In this video, you're going to learn about various hardware and software networking tools in addition to various command line interface tools. So let's talk about hardware tools. And the first one we're going to talk about is the crimper. So a crimping tool, this is a device used to conjoin 2 pieces of metal by deforming one or both of them to hold each other. The result of the tool's work is called a crimp. A crimper attaches a connector to the end of raw twisted pair or coaxial cable. If you are working with twisted pair, you need an RJ45 crimping tool, which often also works with RJ11 telephone cable. After untwisting the wire pairs and aligning them according to the appropriate standard, which is typically a T568B standard, you want to insert them into an RJ45 connector and push the cable and connector assembly into the crimper. Line up the crimper jaw with the recessed area of the connector and then squeeze. Next, we have a cable tester, and this is an electronic device used to verify the electrical connections in a signal cable or other wired assembly. Basic cable testers are continuity testers that verify the existence of a conductive path between ends of the cable and verify the correct wiring of connectors on the cable. More advanced cable testers can measure the signal transmission properties of the cable, such as its resistance, signal attenuation, noise, and interference. Cable testers include a LAN testing unit that could be plugged into a port on the patch panel and a terminator that could be plugged into the other end of the cable into the corresponding RJ45 jack. This tool tests each wire in the cable and makes sure everything is wired properly. Next, we have a punch down tool, and this is a small handheld tool used by network technicians to insert wire into insulation displacement connectors, patch panels, or punch down blocks. A punch down tool punches individual wires down into the 110 IDC clips of an RJ45 jack and the patch panel. The punching down of the wires is the actual termination. The patch panels connect the various ports of the patch panel to a switch and the RJ45 jacks to the computers. Next, we have an OTDR, or an optical time domain reflectometer. So an OTDR, this is a device used to precisely detect faults in an optical fiber link of a communication network. An OTDR simply generates a pulse inside a fiber to be tested for faults or defects. Pulses are returned to the OTDR and their strengths are then measured and calculated as a function of time and plotted as a function of fiber stretch. The strength and return signal tell about the location and intensity of the fault that is present. Next, we have a light meter, and this is a low-cost way to certify optical fiber by measuring fiber optic light continuity, loss, and the actual strength of the optical signal. In fiber optics, when a beam of light which carries a signal goes through the optical fiber, the strength of that light beam will diminish over distance. This means the signal strength becomes weaker. The loss of light power will affect the fiber optic network in a negative way. The loss of light power or attenuation of the optical fiber is caused by 2 issues, scattering and absorption of the light source. If the degradation is too great, then the performance of the network will be affected, and potential causes of signal loss include the following: tight bends in the cable, dirty or improperly cleaned connectors, too much stress on the cable during installation, poorly installed connectors, improper splicing techniques, and poor cable quality. Then we have the tone generator and probe. A tone generator and probe kit. This is an excellent tool for finding individual phone lines, and it consists of two components. You have the tone device. This connects to one end of the network cable and sends a tone along the length of the cable. And then you have the probing device. This is also known as an inductive amplifier, and it can pick up the tone anywhere along the cable length and at the termination point. Next, we have a loopback adapter, and this is also known as a loopback plug, and this is a connector used for diagnosing transmission problems. It plugs into an Ethernet RJ45 or serial port and crosses over the transmit line to the receive line so that outgoing signals can be redirected back into the computer for testing to verify whether the network adapter and TCP/IP are functioning properly. Multimeter. So a multimeter, also known as a multi-tester, this is an electronic measuring instrument that combines several measurement functions in one unit. A typical multimeter can measure voltage, current, and resistance. Analog multimeters use a microammeter with a moving pointer to display readings. Digital multimeters, which are the most common in use today, they have a numeric display and may also show a graphical bar representing the measured values. Multimeters can be used for testing both coaxial and twisted pair cabling, as well as AC and DC voltages to test computer power supplies and AC adapters. All multimeters have standard red and black test leads. When used for voltage tests, the red lead is attached to the power source to be measured, and the black lead is attached to the ground. Next, we have a spectrum analyzer, and this measures the magnitude of an input signal versus frequency within the full frequency range of the instrument. The primary use is to measure the power of the spectrum of known and unknown signals. The input signal that most common spectrum analyzers measure is electrical. However, spectral compositions of other signals, such as acoustic pressure waves and optical light waves, can be considered through the use of an appropriate transducer. Spectrum analyzers for other types of signals also exist, such as optical spectrum analyzers, which use direct optical techniques such as a monochromator to measure measurements. By analyzing the spectra of electrical signals, dominant frequency, power, distortion, harmonics, bandwidth, and other spectral components of a signal can be observed that are not easily detectable in time domain waveforms. These parameters are useful in the characterization of electronic devices such as wireless transmitters. The display of a spectrum analyzer has frequency on the horizontal axis and the amplitude displayed on the vertical axis. To the casual observer, a spectrum analyzer looks like an oscilloscope, and in fact, some lab instruments can function either as an oscilloscope or a spectrum analyzer. Now let's talk about software tools, and the first one we're going to talk about is called a packet sniffer. And this is a computer program or computer hardware such as a packet capture appliance that can intercept and log traffic that passes over a computer network or part of a network. Packet capture, this is the process of intercepting and logging traffic. As data streams flow across the network, the analyzer captures each packet and, if needed, decodes the packet's raw data, showing the values of various fields in the packet, and analyzes its contents according to appropriate specifications. Next, we have a port scanner. So a port scan, this is the process that sends client requests to a range of server port addresses on a host with the goal of finding an active port. This is not a nefarious process in of itself. The majority of uses of a port scan are not attacks, but rather simple probes to determine services available on a remote machine. A port scanner, this is an application designed to probe a server or host for open ports. Such an application may be used by administrators to verify security policies of their networks and by attackers to identify network services running on a host and exploit vulnerabilities. Protocol analyzers. This is the tool that could be hardware or software that is used to capture and analyze signals and data traffic over a communication channel. Protocol analyzers work by capturing data across a communication bus and embedded systems. With the help of protocol analyzers, engineers and developers can design, debug, and test their designs through the entire development life cycle of a hardware product. Quite often, protocol analyzers are used for analyzing network traffic on LANs, PANs, and even on wireless networks. With the help of protocol analyzers, data can be monitored and decoded, and the captured data can then be interpreted to generate actionable reports and useful information for network system administrators. Wi-Fi analyzer. So a Wi-Fi analyzer allows for you to analyze both 2.4 gigahertz and 5 gigahertz wireless networks in the area. Wireless networks use specific channels within the wireless spectrum. An overcrowded wireless channel results in decreased bandwidth and or connectivity issues for your network. You can use a Wi-Fi analyzer to see what channels are in use and to identify the best channel to set up on your router. A Wi-Fi analyzer can be a standalone device, a program for a desktop computer, or an app on a smartphone. Then we have a speed tester. So most cable ISPs do not have data caps. To determine the actual upstream or downstream speeds your connection achieves with an ISP, you want to use a speed testing website. Many ISPs provide speed testing web page links on their customer service page. Upstream, also known as uploading, this refers to data, page requests, email, and so on that is being sent from your computer or network to the internet. And downstream, or downloading, this refers to any information being received from the internet. And then we have various command line tools that you need to be familiar with for this examination. The first one is ping. This sends IP packets to check network connectivity. Then you got traceroute. This is similar to ping, but returns path information to an IP address destination. In Mac and Linux, the command is traceroute, TRACEROUTE. Then you have NSLOOKUP. This gathers the network's DNS information. You have IP config. This displays TCP/IP network information on a computer. In Mac and Linux, the command is ifconfig. Then you have IP tables. This is a Linux command to put rules in place for packet filtering for the Linux kernel firewall. And you got netstat. This displays a list of active TCP connections on a local network. Then you got TCP dump, and this is a data network packet analyzer computer program that runs under a command line interface. It displays TCP/IP and other packets being transmitted or received over a network to which the computer is attached. Then you have path ping. This is used to combine the functionality of ping and traceroute. It is used to locate spots that have network latency and network loss. Then you got nmap. This is used to discover hosts, services, and operating systems detected on computer networks by sending packets and analyzing the responses. You got route. This allows you to make manual entries into network routing tables. It distinguishes between routes to hosts and routes to networks by interpreting the network address of the destination variable, which can be specified either by symbolic name or numeric address. Then you got ARP. This displays and modifies entries in the address resolution protocol cache. The ARP cache contains one or more tables that are used to store IP addresses and to resolve Ethernet or token ring physical addresses. And then you got dig. This performs DNS lookups and displays the answers that are returned from the query name servers. All right, so that was my quick little class on networking tools. So let's go ahead and get into some of this wonderful check on learning. So the first question is, you are helping a friend with a new wireless router. They are complaining that certain areas of their apartment have much slower internet than others. They live in a dense area with many other apartments in Wi-Fi range. Which tool could help you troubleshoot this issue? Would it be a wireless loopback plug, a port scanner, a spectrum tester, or a Wi-Fi analyzer? So they're complaining about their internet being too slow and they live around a bunch of other people. So what is going to help you figure out what might be going on with this issue? And the correct answer is, this will be a Wi-Fi analyzer. This tool will help you figure out the best channel to set your router to so you can hopefully avoid interference with somebody else's Wi-Fi if you live in an environment like this. Next question. Which of the following tools can verify an Ethernet's cable's wires are in the correct order? Would it be a cable tester, a wattage plug, a loopback plug, or an amplimeter? So which one of these will help you verify that you have wired up your wires in the correct order? And the correct answer is, this will be a cable tester. Next question. Which of the following is a device used to test ports, such as a network port? Would this be a tone generator, a loopback plug, a cable tester, or a leakage tester? So which one of these is going to help you test the functionality of a network port? And the correct answer is, This is going to be a loopback plug. So remember, a loopback plug is a device that you plug into the port to test to see if your transmit and receive signals are doing what they're supposed to do, meaning they're sending data out and receiving data. And if that's the case, then you know that that device is good to go. So in summary, we have talked about various hardware and software networking tools in addition to various command line interface tools. In this quick little video, you're going to learn about wired network troubleshooting as it relates to bad cables or connectors, bad ports, opens and shorts, splitting pairs in a cable, decibel loss, transpose, transmit and receive leads, cable placement, exceeded distance limitations, crosstalk, speed and duplex mismatches, and transceiver mismatches. Let's talk about bad cables or connectors. So faulty cables with electrical characteristics preventing a successful transmission, or faulty connectors which do not properly make a connection. They can prevent successful data transmission at layer 1. A bad cable could simply be an incorrect category of cable being used for a specific purpose. Bent pins in a connector or incorrect pinouts, they could also cause issues. So make sure all your cables are good to go and you don't have any bent pins. Next, we have a bad port. So a port may be bad on your network device. Oftentimes, you can easily confirm this by using the network connection LED and status indicators. So you check those, make sure the lights are doing what they're supposed to be doing. If not, you may have a problem where you might want to clean out the port, or if possible, you may want to swap that port out with another functioning port if possible. Next, let's talk about opens and shorts. So an open, this is a broken strand of copper preventing current from flowing through a circuit. However, a short occurs when two copper connectors touch each other, resulting in current flowing through that short rather than the attached electrical circuit because the short has lower resistance. Then we have splitting pairs in a cable. So an unshielded twisted pair cable consists of 8 separate copper leads. However, only 4 of those 8 leads are used for data, 2 to transmit and 2 to receive. This results in 4 unused leads. Some installers use those 4 extra leads to support a second Ethernet connection on a single untwisted pair cable. Although such an approach can function, non-standard wires are being used for connecting the second Ethernet connection. Therefore, you should be aware of any non-standard pinouts used in the network that you are troubleshooting. Then we have decibel loss. So the signal power of a data transmission might be degraded to the point where the transmission is not correctly interpreted by a receiving device. This loss of signal power, called a decibel loss, could result from exceeding the distance limitation of a copper or fiber cable. Then we have transpose, transmit, and receive leads. So some Ethernet switches support medium dependent interface crossovers, or MDIX, which allows a switch port to properly configure its leads as transmit or receive leads. You can interconnect such switches with a straight through cable as opposed to a crossover cable. However, if a network device does not support MDIX, it needs an appropriate cable or a crossover cable to allow its transmit lead to connect to its receive lead on a connected device and vice versa. Therefore, care must be taken when selecting cable types, interconnecting network components. Then we have cable placement. So because copper cables are subject to electromagnetic interference, you should arrange cables to minimize interference. Ideally, Ethernet cables should not be placed in close proximity with high voltage cables, generators, motors, or radio transmitters. So for example, when running cables between buildings via underground conduit, you should ideally place network cabling in a conduit separate from the electrical cables. Then we have distance limitations are exceeded. So if Ethernet devices are interconnected using a cable that exceeds the Ethernet distance limitations for the cable type, a digital transmission between those devices can be degraded to the point where the receiving equipment is unable to correctly interpret the transmission. Attenuation is the technical category for this problem. Therefore, a network design should consider distances between devices. Then we have crosstalk, and this can occur when an analog connection creates an electromagnetic field around its conductors, inducing its waveforms on a nearby analog connection. This phenomenon is most commonly experienced in an analog phone call. Crosstalk can be minimized by using a higher category of cabling, because higher categories of cables better limit the radiation of electromagnetic waves. Next, we have speed and duplex mismatches. So speed and duplex mismatches, they can be tricky to troubleshoot in a network, especially considering that connectivity is often maintained just at unacceptable levels. And then you have a transceiver mismatch. And transceivers, they must be selected carefully to ensure compatibility with the cable type and wavelengths that are in use. All right, so that was my quick little class on wired network troubleshooting, where we talked about bad cables or connectors, bad ports, opens and shorts, splitting pairs and cables, decibel loss, transpose, transmit and receive leads, cable placement, exceeded distance limitations, crosstalk, speed and duplex mismatches, and transceiver mismatches. In this quick little video, you're going to learn about wireless network troubleshooting as it relates to RFI, signal strength, misconfiguration of wireless parameters, latency, multiple paths of propagation, incorrect access point placement, refraction, and absorption. Let's talk about radio frequency interference. So wireless communication can be interrupted because of RFI. Common RFI sources that impact wireless networks include 2.4 gigahertz cordless phones, microwave ovens, baby monitors, and game consoles. So it is in your best interest to make sure that you don't have any of those devices next to your wireless access point so that it will not interrupt your signal. Signal strength. So the received signal strength indicator, or the RSSI value, this measures the power of a wireless signal. An RSSI value varies based on distance from a wireless antenna and physical objects interfering with the line of sight communication with the wireless antenna, such as drywall, metal file cabinets, and elevator shafts, etc. Some wireless networks automatically drop their wireless transmission rate when an RSSI value drops below a certain value. So the moral of the story is, if you want decent signal strength, make sure your device has a good line of sight to the access point, and make sure that there is nothing blocking the signal if you can help it. Let's talk about misconfiguration of wireless parameters. So a variety of wireless parameters must match between a wireless client and a wireless access point for communication to occur. So for example, the client needs to be using a wireless standard that's supported by the wireless access point, such as the 802.11 ABG, N, and AC standards. Wireless channels must also match. However, wireless clients usually automatically set their channel based on the wireless access point's channel. Encryption standards must also match, or you will have a security type mismatch. So for example, a wireless client using WPA would not successfully communicate with the wireless access point that's using WPA2. In addition, the service set identifier, or the SSID, of a wireless access point must be selected by the wireless client. In many cases, a wireless access point broadcasts its SSID, and a wireless client can select the SSID from a listing of visible SSIDs. In other cases, a wireless access point does not broadcast its SSID, thus requiring a wireless client to have a matching SSID manually configured. Finally, the most common issue is simply that the wrong passphrase is being used by the client to attempt to access the wireless network. Next, we have latency. So wireless networks, they can experience more delay than their wired counterparts. And one reason for the increased delay is the use of carrier sense multiple access collision avoidance, or CSMACA, in wireless local area networks, which introduces a random delay before transmitting data in an attempt to avoid collisions. Another yet similar reason for the increased delay is the fact that all wireless devices associated with a single wireless access point are in the same collision domain, introducing the possibility of collisions or retransmissions, which too can increase the delay. Then we have multiple paths of propagation. So an electromagnetic waveform cannot pass through a perfect conductor. Admittedly, perfect conductors do not exist in most office environments. However, very good conductors, such as metal file cabinets, are commonplace in offices. As a result, if the waveform of a wireless transmission encounters one of these conductive objects, most of the signal bounces off the object, creating multiple paths or modes of propagation. These multiple modes of propagation segmentation can cause data, specifically bits, to arrive at uneven intervals, which possibly can cause data corruption. This problem is similar to multi-mode delay distortion, which is seen in multi-mode fiber optic cabling. Next, we have incorrect access point placement. So wireless access points, they should be strategically located in a building to provide sufficient coverage to all desired coverage areas. However, the coverage areas of wireless access points using overlapping channels should not overlap. To maintain coverage between coverage areas, you should have overlapping coverage areas amongst wireless access points that are using non-overlapping channels, such as channels 1, 6, and 11 for wireless networks using the 2.4 gigahertz frequency. A common design recommendation is that overlapping coverage areas that are using non-overlapping channels, they should have an overlap of approximately 10 to 15%. Also keep in mind the use of the 5 gigahertz band, which offers many more non-overlapping channels. Next, we have refraction. So refraction, this is the bending of a wave when it enters a medium where the speed is different. It is important to track possible refraction when designing your wireless network, because if a signal changes direction in traveling from sender to receiver, it can cause lower data rates and high retries, and this can lead to an overall lessening of capacity. And then we have absorption. So this occurs when a material is converting the signal's energy into heat. Varied materials have different absorption rates. Wood and concrete can make a significant impact on signal strength because of how much they absorb the radio waves. So that was my quick little class on wireless network troubleshooting, where we talked about troubleshooting issues as it relates to RFI, signal strength, misconfiguration of wireless parameters, latency, multiple paths of propagation, incorrect access point placement, refraction, and absorption. In this quick little video, you're going to learn about common network service issues as it relates to mismatched MTUs, incorrect subnet masks, incorrect default gateways, duplicate IP addresses, incorrect DNS configurations, duplicate MAC addresses, expired IP addresses, exhausted DHCP scopes, rogue DHCP scopes, untrusted SSL certificates, incorrect times, blocked TCP UDP ports, incorrect host-based firewall settings, incorrect ACL settings, and unresponsive services. Let's talk about mismatch MTU. So router interfaces, they have a parameter called the maximum transmission unit that defines the largest packet size the interface will forward. So for example, a 1500 byte packet could not be forwarded via a router interface with an MTU of 1470 bytes. A router will attempt to fragment a packet that is too big unless the packet has its don't fragment bit set. If a packet exceeds an interface's MTU and has its don't fragment bit set, the router drops the packet. Normally, the router responds to the sender with an ICMP or an Internet Control Message Protocol message indicating why the packet was dropped. However, if a router is configured to not respond to such a condition by sending an ICMP, the packet is dropped without the sender being notified. Such a router is called a black hole router, and you can use the traceroute utility to help locate a black hole router. Let's talk about an incorrect subnet mask. So when one host attempts to communicate with another host on the same subnet, the sending host sends an ARP request in an attempt to determine the MAC address of the destination host, rather than forwarding traffic to the sending host's default gateway. Therefore, if a host has an incorrect subnet mask, it could incorrectly conclude that another host is on its local subnet, when in reality, the other host is on a remote subnet. As a result, the remote host is unreachable from the perspective of the sending host. Then we have an incorrect default gateway. So if a host has an incorrect default gateway configuration, traffic from that host is not forwarded off of that host's local subnet. Then we have a duplicate IP address issue. So hosts on the subnet should have unique IP addresses. If two hosts are configured with the same IP address, unpredictable traffic patterns for those hosts can occur. Then we have an incorrect DNS configuration, because hosts often use DNS to resolve domain names to IP addresses. addresses. If a host has an incorrect DNS configuration, that host will be unable to browse the internet using domain names as opposed to IP addresses. Then we have a duplicate MAC address. Although it's rarer than a duplicate IP address on the network, you could experience a duplicate MAC address. This is typically caused by a software configuration of MAC addresses. Then we have expired IP addresses. So a leased DHCP address that has expired for a workstation that could cause issues as well. We have an exhausted DHCP scope. Although this is rare, you may have a DHCP scope that has run out of addresses to lease. This could be the result of a DHCP exhaustion type of attack. You have a rogue DHCP server. This security concern could certainly cause troubleshooting headaches on the network due to the incorrect IP configurations that could result. This is often the result of users bringing in their own devices, either maliciously or accidentally. You have untrusted SSL certificates. So if using certificates for authentication, you might have an issue with the SSL certificate that is preventing such authentication. You have incorrect times. Because many network configurations rely on the correct time, you might have problems in the network due to a workstation, server, or network appliance that has the wrong time set. And you have blocked TCP and UDP ports. So perhaps your trouble ticket is the result of a blocked TCP or UDP port. This is often the result of a misconfigured security device in the network path. You have incorrect host-based firewall settings. So another security area that could cause problems are host-based firewalls. You have incorrect ACL settings, access control lists. They can have a direct effect on network traffic and could be the cause of one or many trouble tickets. And then you have unresponsive services. So a service that has failed in the network. This is another common cause of problems. All right, so that was my quick little class on common network service issues, where we talked about things such as mismatched MTUs, incorrect subnet masks, incorrect default gateways, duplicate IP addresses, incorrect DNS configurations, duplicate MAC addresses, expired IP addresses, exhausted DHCP scopes, rogue DHCP servers, untrusted SSL certificates, incorrect times, blocked TCP UDP ports, incorrect host-based firewall settings, incorrect ACL settings, and unresponsive services. Now, if you felt like you've gotten something valuable out of this information, go ahead and hit the like button, drop a comment, share this video, but most importantly, subscribe to this channel. Also, go check out my website, Technology G, so that you can get read up on the latest and greatest to help you successfully pass the CompTIA Network Plus N10-007 certification. And until next video, ladies and gentlemen, peace.